Hey everybody, it's time for another bonus lecture. So let's see, this is February 1st right now. So this is Valentine's month for those of you that celebrate it. So I have a little 5-year-old daughter, so of course she's been planning her outfits that she's going to wear to daddy-daughter dances. So any of you that have children or have loved ones, it is Valentine's month, so don't forget about that. That is important. So this month, for the bonus lecture, we were going to do a bonus lecture on the Atari 2600. So what I wanted to do was reverse engineer sort of a game cartridge, kind of download the binary image, update it, modify it, and then re-upload it onto another ROM or EEPROM and then play it. So as I was doing that, I realized I haven't done this in many years. So many years ago, I used to hack these cartridges and build things, and I had forgotten there's a couple little things that make it sort of inconvenient to do it without building a circuit board. So I didn't really want to build a circuit board, so I kind of wanted to do it just on solderless breadboard. So I'm still working on that to try and make that so it's easy so that you guys can follow if you want. So this month, I've talked about this before, programmable logic technology, and in many of the lectures I talk about programmable logic and mention things like PALs, programmable array logic, or GALs, generic array logic, or FPGAs, field programmable gate arrays. And what I wanted to do was I wanted to kind of, in this lecture, we're going to kind of take a look at something that's very state of the art. So programmable logic, the whole idea of it is that you have a chip, and the chip is made of kind of a fabric you could think of, a cellular fabric, and each one of these cells or blocks, right, can be reconfigured and then reconnected to each other through a connection matrix. So basically you have a bunch of inputs on a chip, you have a bunch of outputs, and then you can programmatically, through software, change the configuration of the hardware so the physical chip actually does something different, but it does it in pure hardware, so it does it very fast. And that's the whole idea of field programmable gate arrays and complex programmable logic devices. And again, I'm just throwing terms out right now. Don't worry about it. Um, but all this stuff kind of starts from the notion that I want to have a piece of hardware where I want to make some slight changes to it, and but I still want to have that hardware speed, right? So I don't want to do this process with software. I want to do it with hardware. So using software programming, I want to program a chip that actually modifies the hardware, all right, inside of the IC. So that's kind of what we're going to talk about. And what we're going to talk about is a series of integrated circuits by a company called Cypress. And they've been working on these things called Programmable System on Chip, PSOC, for many years. And they're currently up to version 6 right now. You can see here on the screen. And this is a pretty amazing piece of technology. And what's cool about it is if you take a look here, and I'll zoom into another picture here. But basically what this thing is it's got a Cortex M4 ARM processor and a Cortex M0 ARM processor, a bunch of peripherals. All right, so it's basically a microcontroller. But in addition to that, it has a bunch of programmable hardware. So you can program this thing and write software for the Cortex M4. You can write software for the Cortex M0, right? But then also you have all these hardware elements, right? And then you can drag these hardware elements onto your design and then connect them together, and then they can just run by themselves because they're pure hardware, or you can control them from software. So what this is, it's a hybrid programmable logic chip, basically. It's got a microcontroller. It has elements of an FPGA field programmable gate array, uh, but it's kind of a mixture, and it has both digital and analog elements. So the point of this is we can go look at things like CPLDs, complex programmable logic devices. We can go look at FPGAs, but those technologies are purely designed to be programmable logic. Now, that doesn't mean that you can't upload a processor to it. For example, an FPGA has so many logic blocks and so many cells, thousands and thousands of them. You can actually take the model of a processor and place it inside of the chip and then program it, and it would have that processor. But it's fairly complicated. So what I like about the PSOC technology is it's like a microcontroller with some hardware, some programmable hardware, analog and digital, and just for a few dollars, $20 or so, you can get a kit. I have some here. So this one's called like the PSOC 62 kit, and then it's got a bunch of stuff. You can see the back there. We'll look at these a little bit. And then here's a PSOC 63 kit, and then they've got other kits that have screens on them and whatnot, and the things are like $20. So for $20, you can start playing with it. So the whole idea is this PSOC technology will allow you to basically program a chip that has a microcontroller, two microcontrollers in this case, an M4 and an M0. So this thing is very, very powerful, and have hardware elements. So for example, you can make filters and amplifiers. You can make a radio with it. You can do all kinds of cool things. It's got op amps, and these hardware elements are programmable, so you can connect them and so forth, and then they can send messages via interrupts or other things to the software, to these cores. So anyway, so if you don't know what I'm talking about, if you haven't watched a lot of the lectures, obviously we talk about digital electronics and go into it very deeply, but we didn't do much on programmable logic. So what I want to show you right now is kind of the three different levels of programmable logic, and then we're going to kind of design, kind of go through the process of when someone wanted to design the first programmable logic chip, what were they thinking? What was their goal, right? So first, let's go and let's take a look here at some of these things. So the first thing is called programmable array logic, PALs. And you've probably heard this term if you're into electronics. So these are invented roughly in the late 70s. And PALs are in lots of things. And they're really cool because what they would do is they would have a number of inputs and a number of outputs. And the whole idea is, this is a kind of an example of one using 5-volt logic here. And so you have these inputs here, and then you have these are like inverters and buffers, and then you have this AND gate, you have this AND gate, then you have this OR gate, and then you have this output. Okay, and then you have these fuses right here. So now you've got this input, let's call this input A, and let's call this input B, right? Okay, so say like you want to do these various things with input A and input B. So say I just want to AND them together. I just want to AND A and AND B together, and I want to get that output. That's all I want to do. With this model right here, how would you do something like that? Well, say if A would be here and B would be here, right? So we need this signal here, and we need this signal here. So we want this fuse and this fuse closed. We would open this fuse and open this fuse, for example, right? Then now we would have signal A is coming through here, and we get that into this AND gate here, right? And then signal B is coming through here, right? And then we get that through this AND gate right here, right? And then that output, so now we have A and B. All right, now we have to be careful because we have these other signals, the inverted version, this would be open, so these would get pulled up. So this would be high and this would be high. So we would get these kind of high pull-ups here, which is not exactly what we want. So the whole idea is that you would kind of figure out what you want to do here and then design the logic such that you get the output. But just for a second, let's just say that these pull-ups were pull-downs and it gave us the signal that we wanted. So we'd have A and B here, and then there's an OR gate here, so then we just need to make sure there's a 0 here, right? So to get a 0 here, again, these are all being pulled up to +5. In this particular, so this is not a really good model of what I want to talk about, but the whole idea is we just need to make sure there's a 0 here. So we would do whatever, break these open or leave these closed so that we're assured that we're going to get a 0 here. So, and we'll get a 0 here if any of these are 0, right? Because they're AND gates. All right, so then we would have A and B. We bring it through here. We've got A and B, and then since this is 0, whatever output of this first AND gate is going to go through this OR, and then we're basically going to get A and B. So the whole point is that you sit here and you design these kind of generic architectures that have inputs, and then each input is inverted. Then you route the inputs, right, to various logic. Usually it's an array of ANDs and ORs, right, and kind of a matrix so that you can kind of pick off any of these terms, these AND terms. So you can get kind of, here's an AND term, and here's an AND term, and then we can OR it with this one, OR them together. So you can get any and term you want and then or them. So basically you can get any sum of products of these A's and B's. And that's the whole idea of this, all right? So that's the idea of a PAL, right? And then they have different numbers of inputs and different numbers of outputs. So, that's all there is to this. And so, but that's incredibly powerful. Now, the only problem is you would design this and you would write equations in some tool or some language, right? And there's different languages, and I've even talked about that before. There's PALASM and there's CUPL and CUPL and different programming languages for simple PALs, where you describe these equations that basically say, I want one output to be, A times B times C, or with C times D times F, whatever, where those are the inputs and the outputs, and then it would figure out what fuses to blow. But once the fuses are blown, they're blown, and then that's it. You can't program it again. All right. So going back here, so that's the PAL, right? And then the Wikipedia entry for this is not bad. You can kind of go through this, and then yeah, there's this example. Here's the program for it. So this is kind of saying, I want Q3 to be clear, and it is equivalent to not Q3 and not Q2 and not Q1 and not Q0 or Q3 and Q0 and so on and so forth, right? And you would code kind of using the specification of this language to kind of get what you want. So that's kind of what programmable logic is all about. Now, you go up the food chain a little bit, and companies still, you can still buy PALs. You can buy PALs from, I believe Atmel has them, Altera may still have them. They're just very old technology. So they've been kind of updated to the next step, which is a complex programmable logic device. And these are around and very, very useful. And these have anywhere from a few dozen or a few hundred gates or blocks to thousands of them. And then as they get into the thousands range, then they become so complex, then they go into or merge into the realm of what's called a field programmable gate array. It's just a bigger, more complex device. Now, typically, there's also one slight difference between complex programmable logic devices and field programmable logic devices, FPGAs, field programmable gate arrays, I'm sorry, is that the CPLD has a flash memory in it, has some kind of memory to retain the program, whereas an FPGA usually has an external memory. So what I like about CPLDs is they're completely self-contained. You program it and it keeps the program, so the hardware boots up and boom, it's that hardware. And then you can reprogram it hundreds of times, thousands of times. Whereas most FPGAs have an external memory. You program the external memory with the bit stream for the program, and then when the FPGA boots it, pulls in that memory and then configures itself, and then it starts running. So a lot of times they just don't have that memory built in, but that's not to say that some companies don't have a version of an FPGA that doesn't have a built-in memory. So anyway, and then FPGAs go up into the millions of gates. You can put whole CPUs, GPUs on FPGAs. And in fact, a lot of designers will design with FPGAs as they're designing hardware, so they don't have to actually build any silicon, right? They'll just build it in the FPGA, and then later that'll be turned into an IC. Anyway, complex programmable logic devices, there's a lot of companies that make these also. Altera, as shown here in the picture, here's an image of one. So they'll be kind of like this this linearity to it, where there's a bunch of logic and then there's an interconnection matrix, so that everything can kind of be interconnected together. This does not have any nice pictures of that, but CPLDs are really cool. You can get these for 10, 20, 30 cents. That have hundreds of gates in them, and then you can program them with fairly complex languages. You can still program with some simpler languages, or you can jump up to like Verilog, if you've heard of that, or VHDL, and then you can write fairly complicated programs that define very complex hardware. So the hardware can have flip-flops and memories and do mathematical computations. So with the CPLD, you can build computers, you can build simple processors and so forth. But you get to a certain point where it just kind of transitions into an FPGA. So that's kind of what a complex programmable logic device is. And surely we could talk about that, but then we would have to learn a programming, a hardware description language like Verilog or HDL, and I don't really want to do that right now. So then now moving up the food chain to the last piece of technology is the field programmable gate array. And these things can get really, really massive. These Altera Stratix chips are just massive. And then they cost like a couple $100 a piece. They are no joke. So these are really, really big. And if you look at this Wikipedia page, it might have a, yeah, so let me see here. Yeah, so in this case right here, now, again, these Wikipedia pages are a little out of date sometimes, but this is just showing, here's one particular FPGA, which is programmable logic, and it has, inside of it, it has a dual Cortex A9 memory, and then it has all these peripherals, and then it has the programmable fabric that you can do whatever you want with, right? So this is a very, very powerful IC to be able to design other chips with and experiment with them, okay? All right. So anyway, so those are kind of the three technologies. So PAL and GAL, which is generic array logic, and GAL is just a reprogrammable version of the early PALs, right? So the GALs they're exactly like PALs, except they have EPROMs usually, so that they can be reprogrammed a few hundred times. All right, and then you have CPLDs, a little bit bigger. They have hundreds to thousands of gates that you can program, and they have counters and flip-flops and much more complex input and output GPIOs. And then you go up to FPGAs, which are the top of the food chain in programmable logic, and these things get massive into many millions of gates, extremely complex blocks and so forth. And with any of these things, you can kind of pick a company. There's Xilinx, there's Altera, there's Lattice Semiconductor. There's a number of them, and many of them have, CPLDs and FPGAs, many, many, many different offerings. They have tools and kits, so you can get one of these things, you can program it, you can learn Verilog or VHDL and mess around with it, and I'd buy and suggest that you do at some point. But what I wanted to do with this is I wanted to talk about, like I said, the PSOC. And this is a cool piece of technology. So I've been playing with this since they came out many, many years ago with a PSOC 1. And what was really cool about it is when you design hardware, a lot of times you need a processor, a microcontroller to do all the work. Then you need some glue logic external, right, to the processor. Maybe it's a counter, maybe it's some flip-flops, maybe it's just a couple gates sometimes. You have some signals coming from the outside world, and you need to do something with those signals. The processor is not fast enough to do it, right? So you actually need some hardware. It's called glue logic. So a lot of times you'll put some TTL or LV TTL chips external to your design that have to do a few things, and it's a pain because you're like, oh, I just need a couple flip-flops or a couple AND gates, and I got to add a couple chips, and then it gets worse because a lot of times you have to deal with analog signals. So now I need op amps, I need filters, I need all kinds of analog stuff to process my analog signals, analog digital, digital analog, that kind of thing. So then I have to add more chips. So basically when you design kind of a modern single board computer, you've got kind of the compute, which is your processor, your microcontroller. It may be a microcontroller, which has internal memory, flash and SRAM, or it might even be a processor, a microprocessor that has external flash and SRAM or DDR RAM and so forth. But then you might have some glue logic, you might have some analog stuff. What if you could put all that in one chip? Now, that's what PSOC is, and PSOC is different from anything else because it not only has the processor, it has digital elements and it has analog elements. And as far as I know, there may be one other company that sort of has something a little bit like this Cypress technology, but not really. There's not a lot of there's maybe one company. So this is kind of the company, and this technology is really cool. So PSOC is really cool, and it's something you can get into right now and do stuff with it. And I just wanted to show it to you because it's just a cool thing, and I thought we could do something a little bit cutting edge in this bonus lecture. All right, so this is the portfolio, Cypress's roadmap for Q3 2019, whatever. We're just going to kind of scroll through here. And then if you take a look here, this kind of shows these different PSOCs. And you can see here they've got the PSOC 1, the PSOC 3, the PSOC 4, the PSOC 5, and they're kind of going up the complexity level here. And then with the latest PSOC 6. And then you can kind of see it's 150 megahertz M4 and 100 megahertz M0. 2 megabytes of flash. This thing is no joke, up to 104 GPIO. So this is a really cool piece of technology. And then if you scroll down here, you can just see in the PSOC 6 portfolio, There's these different variations of them, and a lot of these things are new or just came out, right? And they have just variations of different analog blocks. They might have more or less memory and so forth, and different features. And then some are the have Bluetooth. Bluetooth Low Energy integrated inside. So basically, this thing has got Bluetooth, a processor, analog, digital, totally programmable. It's pretty amazing. And then you go to this 64 line, which has this secure boot, which has more security features, which is a big deal when you're doing IoT stuff, because with all these IoT devices popping up and so forth, security is a big issue because they're everywhere, and your information is your passwords, your logins, your information, personal information can be hacked, and so security is a big deal in these things. All right. Anyway, now let's scroll down here. And now the PSOC 4 and 5 are available still, and you can use those if you don't need the functions of the PSOC 6. So you can use the PSOC 4 or 5 just as well, just to let you know. Now let's scroll through here, and I'm just going to kind of zoom down, kind of close your eyes if scrolling hurts your eyes. Here we go. And then let's just take a look at like this PSOC 63, which I've got over here. And here's one of the kits here. This is a 63 kit, I believe. Yeah, it's a 63 kit right here, and it's just basically just a dongle that you plug a USB into, and then I'm going to show you when we go on the bench more detail. But on it, it's got a programmer, and it's got a single PSOC 6 Bluetooth module that you can do stuff with. Now, I wanted to show you this because here's another, it's kind of an overview of all the features. These things are just, quite amazing. Like I said, it's got a Cortex M4, 150 megahertz with a cache. It's got a Cortex M0 Plus, 100 megahertz with a cache. It's got 288 kilobytes of SRAM. And this is shared, and it's got flash 1 megabyte. In this particular model, there's other models that go up to 2 megabytes. It's got cryptography, the DMA, real-time clock, and then over here in the analog, it's got now here's the cool thing. These analog blocks, you drag these in, and this is programmable hardware, right? So you've got 2 op amps, 2 comparators, you've got a 12-bit DAC, you've got a 12-bit SAR ADC. And you've got capacitive touch cap sense, and then you've got these digital blocks, which they call these universal digital blocks, and then this is a timer counter PWM, and there's a lot of them, 32 of them, and there's 12 of them. So basically, say you need a PWM, you can do that like on a microcontroller. You can do a PWM, right? Let the microcontroller do it, but the microcontroller maybe it has 1 or 2 PWMs. But with hardware, you got 32 of them here. You just drag them on here, program them, and they run without the processor. That's the cool part. Of course, you can control them from the processor if you want. Anyway, and then we've got, of course, the Bluetooth, and then we've got all these GPIOs over here in different ports. Anyway, so that's kind of what the PSOC is all about. So now, all right, so we want to program this thing, and this is a big, anything that's programmable logic, unless it's like a PAL, where you've got like a PAL with 8 inputs and 10 outputs or something like that in a very simple programming language that's maybe just the text editor that you can kind of wrap your head around pretty quick. You kind of write some code, it compiles it, you upload it, and you can kind of make an AND gate out of it or an OR gate out of it, or you can do some combinational logic function. That's kind of PAL stuff, right? But when we're messing with this is, it's complicated. This is cutting edge technology. So it's got Bluetooth, there's a Bluetooth stack. There's 2 processors on it. This thing can run FreeRTOS, right? So it's a multi-core, multi-processing system. So you can run FreeRTOS and run tasks on these cores and do different things. This thing is complicated. It's not simplistic. So if you really want to get into this, if you go onto YouTube and type in PSOC 6, well, here's one of them. There's PSOC 6 Academy or something. Anyway, I think this is, let me see, PSOC 101. There should be more videos here. There should be like 59. But anyway, if you go and type in PSOC 6, you can watch all these videos. There's dozens and dozens of them. And, their quality varies, and they kind of go really fast and kind of skip around. So, it's kind of hard to figure out what's going on if you haven't done programmable logic. But if you watch enough of them, some of the simpler ones, you can kind of get your head around and understand what's going on. But there's a lot of training. There's a lot of books on this. And then the cool part is when you're programming, you're not going to program in Verilog. You're not going to program in VHDL. You're going to program in C and C++, C, for your code, for your microcontrollers. And for the hardware aspect of things, you're literally going to drag and drop things, and that's what's cool about it. So the first thing that you're going to do is, if I can get here, yeah. So if you were to go to Cypress, now of course, you know, if you, I'm not going to, this is a massive, massive, this is a whole course unto itself. So I'm just going to kind of show you kind of the broad strokes of this. But you would go to Cypress, and then what you're going to go do is you're going to go download what's called PSOC Creator, and it might be on, so right now I'm on the PSOC page here. So if I go to, I think if I go to, let's go to, let's see here, Datasheets Development Kit. Yeah, so like the first thing is we can go to PSOC MCU Development Kit, and let's see what they say here. And here's the, so there's the PSOC 63 kit, right? So this one is a good one to start with. Here's the 62, which has all these different little elements. And then here's the Pioneer kit, which is kind of the one that I like because it's got all this stuff built into it. It's got an e-ink LCD, and it's got a bigger board with a bunch of different elements on it. This is $100 though, so for a lot of people that's going to be hard to afford. Now this one though, this doesn't have that LCD screen, but this is only $30, and it has all these pieces. And you just you break them off, untab them, and then you can kind of wire them and connect them together. So this is a nice system to get into, and it's only $30. But you know, if you're even on more of a budget, then we come back here to this one, and the 63. And I think this one's $15 or $20. Yeah, $20. And so here is the PSOC 6 BLE module, all right? And then here is a built-in programmer, so you don't have to buy the programmer, it just comes with it. This hooks up to your PC, then you're gonna write your code, you're gonna build your application in PSOC Creator, which I'm gonna show you and we're gonna do. And then this right here links up to this PSOC and then programs the PSOC for you, and then once it's running, that's that. And then this, of course, ironically, coincidentally, is a PSOC also. So it's a PSOC, they use to program the PSOC, all right? And then if you want, you can break this tab off and you can just use this as a programmer. So this is a standalone programmer. So then if you were to build your own board with a PSOC on it or a PSOC module, then you could use this and you just take these few connections, ground power. It uses software wire debug, SWD, which is an industry standard for programming devices. And you just connect that to your chip, and then you can program your chip. So this is a really, this, you cannot beat the value of $20. Come on, $20. So it's like, you know, 1-2 coffees or something for you coffee drinkers out there. All right, so anyway, that's what I recommend, is that you get the PSOC 6 BLE prototyping kit, CY8C Proto 063 BLE, and then of course this is, you know, Bluetooth enabled also, so you can make applications that talk to your phone or whatever. All right, so now that's that. Okay, so we know maybe we're going to be using this, and that's what I'm going to be using on the bench. Okay, so now we need some software here. So let's see here. Let's go get our software, and we'll go back here, and I think it's under Design Support. All right, and then we're going to go here to PSOC Creator. Now I've already installed this on my computer, so I'm not going to do an installation with you. I'll tell you, it's a normal kind of installer, a Windows-based installer, and you just install it, and then it's going to need to do an update, so you got to do a bunch of updates. So after you've installed it, you got to go and do updates, and I'll kind of show you that once we launch the program, and then you got to update the software libraries and this and that. So the updating is a little bit of a pain, like anything. Something updates and then it breaks something else. So sometimes if it doesn't work, you got to just uninstall it all and do it again. So, you know, hardware stuff is painful. I'm not going to lie about it. It never works easily. Like with software, you know, you want to do some JavaScript, you just open a text editor and you write JavaScript and load it in a browser and boom, it works, right? Or if you're a desktop programmer, use Visual Studio like I do, Visual C, C++, you know, that's a very, very advanced, mature tool. You write your code, it just works. But hardware stuff, hardware tools are for hardware guys, and we're expected to be a little bit more tolerant of fixing things, right? So, you know, get used to it. Anyway, so PSOC Creator 4.2 is the latest version. Now, there's also something called PSOC Designer, but that's only for PSOC 1. Don't use that. Don't mess with that. You want PSOC Creator 4.2. And then as of this video, there's a beta of 4.2 or 4.3. Don't use that. Just stick with 4.2. All right, and then of course, if you're watching this video later, whatever the latest solid version is, 4.3 or 5, use that. Okay. All right. So anyway, you would download this here. you would just click download and download it, all right, and then you would do the installation. And then here, there's all these things, new features, getting started, design support, application notes, all this kind of stuff, training. You watch all these videos. This guy's name is Alan Hawes. He's the executive vice president of the PSOC stuff. And then there's all these videos, which are these links. So you can just kind of go through and watch all these, whatever. More downloads of various things. All right. So that's what you need to do. You need to get PSOC Creator on your computer. Okay. All right. Now, once you have PSOC Creator on your computer, let's go ahead and let's launch this program. So let's see wherever I hid the thing, which should be right here. And then I'm going to tell you a couple tips and tricks also. So when you get, this thing takes a second to load. When you get your kit, right, and you plug this thing in, right, you plug it into your computer, it's going to start trying to install drivers and this and that, and then it'll hopefully find everything and it'll be cool. But the firmware on it typically is out of date, right? And the firmware that's really important is the firmware that's on the programmer here, right? The chip here, right? That's the chip you're going to program, the PSOC. We don't care what's on that, right? There's some demo on it, who cares? But what we care about is this. This thing right here is the programmer, and this thing is called KitProg. There's KitProg 1, KitProg 2, KitProg 3 as of today. There's KitProg 3. So, but the hardware luckily stays the same, but the software, the firmware changes. So to make this into KitProg 3, you have to update the firmware. The tool, PSOC Creator, expects KitProg 3 firmware on this. So when you just buy one of these, of course the firmware is a year, 2 years old whenever they manufacture these, you're going to have the wrong firmware. So one of the first things that you're going to have to do is you're going to have to upgrade this firmware. And I'm going to show you how to do that, also the tool you need to do that. But for now, I just want to show you that, and just let's launch this. Okay. So it's like any of these tools, it kind of brings up information, this and that. It has a view where there's events and any kind of stuff they want to tell users and whatnot. All right, and again, this is not going to be a comprehensive training video on PSOC. That would take, it took, the Cypress guys 100 videos to train on this thing. So I'm just going to try and show you that you can do stuff with this and how cool it is. All right. All right, so the first thing that we have to do is we're going to create an application. We have to select the chip that, or the board that we're using, the board, the chip, and kind of get a schematic and get a project so that we can write some code if we want, and we can do some hardware development. All right, so we have to do that. Now, the other thing that I told you about is when you install PSOC Creator, another thing that it's going to install is called this PSOC Programmer. All right, let me show you this. And this thing, bring it over here. So this thing is going to allow you to update the firmware. So right now the firmware is already updated to KitProg 2. So then what's going to happen is when you run this PSOC programmer, since the PSOC programmer comes from PSOC Creator, it wants to see KitProg version 3 firmware on your hardware. So this thing's going to come up and complain to you and say, hey, you've got old firmware. And it's going to have a different view, and it's going to say, would you like to update the firmware? You're going to say yes. And then it'll update the firmware, it'll reflash it, and then typically it'll either reset fine or it'll brick. It'll just stop. So then just unplug it, plug it back in, and then it'll kind of come back up and things will be okay. But you must update the firmware to KitProg 3, and maybe when you watch this video, it's a year or two later and it's KitProg 4, KitProg 5, because you're using another version of PSOC Creator. But this is what you do it with. Now, other than that, what's this for? Well, this is their general PSOC programmer. So what this allows you to do is a standalone tool where you can select a programming device. Now, in this case, we've only got this KitProg, but there are other programmers we could get. We can buy programmers that can program PSOC chips, right, on the third-party market also. So those would come up here, then we would select them, and then we would be able to select how we want to program it, this and that, and then we would go over here, we'd say file, we'd say file load, and we would load the hex file, right? And then we would download that into the PSOC chip. So you can use this to program it, but you don't need to use this because this functionality is integrated into PSOC Creator. So let's go back to PSOC Creator. All right. Okay, so we got this tool, and this is a really big tool. You know, if you're going to get into this, you got to read this and watch all these videos from Cypress. But What we're going to do is just kind of jump in, and I'm just going to kind of guide you to do a couple simple things, all right? So let's see if we can get some stuff working here. All right, so the first thing is we need to create a workspace, all right? So what we're going to do is we're going to create a project, which will then create a workspace, and then like if you've used any software tools, a lot of times they have what's called a workspace, and then under the workspace are various projects all contained within the workspace. So first we need a workspace. And then within the workspace, we are going to put a bunch of different projects, right? So now, in my case, I've already kind of created a workspace, but I'll go ahead and do this again so you can see it, and then I'm going to kind of load my previous one so I can kind of use that. But here's what you would do. So there's no create workspace here. All right, so if you come here, there's only new project, all right? So we got to do new project. Okay, now it's going to ask you, what do you want to use, all right? So the target device is the PSOC 6, and then the module name that's on that kit is this 416045-02. And the only way you would know that is you got to read through all this documentation, you got to look at this thing, you got to read on here and all that and figure it out. Otherwise, you might be targeting the wrong chip. So that's a little detail. Now, a lot of the PSOC 6s are all very, very similar. So you could actually write some code, and it would compile and all that, but when you tried to upload it, you would get a device ID mismatch, and it just wouldn't work right. So this is a pain, and this little one thing can make things not work. So you got to be careful of that. All right. So we're going to create this project right here, and then notice here, this is just to create an empty workspace, but I don't want to do that. I want to create a project and a workspace by doing this. Okay, so we're going to do this. We're going to say next. All right, now we could do a code example from the library, but we're not going to do that. We just want a blank schematic. Now, these things right here, SimSys, this is the Cortex software library that's been developed over years. Just leave all these disabled. This is IAR, company that makes C compilers and whatnot. Leave that alone, and then this is Makefile stuff. Just leave this alone. So just leave these all disabled. Okay, now here's where we get into things. So the first thing is I do not like programs putting anything inside of my Windows C drive. I don't know why everything wants to put everything in my documents. That's just horrific. So what we're going to do is we're going to go over here. So we're going to select that folder. All right, so now that's good. And now I'm going to give this another name. So I'm just going to call this, bonus crash course electronics workspace. All right, and then design one. Yeah, that's cool. We'll just leave it like that. Okay. Now, if grab the hard drive, we can see there's where it just created that. So we've got this design, we've got this workspace, and we've got some information here. So we're going to keep looking at this as it develops things. One thing that I like to do when I do anything is I like to understand what's going on. And I don't like to just use these big tools and not understand what files are creating and this and that, because as you develop software or hardware, you've got files, in one place, you got files in a local directory, you got files in information in the registry. If it's Windows, it's just all over the place. You just have no idea what's really going on. So it's really nice to look at the workspace and project directories so you can understand what is going on inside here. All right. Okay. So now this is where this stuff gets cool. So let's move this down here. All right, and now bear with this tool. This is a very complicated tool. It looks very Eclipse-based to me, so probably is, and that's why it's so slow. Anyway, if we look at this tool, we see that there's this kind of sheet right here. This is the schematic. This is where we're actually going to draw the schematic of our design, right? So this is a microcontroller, two of them, two microcontrollers, a Cortex M4 and a Cortex M0, and there's a schematic. So this is like a new thing, right? It's like, where's your code and all that? So, all right, so check this out. So over here, these are all the components that we can put into our design that are inside of this chip as programmable logic, all right? Then over here, of course, this is our normal view. We've got kind of our workspace and our first project. And then we can add more projects under here and do whatever we want with them, all right? So now, right now, if we go here and we look, in these C files, we can see there's core 0 and then there's this core 1. So this is the M0 course and this is the M4. If we go back and we look here at this main, so there's going to be two mains. So remember, this thing is multi-processor, right? So this is super cool, multi-processor. So if we go look at the main here, and it'll open that up, there's nothing in it right now. So there's a little bit of code that it's generated, and to enable the, so basically when this thing starts up, it starts up the M0, then the M0 starts up the M4. That's this call right here, then it goes into an infinite loop. Then if we go to the M4 code, it just enables interrupts and then it goes into an infinite loop. So everything is empty right now. So we're not going to mess with it. We're just going to leave it empty. Okay, so let's do something together. All right, let's build something. All right, so the first thing that we want to do is let's take a look over here and see what kind of stuff we have. So here's analog. Here's the capacitive sense stuff. Here's communications blocks. Here's digital. Here's ports and pins. Here's system. There's all kinds of cool stuff in here, right? So now, for example, let's say that we want to do something with analog digital converters. We would open that up and we have this, a SAR ADC, all right? If we wanted to do something with amplifiers, right, there's an op amp right there, okay? If we want to do something with, a DAC, there's different DACs right there. So there's all these different elements. Here's UART. There's a couple different, there's only one UART. I think there's a couple. There should be one SPI thing. Anyway, so all these blocks, and then here's pure digital logic, right? So, here's a PWM, a quadrature decoder, a timer counter. Here's logic stuff, and this, and that, all these different things. So here's those gates I was talking about. So if you just want, you've got your microcontrollers and I just need a few gates, those few gates are on the chip, and then what you're going to do is you're going to run the external signals into the chip from the GPIOs, connect them to this hardware, do whatever you want with them, or send them back up, send them back out. It's super cool, all right? And you're not going to have to write any Verilog code or VHDL code. You just drag and drop things and connect things. So it's very, very cool. All right, so let's close some of this stuff up so we can kind of see what's going on here. All right, so let's do kind of a hello world program here. All right, so we're going to do a hello world program in pure hardware. All right, without the microcontrollers doing anything. So let's check that out. All right, so let's blink an LED. Now, if we look at the kit on the back of and then I'm gonna switch over in a little bit so you can see everything on the other screen, of course, simultaneously. But if you look at the kit, there's a bunch of pins here, right? And on the back, it's labeled with port numbers. So, P01, P02, P23, et cetera, et cetera. And then if you look around on that and you look around on the back of the kits, themselves, they have kind of labels showing what's connected to where. So what we need to do is we need to figure out where the LEDs are. So when I'm looking at this kit, the LEDs are on P63 and P71. There's two LEDs on this kit. They're not RGB, unfortunately. So P63 and P71. All right, so that's where that is. So we're going to kind of remember that for a second. So what we want to do is I want to blink an LED. All right, so let's see what we can do here. Let's try and find something that would allow us to do that. How about we go get if I can find it here, we want let's do a PWM. So we're just going to take a PWM, and I just dragged it out there. See, I just dragged the thing out there. That's it. All right. So just taking this and dragged it out, and this is going to be what is going to generate our signal. So now, if we look at this PWM, it's got a bunch of outputs and inputs on it. So here's an input, which is the clock. Here's an output, which is interrupt. Here's the PWM signal. Here's the inverted PWM signal. Here's the compare out. Here's the overflow. Here's the underflow. It's got all these kind of things. Now watch this. When I click into this, double click, then this opens up, which allows me to change its name. All right, so we can make this whatever name we want it. And then what's going to happen in the software, when we want to communicate to this thing and call API functions, and those API functions are based on what's called the PDL, the Peripheral Driver Library. That's what Cypress created, this big driver library that has all the software and driver functions to talk to this hardware. That's called the PDL. So this compiler is smart so that whatever name you give it here, so say like if there's an API function like start or stop, you'll just say the name PWM_1_start, and then that will call the start for that hardware element. So it's really cool. So you make these whatever names you want, all right? So it's PWM1, we're just going to leave that, all right? And then the PWM resolution here, we can, click on this. It can be 32 bits or 16 bits. There's a prescaler. There's alignment. There's a number of these different things that if you dig down into how PWM works, and pulse width modulation is what it stands for, if you haven't heard of that. And what it is basically is a PWM signal is a way, and I of course talk about this in lectures, but a PWM signal is a way to synthesize an analog voltage by how long something is on relative to how long it's off. So for example, if we have a signal, and you see the signal right here, it's a square wave. And right now you can see the square wave is on, then it's off. It's on, then it's off, the same amount of time. If that square wave is fast enough, right? And if we take that and we were to filter it through a low pass filter, we would create something, a signal, and that signal would be at 50% whatever this high would be. So if it was a 5-volt system, it'd be at 2.5 volts. So the whole point is by varying the duty cycle, which is the relationship of how long the thing is on to the total time of or total period, right? Then we can vary the signal strength. So if we put these pulses through an LED and we change this duty cycle, the LED will get brighter or dimmer, all right? Now, if we slow this way, way, way down, right, to hertz, then we'll be able to turn it on and turn it off and blink it, okay? So that's kind of what we're going to do here. All right, so right now the period is 32,768. All right, so that's the total count, and then the compare value is at 16,384, which is half of that. So that's why the signal looks like this. Now watch this. We can actually change this. If I put 1,000 in there, you see the signal, see how small it is? Right? So it actually modifies it and changes the graphic, which is really cool. And then it recomputes what the duty cycle is. So if I put 100, it's a 0.31% duty cycle. See how cool that is? If I put like 10,000, it's a 30% duty cycle. All right. So right now we're going to put almost 100%. We're going to put a 50% duty cycle because I want this thing to turn on and turn off. But we're going to turn it on and off slow so that we can see it turning on and off. Okay, so check this out. So that's the PWM. All right, let's go to advanced, see if there's anything here. Oh, and again, you got to look through all the documentation to understand what all these things do. All right. We want the output polarity. Now the LEDs are active low, but since the PWM is going to be high and be low, it doesn't matter if it's active low or active high. It's going to hit one of those either way. So we don't have to invert anything. We'll just leave that uninverted. And then we don't need to mess with this. This is some other more advanced features. Okay, so now we can just click OK. All right, so there's our PWM. Now, the PWM, you see, has a clock input. So we need a clock input to this. All right. So let's go try and find a clock. So we can always search through here, but another thing you can do just to save yourself time, because a lot of times things are where you wouldn't think they are, just type in clock. And we can see there's a couple different clocks here. So there's under digital utility sync and this UDB clock enable. I don't want to mess with that. I don't want a real-time clock. I want this. So I'm going to take one of these clocks. Okay, and it's going to be called clock 1, and you can see it's at 1 megahertz. Now, let's talk about wiring things up. So over here you can see there's these tools, right? This is a wire tool right here. Also, you can press W. So this is how you connect wires. So if I press W on the keyboard, see how it turns to an X, and I put it right there, and this is how you connect wires in your schematic. Now, another thing you can do, I just press Control Z, is if you drag something on top of something and then drag it away, it's smart enough where it'll kind of create a wire for you. Okay, you can kind of do that. All right, but again, this wiring thing is not the most robust thing on earth, so be careful and make sure things are actually wired. All right, so let's go ahead and let's double click this and see what's inside of a clock. Okay, now so we got this built-in thing again. We're not going to mess with this, but in basic this is good. So clock type new, existing, we're going to use new. All right, and then built-in, the name of the clock is clock 1. We're just going to leave that like that. Now we can select the frequency here. So we can do it as hertz or kilohertz or megahertz. So why don't we just make it hertz? All right. So now if we make this thing hertz, the period of our PWM is going to literally be hertz. So we're going to see this thing blinking on and off, right? So let's make it like, we'll make it like 3 hertz. This is going to be really, really, really slow, right? But that's cool because we'll actually be able to see this thing blink, all right? So we're going to make it 3 hertz, and I'm going to apply and click OK. All right, so now we've got our clock, we've got our PWM. All right, so that's cool. Now we need to get the signal out to the GPIOs of the chip, okay? So we need to get it out to the GPIOs of the chip. So now let's look for an output and then take a look here, ports and pins, digital output. So I'm just going to drag one of these. Now where do I want this? I want it at PWM or PWMN. Now we've got 2 LEDs, so what we could do is we could put one on one and one on the other. That'll be cool. Let's just do that. So I'm going to grab that. I'm going to drag that, and then I'm going to take this and Control C, and I'm actually going to copy it, and then I'm going to drag that on there. Okay. Now we've got these 2 things which are going to connect to our LEDs. Now this time I'm actually going to relabel these. So I'm going to call this one LED 1. And then I'm going to come back to that in a second and play around with it. And then I'm going to call this one LED 2. Okay? Now, we've got both of those, and I'm going to Control S to save. Okay, so now let's go into LED 1. And now, this is where things get complicated. So each one of these GPIOs is a very complicated I/O pad. It can do input, it can do output, it can do analog, it can do all kinds of crazy things. It's got pull-ups, it's got pull-downs, it's got strong drive, it's got slew rate control. It's not a simple thing. So that's what this dialog is all about, to let you select all these things. So right now we are doing a digital output. I want a hardware connection, meaning hardware is going to do this, not software. So we leave that. Then we want strong drive. We can change what the drive is, right? We can put strong drive, we can put open drain, all these different things. But I want it to drive it in both directions, high and low, with this with this totem pole FET driver. Okay, so that's what I want. I don't care about the initial state, maximum frequency. I don't care about that. We could slow this down, right? But we'll just leave it at 100 megahertz. Okay, it doesn't need to be bidirectional. If we want to read the data sheet for this, we click data sheet, and then we can see and read about the GPIO and understand what all these settings are. Okay, but that's what we're going to do. We're just going to do that. Now let's go to LED 2, and it's going to be same thing, strong drive. It's a digital output, hardware connection, and click OK. All right, and make sure I clicked them both. Yep. Okay, so now we've got them both there. So there is our hardware design. So we've actually, without VHDL, without Verilog, we've designed hardware. So this is physical hardware. Now there's a couple details. We need to connect, so this LED 1, this piece of software does not know where LED 1 is on the chip. So the chip has got a bunch of pins on it, right? We need to associate LED 1 with a pin on the chip and LED 2 with a pin on the chip, so that signal will be sent to the actual LEDs. Okay, so that's what we're going to do now. So now what we're going to do is we've got this, and we're going to build this application, and by building the application, it's going to bring everything in and generate the software. Then we can go into it and add the software and modify the pins and all that. So this step is kind of, you got to do it to kind of do the next step. So you're going to go to build here, and you're going to say build design, Shift F6, and there's lots of different ways you can do it. You can do it there, you can do on the project and right click, you can do all kinds of stuff. And then down here, you'll see it's doing all the stuff. And some of these terms are interesting because you've probably never seen them before. So you can see this, elaborating the design, then HDL generation. So it's actually generating HDL, hardware description language. It's generating that. Now it's doing analog placement, analog routing, code generation, digital placement, digital routing. Now it's generating the bit stream. It's verifying the bit stream. Now it's doing a timing analysis, which means it's checking to make sure that there's timing closure, that everything is going to operate and within timing constraints and nothing's going to be broken. So basically it said, you want to put a PWM, a clock, and a couple of GPIOs. I'm going to take all the fabric of this PSOC 6 and I'm going to put that stuff someplace for you inside of the fabric. Now we could say where to put it if we want to be that crazy, but it'll do it for us. That's what this fitter is about. It fits it and puts it inside of there. Then once it gets done with all that, now it's got the hardware aspect of things. It's generated the hardware description. It's generated the bit stream to program the hardware. Now the next thing that it's going to do is it's doing the software. So now it's running the GNU compiler to write ARM code, take the C code, assemble it, create a binary for the M4, for the M0, bring in all the PDL, the peripheral driver library, all that stuff, and create these applications so that we have a program. And it's successful, thank goodness. So now you can see, look at all the stuff that was created. Okay, a lot of stuff. Now, if we go back and we look at the M0 file, there's still nothing else in it, but now notice that this is not redlining anymore, showing us a problem. And then if we go back to CM4, again, there's nothing in this, and that got rid of that, and so that's working. Okay, so now let's go to the CM0, and now this says enable the CM4, and then it just sits here and does this infinite loop. Now, we don't need to enable the CM4. We could just not enable that if we want and not even use it, right? We could just comment that out. Well, we'll just leave it for now. Now, this processor right here is going to run, and then the CM4 is going to run. So we can put our code here. We can put it in the Cortex-4 here. We can put it in both. We can do whatever we want. So why don't we put it into the Cortex-M4 section, okay? So we're going to place initialization code here. Now, the hardware is fit and placed inside of the hardware, but you still have to do a couple things with this. So you have to make a couple calls to the API to turn things on usually. So that's a little gotcha. Things won't work, and you'll be like, why is this not working? Because you got to make a couple calls to turn things on. Okay, so let's go back and let's look at our design again, and let's see what we got to do here. Now, when we go back to our design here, let me go here. So when we go back to our design, what do we have? We've got an LED, we've got a PWM, and we've got a clock. All right. Now, I'll tell you right now, for GPIOs, you don't need to do anything to them. They're too simple. There's nothing to do. But like the PWM, you do need to do something to. All right. So this is called PWM1. All right. So if we go back to this right here, what we want to do is we want to say sci, and then we want to say syslib. Oh, I'm sorry. We can actually get away with doing just this. PWM_1_S, and then you can see the code completion will help you find things. So PWM start, like that, no parameters. So that starts up the PWM. So now it's taken care of. You can do it with, I was thinking of lower level functions to do it manually, but you can use this higher level function to do it. Now what's nice is it takes the name, and then the start subfunction is you can access it by using the name inside of the design. So that's really, really convenient, so you don't have to do any weird naming things. Okay, so there's the PWM. Now the other thing that we had is the clock, right? So, and I believe I just called it clock, clock 1. All right, and the same thing, we want the start function. And let's see here, let's go back to the design. It's clock_1. And now, and again, many of these things, so this one doesn't need, so clock 1 enable, we don't need, it's going to be enabled as it starts up. So this one doesn't have a start, so we don't need to call it, so it'll just run. But the PWM does have one. So again, you kind of figure these things out as you go. And so the clock is already going to start up running. We can enable or disable it, but it's already going to be enabled. The PWM, we did need to start. We don't need to do anything with the LEDs, but now we need to assign the pins here. So that's another little thing that we need to do. Okay, so now how do we get to that? Okay, so check this out. So this, over here in the project with all these files, the top level designs, this is the schematic, that CYSCH, that stands for Cypress schematic. That's this thing, the schematic, okay? All right, and I'm just holding control and scrubbing. But the design-wide resources, we need to go to this page, and this we haven't seen yet. So this has a bunch of stuff inside of it, okay? So here's the pins. So this is what this module looks like. That Bluetooth module on there looks exactly like this. So that is what's going on over there, all right? And we need to assign some pins here. Now there's all these other pages, which if you use them or don't use them, all right, they'll show up here. All right, so there's no DMA. Here's all the clocking stuff, very, very complicated, interrupt stuff, system stuff. There's all kinds of stuff. And again, that's why you have to, there's an enormous amount of documentation to read to understand everything that's going on here. But now, right now, look what it's done. The fitter assigned LED1 to P00 and P01. So if you were a programmer and you wrote this thing, that sounds pretty reasonable. What it did was it said, what's the first port 0, what's the first pin 0, and it just started assigning these things because they're all more or less generic. The PWM could be assigned to any of them. So it just said, I'm just going to put it to the first 2 inside of the list, and that's where it put it. But those are not correct. We need to put it, if we look back at our design here, they should be on P63 and 71. So we're going to put LED1, and how you do it, it's over here, you can see it. So we're going to put it here on P63, so take our time here, you can see 63. And then when you do this, it's kind of cool because it shows you all the different hardware peripherals that are kind of connected to or potentially can go to that P63 thing, that P63 pin. Some hardware can only go to specific pins, and it's showing you, hey, these are the specific things that go to that pin, so be careful. If you use this for the LED, you're not going to be able to use these functions. So I don't care because I just want to blink this LED. So I'm going to put it at P63, and then it updates, and then the other one is P71, right? Was it P71? P71, P71, and yes, okay. P71, so we're going to connect it there, and again it says here's all the things that only can go to this pin, but I don't care. All right, so we've got that and we've got that. All right, so I'm going to go ahead and save that. Okay, all right, so now we're getting someplace. So now we've assigned our chip pins. We've went into our code here and we've said start, and then this is just going to go into this empty loop and do nothing. So we could put the processor to sleep and that PWM is still going to work, and that's what's cool about it. All right, okay, so let's see here. And I think that's about it. So now, here's some other little tips and tricks. Now, before you build this, you got to kind of go into a couple of these menus and make sure things are correct. And and I apologize, I didn't write this software, but engineers make a lot of assumptions. Once someone shows you something, you're like, oh, that's easy. But if no one shows you this, you will sit here for hours and days and just not get it to work, and it'll be very frustrating. So if you can't get something to work, try to Google what's happening. It keeps saying this or it does this. Just Google it. PSOC creator does this, and you hopefully will find it. But anyway, you got to go up here to project, go to device selector, and we have to make sure it's got the right device. So we need to make sure it's got this 416045-2. That's the actual module that's on that little dongle. Sometimes you may have picked the wrong chip, and it might pick the chip that's inside of the module. It'll compile the code, but it won't work right. So you need that. Make sure that's right. So that's okay. So we'll just hit cancel. We don't want to change it. So that's cool. Now another thing we need to look at is, let's go look at the build settings. Okay, and I believe I want to be here. Yeah. So let's hope this opens up a little bit. Okay. So one of the important things with this is you've got a lot of different compiler settings here, and these are complicated, these are advanced things. Even if you're a professional programmer, messing with the compiler settings a lot of times is something you may have never done in your life, actually. So you got to look through these things and understand what's going on. But anyway, there's all these different settings here. Luckily, in this case, we're not going to have to change anything, but you can see, like under here, under synthesis, for example, quiet output synthesis goal is speed. We could change the synthesis goal to area, meaning I want to use up less area of the chip fabric. I don't care about speed. I want it to use less space, and I want it to run slower. I'm okay if it runs slower, so it can route things around in long distances, right? So that's where you would change that. So you can play with this stuff, right? Optimization effort, exhaustive, meaning, I'm going to go through until I find what I want to find here. Or you could put none to speed up the compilation process, or put normal, right? That's what these things are all for. So you got to go through these things and understand what's going on. Now, one thing I want to focus on is this peripheral driver library. This is a source of a lot of confusion and problems that I've had with it, and thousands of other people have had with this. So select this, make sure that you have the latest peripheral driver library. So what that means is, when you go and you install this software, and I'm going to show you in 1 second after I get out of this, there's an update thing inside of help. It's going to update this peripheral driver library. After it does that, this thing a lot of times will not update. It'll keep it pointing to the wrong library, So you got to go in there and make sure it points to the latest library, whatever it is. In this case, it's 3.1.1. But it'll point to the wrong library, then the software won't link, and it'll just be a mess. All right, then you go down here, and there's some things that you need to do. Like if you want to use FreeRTOS, you got to click this, right? And then you can select which heap you want. There's multiple heaps for memory management, right? And then if you want to use printf to kind of get the standard C to the user console, you have to click retarget IO, right? So right now we're not using that, so we don't really care about that, and we haven't made any changes here, so we're not going to have to hit apply, and we're just going to cancel this. But that's where you find this. You need to go into the build settings, and you need to mess with that, unfortunately. Okay, now I just was telling you about the other thing, which is here, and you go here to this update manager, and you go to this update manager, you click this thing, and this goes out and talks to the server. that's the idea. Checking for updates. And like all update managers, it works, it doesn't work, it's half broken, whatever. You got to be careful of it. And a lot of times after you do the update, then you have to shut this thing down and restart it and all that. So you can see I've got this library right here, and the last thing that it did was a network error. So in my case, I had to actually go to Cypress and then type in peripheral driver library, and I found the page in Cypress's website, and then I downloaded the peripheral driver library 3.1.1. I closed this application. I used its installer to install it. Then I went manually in those build settings and changed where it was. So this didn't work for me. The other versions all worked, right? But this one didn't. But anyway, it'll allow you to update the program. Remember we saw that, and then all these other PSOC things. So this is kind of what you'd ideally like to do, and if you're lucky, it'll just work, right? But with me, nothing ever just works, so it's always got to be painful. Okay, so that's that. So we're almost ready, right? So I'm not showing you anything over here because I want this screen, I wanted you to see everything over here. There's really not much you're going to see until we blink the LED, but I'm going to get that in 1 second. All right, so what I'm going to do here is we're going to go ahead and we're going to build, we already did the build, so now what we're going to do is we're going to go ahead and we're going to do the programming. All right, so now what I'd like to do is as we do the programming of it, I actually want you to see what kind of happens there. So I'm going to go ahead and turn on this other camera so we can see what's going on. Okay, so we're looking at the board here, and so right now it's running another piece of software that's doing kind of a breathing program. So that's just running on there. So we've got everything all hooked up, and again, this is the KitProg programmer, and it's got KitProg 3 firmware on it. These are our two LEDs, and if I zoom in a little bit more here, I'll zoom in too much, we'll lose focus probably. This camera never cooperates with us. There we go. So anyway, we've got those two LEDs, LED 3 and 4, if I were to turn this around real quick, so you can read it. And there they are right there, LED 3 and 4. So those are what we're trying to blink, okay? Now, when we program this thing, ideally, we're going to see some activity going on here. This will be blinking or doing something when it's programming. So that's what we're going to try and do, all right? So let's go back over and let's try and upload this code and see what happens and see if we can get this thing to blink. Okay, so we built the program, so that's all cool. So now what we want to do is we want to program this. Now, okay, there's another detail. We have to make sure we have the correct programmer selected. So if we go here and we say select target and program, we can do that. So we can go here and we can say select target and program, or we can go here and we can press this little button right here and click program. So, and I think we can also do it right here. We can right click, and I'm sure there's a device selector. Is there a program right here someplace? I guess not. All right, so I'm going to click that little program. We could do debug also. Okay, now so now what's happened is it's over KitProg 3, it's communicated and it says, hey, there's two different processors here on this thing. So anyway, what you're going to do is you can select either of them, I believe, but it's going to program the entire thing no matter what. So we're going to select CM4, and then you can double click this, or you can say OK connect, and it'll do the programming. So keep your eyes down here quick, because it's going to happen quick. And we must have done something. It's redoing the design. So that's good. It's going to take a second. And then right when it starts programming, the device should freeze up and everything should stop doing stuff. Not yet, not yet. Timing analysis. And then of course we could speed this up with some of those settings that we saw, right? So now it's in the software portion of things. And this is a tiny program, and this is a very fast computer that I have here. So you can see this stuff is complicated. All right, here we go. And this is the other, I believe the other one was the M0. Now we're doing the M4. If I scroll back up here, yep, and then there's the M4. All right, here we go. And programming and done, that quick. All right, so the light is not blinking. So what is wrong? So we did something wrong. So let's go back and let's figure out what we did wrong here, okay? So let's take a look here and let's see. So I made a mistake someplace. So let's look at the PWM, and So I was kind of thinking two different things at once I can see right now. So the PWM period is 32,768. The compare is at 16,000. So if we want this thing to kind of have a period of 1 second, we need the clock to be going at 32 kilohertz, right? I put it at 3 kilohertz because for a second there I was just thinking it was a clock that was going to clock the LED and blink it back and forth. So what's happening is we're putting a 3 hertz clock into here, and so it's going to take it 32,000 clicks before it even does 1 cycle. So it's working. It's just working in slow motion. So let's go fix that. So here's the clock, and it's at 3 hertz. So we're just going to go there, and instead of making it hertz, we're going to make it kilohertz. And why don't we make it? Let's make it like 16. We'll make it 16 kilohertz. That should speed it up. All right. So that'll make it like it'll take a half a second or 2 seconds. All right. Actually, let's take a second. Let's not. You know what? Let's make it faster. Yeah, no, let's leave it there. That's cool. Let's try that. Okay, so that's it. So we make that one little change, and now we're just going to reprogram it again. So boom, and then we'll double click this, click OK. No errors. There we go. Programming, and there it is, and it's working. 1 2 1 2 1 2 1 2. There it is, perfectly. So that's it. So it does exactly what we think it should do. And we could put this up to whatever and speed things up if we wanted to. We'll do one more. All right, and then let's do let's just take a couple minutes after this programs. Let's just take a couple minutes. Let's do one last experiment. All right, and hopefully it works and I can get it done fast enough. Okay, and there we go with the program, and it's blinking 4 times faster. Okay, so that's what we expect. Now, so this is all fine and dandy, and I think you can imagine we could add all kinds of other blocks and do all kinds of other cool stuff and build a very complicated piece of hardware. And also understand that there's no software running in either of these processors, just sitting in a loop, and this one just sitting in a loop. We could have put them to sleep, all right? Now, what if we want to do something else and add another piece of hardware and actually have some software running? Let's do that, okay? So let's go ahead and let's put a UART in here, okay? So here's a UART, and we're going to drag it over here. There it is, and it's called UART1, okay? And I'm going to double click on this. And again, you got to read the data sheet to see how it works and all that. So it's got TX and RX, so we're going to just leave it TX and RX. We're not going to need both because we're just going to do writes. We're going to put it 115/200. It's going to be N81, so that's all cool. Advanced, this is so that you can cause DMA things to happen. And actually, the hardware has DMA channels which you can use without software. So you can do the UART can talk to the SPI, can do this, all in pure hardware, all with drag and drop, all with you doing these kinds of things here. So it's very, very, very powerful. All right, pins, we don't need to mess with that. Built in, we don't need to mess with that. So basically, this is done. Okay. Okay. Now we need to. Is there? I'm looking for where the pin. Let's see. Show UART terminals. Let's see. Expose signal. I'm trying to remember. I think we got to figure out. We'll see when we compile. We'll see when we compile what happens here. We'll see when we compile what happens. I think it automatically knows where these pins are connected. So let's see what happens. Okay, so now let's go ahead and we're going to build the program so that everything gets brought in properly. And again, as you use this stuff, you get the hang of it and you remember what's going on and so forth. But it's complicated. This is cutting edge. This is as complex as this stuff gets. So it takes time, and you gotta work with it to remember what's going on. Okay, so now that that's taken care of, so now if we go to the design resources page here, we can see that the UART, it's placed it on pin 5.1 and 5.0, the TX and the RX. Now, if we go ahead and we look at the design here, I can tell you that TX is on 5.1. That's correct. And RX is on 5.0. That's correct. Okay, so that means that it placed it in the right place, so we don't have to worry about that. Now let's go back to here. So here's where we started up the PWM. We've also got to start the UART. So we have to actually say UART 1, and then this does have a start. All right, so we're going to start that up. All right, and now the UART is started. So now I want to actually print with the UART. Okay, so right here in this infinite for loop, what we're going to do is we're going to print something out. So again, we'd have to look through and figure out all the different functions here. You can see there's a lot of them here, but I believe that transmit is what we want. And if we look at the buffer and then the size of the buffer, so we're just going to say /n/r. We're going to say hello world of PSOC exclamation. All right, and then we need the length of the string, so we're going to say, actually, so we don't have to include any other libraries, let's just figure this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I believe it's 22 characters. If not, it's going to be short. Okay, so this is going to print on the terminal, and then we need to slow this thing down a little bit. So there's a function, syslib, and believe it's called delay, and it's in milliseconds, and so we'll put 100 milliseconds there. Okay, so now if all is well, we should be able to program this, dump it in here, and then it should print out on the UART this every 100 milliseconds. Okay, so let's go ahead and give it a try. And then of course we're going to have to set up a PuTTY program. All right, so we'll let it do its build, and now it's programming. All right, and now it's done. So what's interesting is it's going to be doing both things simultaneously. So now let's see if we can actually see the UART working. All right, so let's close this. Let's open up PuTTY. Okay, now where is the UART? So that kitprog3, right, element of it, right, this, right, that's installed itself on a COM port. So if we go to the device manager and we look at the COM ports, we can see, and that's not what I wanted. I just love the new view of everything in Windows 7 and 10 and all that. Always clicking the wrong thing. Okay, so check it out right here. So kitprog3 is on USB UART 174. So we just need to know that 174. So I've already created a COM port on 174 at 1152. So if I load this and I open it, we should be seeing hello world of PSOC, and we do. And there it is. So it actually is working. And it is printing out. And while it's printing out, the LED is still blinking, right? LED is still blinking. So the hardware is working simultaneously, and literally that's that little piece of code right there and the other hardware, which is doing this PWM. And we could change the PWM. We could go in here and write code to actually update the PWM or the clock or the compare or whatever in the code itself, so you could actually talk to the hardware. So anyway, that is programmable logic, and specifically the PSOC technology from Cypress. So this is really cool. This is something you should check out, over a weekend if you just kind of have been interested in programming programmable logic and just, where to even begin. There's so many different CPLDs and so many different FPGAs and so many different tools, like you just don't even know where to begin. But I'll tell you, this is a great place to begin, and you get analog, you get digital, you get the kind of FPGA, and you get processors, multiprocessing, and a tool that does everything all at once. So give it a try and let me know how you like it. And this is great for projects, and we didn't even touch on the Bluetooth stuff. So you can make an entire IoT device ultra low power with a single chip. Super crazy. All right. So anyway, hope you guys enjoyed that, and I will see you in the next lecture. Bye. These things look like. All right, so what I'm going to do is I'm going to scoot this over, and I'm just going to immediately get our little Circuit Scribe book. Now, I'm going to try and come down just a little bit for you, a little bit, so we can get a little bit closer here. All right, how about that? Okay, so let's take a look here. So one of the first little circuits right here is this one. And basically we've got power and we've got our LED there. All right, so I'm going to put this little metal plate under here. Okay, like that. All right, and all that really is helping us do is just make good contact. So when the magnetic printed circuit boards latch down, they make good contact, okay? All right, so then we need the 9 volt. So we'll pop this in right here, and we're gonna put it so that its polarity is in this direction. All right, easy enough, okay? And then we're gonna go ahead and put an LED. All right, and just pop that down. There we go. Okay, and then when I turn this thing on, there it is, and you can see it's red, and then we flip it around, and it's blue. So now what's cool about this, and this is what little kids like, so what's cool about this is you can just draw another part of the circuit here. So what I typically do, or my daughter does, and we're dealing with very low currents and low voltages, so we can kind of do this in real time. So what we can do is we can say, why don't we come over here, and we'll draw some more circuit, all right? And then now what I'm going to do is I'm going to actually draw this. So I'll speed the camera up so you don't have to sit and watch. Okay, so I've drawn it. And then, when you get done, let it dry a little bit and then, just do kind of an extra little pass over it to make sure you got good conductivity there. All right, and then it dries pretty quick, so you don't have to worry too much. All right, so let's go ahead and put our LED back. And we'll put our LED here. All right, it's red. And then, of course, if we turn it around, it would be blue. And then we just put another LED in parallel. And there you go, it works. All right, so how cool is that? So that's basically how this thing works, And then kind of show you a couple other examples here. For example, let's see here something fun. Something with, do this one. So this one here has a little dimmer. All right, so just the dimmer, which is just a potentiometer. So here's our dimmer here. So we just pop that in there. We put our power source on here, like so. And then we put an LED here, like this. And then as we turn this up and down, it gets brighter and darker. And then we can turn it around like this, brighter and darker. And then, now, we don't have to put an LED there. We could put something else there if we wanted to, right? We could put a buzzer, for example. We could put 2 LEDs. We could put a buzzer. So we'll put 2 LEDs. And you can see what's cool about this, if you're a little kid, you just kind of play with it and you start to get, an understanding of what's going on here, right? And put a buzzer here. We got to make sure the polarity's right. So that's got a very annoying tone. All right, so that is how you do it. So basically that's it. So you just basically just draw whatever you want. And then like I said, you can draw this on anything you want. This is just standard paper. It's not magical paper, right? Just normal paper. And then, for example, what I like to do is just get something, that's fairly dark, something with a little bit of color in it, right? Black would probably be ideal, but I ran out of black. And then here you just kind of draw, whatever you want. So again, if we want to do something really simple, what we can do is we'll just come down here and then we'll just kind of mark where these little pads are. So just kind of go down here, mark. Let's do it with our other pen. We mark, all right. And then we'll kind of draw circles around here like this. And we just want these big enough so that it picks up these little magnetic spheres on here, right? All right, and then again, we can do something just real simple. We'll just put this one right here, and then come down here and mark, kind of do that. And then we'll just kind of draw a little horizontal line. And then here we'll go like this for fun. All right, again, I will just do this and then I'll speed the camera up. Okay, there we go, done. All right, so let's go ahead and put our power source on here. And we'll put it on here. Nice. And then we'll go ahead and put an LED here. Like that. Turn it on. And there you go. And go like this. And then now, so to prove that this thing, let's cut it. See if we can have something to cut it with. Here we go. So for example, if you had a circuit that had a break in it, right? So we're just going to cut this. So I'll take this and just cut it right here. And now you see it's dead, it's broken. And then, we'll fix that and just connect it back. There we go. Now it's connected and working again. All right, and so, and like I said, the other thing that you can obviously do is, let's say, for example, you know, we've got a circuit board here, right? And let me zoom in a little bit. So let's say we have a circuit board here, and then after I got done with the design, I realized, oh no, I need this connected to this, something like that. I could draw on this printed circuit board, just draw a circuit trace, and then I would have my conductive trace instead of doing a blue line or a wire, a jumper wire. So I can just kind of draw on here, which is much, much nicer, and then get that connection. So anyway, that is the Circuit Scribe. All right, and it's very cool. And so the pens just kind of come like this in a little package, and depending on if they're on sale or not, they're like, you know, $5 to $10 each, roughly, when you get them from Circuit Scribe or Amazon, this and that, and they come in bulk packs. And then when we get back on the computer, I'm going to give you I called up the company, and they were very nice, and told them that I was going to do a class or a bonus lecture on the Circuit Scribe stuff. So they gave us a discount code. So if anybody wants to do something with Circuit Scribe, you can use the discount code. So, and that's Crash 10, but I'll show it to you once we get back to the computer. But anyway, a lot of fun. The magnets are a lot of fun. Kids love the magnets, obviously. Keep them away from each other. So anyway, that's about it. So let's go back to the computer and take a look at a couple other things. Okay, so we're back here on the computer. So like I said, anyway, if you want to try this out, it's definitely something cool. So if you have children or relatives, whatever, that are children that you want to show electronics, then this is a great little kit to do it. Anyway, we got a discount code. It's CRASH10, CRASH10. I'll put it up on the screen so you can see it, and then you can just type that in at the end when you go ahead and get your product off their website if you do. Otherwise, you can just use a URL. So if you just say circuitscribe.com and then / reference equals crash 10, that's another way you can do it. But all you need to do is type in crash 10. And the other thing is their discount stack. So I guess there's always like a 5% or something. It says it someplace. So it'll always add them together, which is kind of nice. So anyway, that's it. So conductive inks, very cool stuff. And like I said, I've tried many of these inks from Amazon.com. And over the years, from Circuit Writer, MG Chemicals, this and that, and honestly, these Circuit Scribe pens work the best, hands down. So it's a really cool product, and it's pretty cheap also. So I think here, so these are like 10 packs. Let's just see how much are they if it's a 10 pack. Yeah, so it's $50. So it's like $5 each. You cannot beat that when you compare the prices of these other pens. Like this is $22 just for this one pen, and these things dry up so fast. It's like, I buy 2 or 3 of these Circuit Writers and none of them work at all, and I throw them away. It just really irritates me. So the Circuit Scribe does work. So I think that's about it for this lecture. So it's a good tool to have inside of your toolbox, having conductive ink. You can use it to fix circuit boards. You can use it to kind of draw circuits. You can experiment with flexible circuits. Say you kind of wanted to play around with a flexible circuit. So say you had a substrate that was flexible and you wanted to say, hey, I want to kind of make something work with this. You could actually draw your circuit there before you take it to a manufacturer and do some drawing and actually manufacture a flexible circuit. You can draw the circuit. You can't draw much of a circuit, right? The other thing is you can buy conductive inkjet ink from Electron Inks, right? So the parent company here, you can go right here, and in their products they have, inkjet inks. So you can do that. They also have inks for screen printing. So if you're a larger company or represent a company that wants to experiment with more advanced inks, then definitely contact Electron Inks. So cool company and cool tech. All right, so that's it. So I will see you guys in the next bonus lecture. Bye. Hey everybody, how's it going? I am going to do another power supply bonus lecture this time. So we have a big power supply design bonus lecture back in, let's see here, it is number, I think 136, yeah. So bonus lecture 136 in section 9. For an hour and a half, we go over the design of a power supply, the Raptor PSX, which has a 3.3 volt, a 5 volt. It has a lithium ion. No, this one doesn't have a lithium ion. It has 3 volt, 3.3, 5 volt, a buck boost converter, an LDO, some cool features, and this lecture goes over the entire design of it. Now, why I'm going to do another lecture is I'm getting a lot of questions about power supplies. I get them from a lot of different students asking, what power supply should I get? And then sometimes I get questions, and I just had a student ask, why would I make my own power supply? So I seem to get a lot of questions about power supplies, even though in the lectures of the course, we talk about power supplies a lot. We design them, and then even in bonus lecture, we go over another design. So what I'm going to do, this is going to be kind of a little power supply primer. This is going to be a short bonus video. We're not going to go too long. But what I want to do is I just want to talk about, you're going to, build some electronics. You're going to do some projects. You need a power supply. What should you do? What should you get? Then maybe you want to build your own power supply. What should you do? What should you get? And then, just kind of talk about those 2-3 different problems. All right. Okay. So let's begin with, and like I said, make sure to watch lecture 136 in section 9 if you're interested in power supply stuff at all. So let's go and do some drawing here. So let's say that you want to work on these projects and you need a 5 volt power supply for a lot of them. So to power our projects, you have a couple options. You could get a desktop power supply, right? So you can go out and buy a nice desktop power supply. And, this would be something, these are fairly pricey, right? And these are going to go ahead and these are going to typically plug into the wall, right? So this is going to plug into the wall AC. And then we're going to have an output here, which is usually an adjustable output, right? And this output might go from 0 to 30 volts, and you might be able to get from 0 to 5 amps, depending on how much money you spend. So this is one option. Now, these power supplies come in 2 different flavors. They come in linear, and then they come in switching. All right. Now, the switching power supplies might be a little bit cheaper, and a lot of times they're more flexible. They can do lots of other features. But the linear is going to give you cleaner power because there's no switching, right? So switching means there's a switch mode power supply in the power supply, switching thousands, tens of thousands, hundreds of thousands, megahertz times a second, and that's how it generates voltages. Whereas a linear power supply is going to basically bleed off voltage with heat. And that's how it kind of works. So in a lab where you're doing very precise work, a lot of times you will use a linear power supply rather than a switching power supply. All right, so now, and then another thing, of course, is the power supply can have more than one output, right? So you might have a supply with, there's one output, and then, it might have another output, and then it might have another output, and maybe 2 of these outputs are adjustable, right? And maybe the third one is not adjustable. It may be fixed, and that third output, maybe it's fixed at 5 volts, since it's a common voltage that people use a lot in electronics. All right, so that's your option one. So you just get a desktop power supply. All right. Now, what's another option? Another option is if you can't afford that, then what you could do is you could just find a wall adapter, right? So you're going to get a wall adapter, and these wall adapters plug into the wall. So again, this is plugging into AC here, right? And the wall adapter might put out 5 volts, it might put out 9 volts, it might put out 12 volts. And then now we got to be careful here. The wall adapter is going to either put out, it could put out AC, but it'll typically put out DC, DC unregulated, okay, or it'll put out DC regulated. Now, we are more interested in the DC regulated, so we want a regulated power supply. And so again, if you're new to the class, regulated means that say if I have 5 volts from the power supply and I pull 100 milliamps of current, all right, then let's say that I pull 1 amp of current, 1 amp of current, and let's say that I pulled 10 amps of current. Whenever I pull all these 3 different currents, this voltage stays the same. It's regulated. So there's electronics inside of this wall adapter. It's kind of a mini power supply, a mini desktop supply that regulates that power supply and maintains that voltage, whatever the voltage is, all right? Now, the unregulated supply, basically an unregulated supply, is usually nothing more than a transformer. So it'll have a transformer. This will be the primary side. The secondary, the primary is going to have your 110 AC coming in or wherever you live, your voltage. And then on the output, that's going to be where your 9, your 5, your 12 volts will be. And then additionally, what will happen here is there'll be a bridge rectifier to turn this to DC, roughly DC. So it'll basically take the waveform and do this to it. So you're going to have this kind of waveform like this, and then what you're going to end up with after we do this rectification is we're going to end up with a waveform like this. All right, so that's definitely not DC, right? But it's at least positive going. If this is 0 volts, we're always positive. Then what we do is right after that, and we're just running out of room here, but we'll put a capacitor, a filter capacitor across the output, and then that will then smooth this. All right, so we'll get kind of a DC out, but there's no regulation. So as we pull current, this capacitor is you're gonna pull charge from it, and you're gonna modulate the voltage all over the place. So as you pull current, this voltage is gonna change all over the place. All right. So what good is an unregulated supply? Well, an unregulated supply is great because it's cheap. It's just a transformer, a bridge rectifier, and a capacitor. Then you can take that into your project, into your hardware, whatever it is you're building, and then you add the regulation to it, right? So you just want to get the 110. You want to go from AC to DC. You don't want to mess with that inside of your hardware, in your PCB design or your product design. So you say, hey, we'll just have a wall adapter. It'll be unregulated. It'll be 50 cents, $1 a piece. Then in the design in our product, we'll go ahead and regulate that and clean it up and make it into a nice clean 5 or 3.3 or 1.8 or whatever voltage it is you need. But if you're building the project, typically you're going to want a regulated supply. And when it's regulated, the supply will say whatever the voltage is, it's 5 volt regulated, and it'll say what the maximum current is, like say 500 milliamps, or it might say 1 amp, right? That's how much current it can supply before this voltage starts dipping. Now, take everything with a grain of salt. The specifications are written by marketing people, and marketing people either don't know, or they exaggerate, or they round up, or whatever. So you have to be very careful, and you have to test these things if this is anything mission critical. So for example, if you were to go and buy, say, 3 different regulated, number 1, number 2, and number 3, 3 different regulated DC wall adapters at 5 volts each, right? And you put those on a voltmeter, right? You might find that one of them is 5 volts. You might find another one is 5.2 volts. You might find another one is 4.85 volts. Then what you might find is as you put a load, maybe you put 100 milliamps, right? You put 500 milliamps. you put 1 amp, and as you do this, this voltage on these things really drops or changes. All right, so you have to test these things to kind of know what you're dealing with. All right, so here's kind of the two different classes of power supplies we can use, right? And then the other thing, of course, is what the Raptor is this kind of more of a kit. So in this case, I designed one of these solderless breadboard designs, and we've seen this before, but you know, this is going to go into something like this. It'll go in the end, right? And then you can use this to power your electronic projects. So this is kind of an open frame power supply. You plug it in right here, or you plug in a USB cable, and then you get power, all right? So this is kind of an open frame, less of a finished product. That's a box. But notice that it has an input here for power. So what can we put inside of there? Well, you can put 6 to 12 volts DC. And this 6 to 12 volts DC that is going into this regulator, I'm assuming, right, that it's DC. So it could be regulated DC or it could be unregulated DC. I don't care because I'm going to regulate it, right? So if you put in a regulated, say 6 volt supply, right, that's kind of overkill because I don't need it because I'm going to regulate it. That's what all these chips and components are for. But it won't hurt to put an unregulated supply as long as it's DC. It's got to be DC, of course, 6 to 12 volts. All right. Okay. So anyway, so those are the two different kinds of supplies. So if you're going to buy a bench power supply, I suggest you get one that has, you know, 2 channels, ideally 3 channels is even better. And inside of the parts list, so in lecture 1, there's a bunch of PDFs, a parts list, an outline of the course. The parts list has a selection of power supplies to get you started, kind of low cost, medium cost, high cost, just some ideas. You can look for them on Amazon, eBay, and other websites to find your kind of a desktop power supply. Whenever you buy any equipment, my advice is always the same, and I say this in the class: buy good tools, right? So if you can afford it, always buy a little bit more than you can afford so that you're getting something good so that it lasts. You know, better to buy a $50 power supply than buy 3 $25 power supplies because they keep burning out, right? All right. So power supplies you're gonna look at. You know, you can find a deal, but you know, typically you're gonna be looking at, you know, $50 to $200. Kind of will get you a decent desktop power supply with 1 or 2 channels. And then if you want to get crazy, then of course you can get up into the you know, 500 to 5K range. If you want like lab precision DC power supplies that, you know, have 5.00000 volts no matter what, you know, that kind of thing. But we don't need that kind of accuracy. All right, and then of course wall adapters cost a couple bucks a piece. We've all got like a box full of them. I've got boxes full of regulated and unregulated. Whenever I have a project that I need something to power it, I'll just go to my box and do that. So now, so say for example you have your regulated wall adapter, all right, and you only can find 5 volt, 9 volt, 12 volt. But what if you need like 3.3 volts in your project, right? Now you could find a regulated wall adapter that puts out 3.3 volts. If you look hard enough, you'll be able to find one on Amazon or different vendors. And a lot of these wall adapters, you can find a wall adapter, and if we go Google for it, I'm sure we could find it. But some of them will have like a little face here, and on the face they'll have a little switch, and that switch will have like 3.3, 5, 6, 9, 12, and you can kind of switch it. It'll actually switch it for you, and you get different voltages. So you can do things kind of that cheap route. Then of course you got to get it into your work area. So you got to somehow connect it to this. So you got to create some cabling and connectors and get it, you know, onto your system. Now, let's say that we don't want to do that. Let's say that we want to have a unregulated wall adapter, all right, and we want to bring in, say, maybe 6 to 9 volts, and then maybe in our project we're going to need a bunch of different voltages, right? We're going to need like 3.3 volts. We're going to need 3.3. We're going to need, you know, 5 volts. And maybe also this is a low voltage system, so maybe it'll need 1.8 volts. So maybe we need all 3 of these voltages. Now again, This is in the course. There's many lectures on power supply design and the bonus lecture on the Raptor, so I'm not going to go into this too much. But in this case right here, you're going to build a regulated power supply, either a linear regulated power supply or a switching power supply. And you're going to bring in your 6 to 9 volts, right, into your PCB. And then you're going to have some regulation. There's a mosquito flying here driving me crazy. Then you're going to have your regulation. So you'll have 3 different circuits, right? You'll have one for the 1.8 volt, right? You'll have one for the 3.3 volt, and then you'll have one for the 5 volt. We'll come in like this and do something like this, all right? And then we'll create each one of those power supplies. So you'll create those power supplies with a linear regulator IC or an LDO, low dropout regulator, or you'll create it with a switching regulator and an inductor, or you could do it with a capacitive switcher, a capacitive switching regulator for lower currents. And another thing that you can do, though, is one student was just asking about this, and he was thinking, wow, it's complicated. I have to build my own power supplies. So that's true, right? If you're going to be designing boards, a lot of times you're going to design your own power supplies because you're going to need many different voltages and the control of them and so forth. And you want to make sure that the regulation is perfect and you don't want to trust the vendor. So from the vendor that you get your little wall adapter, you just care about, just give me 6 to 9 volts, DC, unregulated, and I'll take it from there. You take care of the AC to DC part. I don't want to mess with the wall, right? You go out and go get UL certified, right? Underwriter Laboratory certified, so something can plug into a wall. Then once it's low voltage, I can deal with it. But if I make a power supply that you plug in from AC, an offline power supply, then I have to deal with Underwriter Laboratories, right? So I'll let you do it. I'll buy your wall adapter, and now I've got a low voltage system. That's another very important point when you're designing power supplies and hardware. All right. So anyway, the other thing we can do is, so instead of, now what you can do is you can go, so let's do some looking here. So you can go and to DigiKey, for example, right? And you can go in here and you can say, 5 volt, let's say 3.3 volts linear regulator. All right. And then we have all these different options here. So the one with 12,000, roughly 11.5 thousand. All right, and then so we want to say an adjustable one. We want it to be active. We want it to be a positive output. I want it in cut tape only, and I want it to be in stock. All right, and apply filters. Let it filter away. All right, and output voltage. We'll just do this. So you can see here you'll get a list of all these different ICs, right? And depending on how you search, you'll get hundreds or you get thousands of results, right? You can see this one right here, this Rohm adjustable regulator, right? And it puts out 300 milliamperes. This other one puts out 3 amps, right? And you can see it's more expensive. The higher current, right, puts out, it's more expensive. So you basically go through and do this search, putting in whatever parameters and whatever order you want to put them in. And then at some point you're going to go and look at the regulator, this expensive one here, and then you're going to pop open the data sheet here, right? And we'll see if it pops open. Oh, Chrome worked for once. All right, then you've got to sit here and you got to look through the data sheet at the reference design, how it works, read about it and so forth, read about its specifications, its line regulation, its load regulation, how fast it can adjust to changes, all that kind of stuff. You got to read through this thing. And, this is 23 pages just for this little regulator, right? There's a lot to read here. And then inside, it'll show you reference designs, kind of a typical, here's a 3.3 volt reference design with all these various components. And these ICs can get very complicated or be very simple. Now, you're not ready for that and you don't want to do that. So instead of selecting your own chip, now, of course, you could always get something simple, right? You could always get something simple like a, LM 7805 or a more modern voltage regulator. So if we go here, so 7805 is a very famous regulator. And now you can see, so for example, the dropout at 1 amp, and what the dropout means is that is the difference. So if you want to maintain 5 volts, you need at least 7 volts coming in. So if you want to draw 1 amp, you need to have 7 volts, because this regulator is going to drop a whole 2 volts, right? That's brutal to maintain that 1 amp. You can get modern linear regulators that have dropout that are 0.2 volts at an amp. All right, so that's what you really want. You don't want to use something old from the 70s like a 7805, but it's good for an example. All right. So let's go ahead here, and here's our famous 7805, and we pop open the data sheet, and let's see if it works. Let's see if we can go 2 for 2 with Google Chrome. Wow. All right, so anyway, then it shows the different packages here, different versions, and then here's the circuit. So you got an input capacitor, and then you got an output capacitor. These are all lies, right? So although no output capacitor is needed for stability, it does help transient response. So you need way more than this simple design. And the problem with internet is you've got so many people that don't understand power supply design, electronics, copying and pasting. The same thing happens in web programming or any kind of programming. And you've got non-experts posting stuff, and then you've just got just zillions and zillions of sites with wrong designs. So, where did this come from? Well, this probably came, from 20 years ago, 30 years ago, and they're trying to show what's the bare minimum to make this thing work, to make a power supply. This is no good. So when we go over power supply design, we talk about, I want to see at least 2 capacitors on the input for 2 different frequency bands. I want 2 capacitors on the output. I want to see a ferrite bead. I want to see a pi network. I want to see another pi network. I want to see some protection. I want to see this. I want to see that. And we add to it a few more components to make it more robust, so we get a cleaner power supply. But nevertheless, this regulator is very simple, and when push comes to shove, it would work with just a couple capacitors, or even 1 capacitor if you really had to. And then they have the various versions of it. So you could design something with really, really simple linear regulators. Now, switch mode regulators are more complicated, although today you can get a switching IC with you literally just add an inductor to it, and you don't need to add a transistor to it. You don't need to add a diode to it. You just need an output capacitor. A lot of them have things built in except the inductor. And then there's what are called capacitive switchers that don't use inductors. They use capacitors for the energy storage. So you could design your own power supply that way. But there's another option also, which is kind of cool. Let me show you that. So the other option is 5 volt, let's see, module. I should have searched this before, but let's see if I get lucky here. I think Traco is the name of a company. Kui, yeah. So here we go, DC converters. Yeah, let's see if this pops up with what we want. So it's a DC converter, and oops, let's come in here. Yeah, so these are some of these. Here we go. Yeah, so a lot of these, basically, these are entire power supplies in a package, all right? So like this Murata Power one, right? Let's go take a look at this. So what is this? So this is an entire power supply. You give this thing DC, so this is where your unregulated DC comes from, and they actually did the design for you, and they know what they're doing, right? So the manufacturers who design the actual chips, when they'll build a power supply module for you, you'll get a good module. It'll do what it's supposed to do and have those extra components. So this one right here, what does this do? This one is 6 volts, I believe. Let's see here. And it puts out 1.5 amps, 8 watts, so that's pretty cool. It's a SIP package, so single inline package, right? Obviously, you can see it. And it's very, very small. You can see this is a probably 0.1 inch pitch here, right? So this is very small. And of course, you could get other ones that plug down, or they solder on. They have castellated pins, so you can solder them onto your board. So say, for example, you want to build a project, and you don't want to mess with power supplies, but you need like 3 different voltages or 2 different voltages, so you don't want to have 2 different external power supplies. You just have one power supply, maybe with 9 volt unregulated. Bring the 9 volts in, get one of these for 5 volts, get one of these for 3.3 volts, and you're done. That's it. But it will be more expensive. So you see this cost right here, this $397, right? Now, if we were to design this ourselves, maybe we could get the IC for 50 cents. Maybe we could get the capacitors for another 50 cents, right? and the inductor for 50 cents, and the resistors for 5 cents. So you can see that's cheaper, right? And then as the volume goes up, ours is going to get cheaper and cheaper and cheaper, right? But of course, we offset that by the time to design and test it, right? So, so that's two different ways to build your power supplies. You can either design them yourself on your board, or you can use a module, right? And then skip that whole design process and then use the module, all right? Okay, let's see. Was there anything else? Let me see. Also, let me see. Traco, 5 volts. Let's see what happens if I type that in. Just want to show you these other modules because, so that one right there, let's look at this DC. Yeah, here we go. Yeah, here we go. So now take a look at these. These are nice, and they're a little pricey, let's see. Let's find one here. And let's see, minimum is 4.5, maximum is 5.5. So now this is not very robust, right? If you look at this, we've got to keep that voltage in that range, right? So if we had an external unregulated DC supply, we don't have much latitude. It has to be 5 volts. So we don't like that. So, let's take a look over here. Now look at this one. This one here is 5 volts out, and you can put in 6.5 to 36. Now I like that much better. So what we'll do is we'll just say spec a 9 to 12 volt DC unregulated wall wart. Now we have our 5 volts. It puts out 1 amp. That's nice, and it's $5.43 each. So I like that one right there. So let's go there. All right. So we got our $5 supply, and then at 100 it's 4.3. So maybe at 1,000, maybe it'd be $4 a piece. Maybe at 10,000 we'd get down to $3. Maybe at 100,000 we'd get down to $2. All right, so you can kind of get an idea. But at 100,000, our design would probably cost 50 cents, right? But why we like this one is it's sealed. So you can see it's sealed in resin, so nothing's going to interfere with it. We're just going to put 3 holes inside of the board, and it's got everything it needs. It's got its power dissipation all computed, figured out. So as long as you put this inside your design, it can't be touched, it can't be messed with, it's not going to break, it's not going to explode, whatever, because it's protected. So a lot of times this is a much nicer way to do things than having that open PCB that you can see with the other example. Let's look at the dimensions of this. They're very small. So yeah, so 11 by 7 by 10 millimeters. So that's tiny, right? That is really really tiny, right? That's just boom. That's pretty sweet. So anyway, me personally, I have to be honest with you. I rarely use these because every time I get a client that wants an embedded system, all they care about is how much it costs. They're like, we want the control board for an SR71, but we want it to be super cheap. So I can't use anything expensive. So I've really learned to be very frugal and do things very creatively to reduce cost, because pennies and dimes count at hundreds of thousands and millions of units, right? Anyway, so I hope that helped a little bit and gave you some ideas for power supplies. So you can buy a power supply, desktop power supply. You can get a wall adapter, do things that way, regulated or unregulated. If you want to build power supplies on your board, then you can use a linear regulator or a switching regulator IC and put all the components yourself, figure it out, get it working. Linear regulators are fairly easy to get working. Switching regulators, not so much. The PCB design and layout does matter. All right, and then if you don't want to mess with it, but you still want the efficiency of a switching regulator, then you can go out and get a module. They're expensive though, as you saw. They're $4, $5, $6, $7 each. But that way, say if you need 3 voltages, you just put in a 3.3, put in a 5, put in a 1.8 module, and you're done. Just feed them all from your wall adapter. Okay, so that's it, and I will see you guys in the next bonus lecture. Bye. Welcome to Crash Course Electronics, Halloween edition. Hello, everybody. It is Halloween, or the week of Halloween, and I thought this week we would do something about making Halloween decorations and using a type of sensor called a passive infrared sensor. All right, so I'm sure you've seen these sensors before, And let's go over here and take a look at them. And for example, here on Amazon.com, we've got some of these passive infrared sensors. So these are breakout versions of them, of course, so you can put them into your projects. But here's what they are, right? So you've seen these. And the whole idea of these sensors is that they don't emit any energy. They only receive energy. That's why they're called passive. So they're called passive infrared sensors. All right. And inside of them, there's some electronics, and most of them they're very similar. You apply power to them, 5 volts in ground or 3.3 volts in ground, and they usually have a single output, and that output triggers when an object moves across the sensor's field of view and has a temperature differential. All right. So if you just go on Amazon and type in PIR sensor, you can see a number of them, different manufacturers, and some of them have some of them may have some potentiometers on them. For example, if we go to this one right here and we look at it, you can see what's inside of there. There's a sensor and there's a board. You see there's 2 potentiometers right there, here and here, and those allow different adjustments. So then it shows different outputs using it in different ways. So each one of these things kind of works in a slightly different way. All right. So the whole idea is we can get these passive infrared sensors, and then we can use them to trigger something. All right. So for example, what I was thinking to do was we'll use a passive infrared sensor, and then we'll use its signal so that when a heated object, a body, a human or an animal, moves across it, then a signal will be triggered, and then we can use that to trigger something else. You could plug it into an Arduino, you could connect it to some lights, you could connect it to a sound source, whatever you want to do. All right, so let's go take a quick look here. So I kind of Googled around and found a page that had some good information. So if you go to Adafruit and type in how PIRs work, you'll be able to find this document here. So, and there's thousands of white papers on them if you want to know more. But in a nutshell, like I said, there's a PIR sensor. So this is just a sensor that's sensitive to infrared light. And then the interesting thing about it is they actually have 2 sensors inside of the head of this. All right, 2 matched sensors. And then what the sensor does is as an object moves across the field of view or the detecting area here, then you'll get these kind of 2 pulses, which will show there's a temperature difference happening on one sensor and then a temperature difference happening on the other sensor. When the sensor detects this, then it has a microcontroller or some electronics inside of it, and it'll send out a single pulse signal, a square wave. And again, depending on which sensor you get, that square wave may be a second or milliseconds or 5 seconds, or it may be adjustable. No matter what, you're going to get a signal, and from that you can process and do what you want. All right, so here's what the sensor looks like on the inside. All right, so they most of them all look like this, and I have one over here. I'll show you when we get to the bench. But there's a lens on it, and this lens, this doesn't do much. This doesn't do any kind of focusing or anything like that usually. It's just to protect it. It's usually just made of plastic that transmits infrared. All right, so it's just used kind of to protect it. Sometimes there's some lensing going on if it's an expensive one. All right, anyway, and then inside of it, you can see here, this is just a representation. There's these 2 sensors, this resistor, and then there's a FET. So this is not necessarily what all of these have in it, so don't worry too much about that. All right, and let's see here. And then it's just showing you there's some talk about Fresnel lenses, which are basically using facets to kind of create a larger lens. That's not really important. All right, anyway, and let's see here. Yeah, so it's kind of showing the Fresnel lens. So some of these have these Fresnel lenses inside of it, which focus the signal. And then kind of showing you some of these sensitivity diagrams here and so forth. All right. So anyway, there's a lot to be had with these sensors, and you got to read about them and take your time. But they're very, very interesting. And anyway, what we're going to do is we're going to take one. So I've just got one simple sensor that I got from Amazon. I've got tons of them all over the place. And the particular sensor I have, which I can't remember the manufacturer of. It's not important. It basically has an input for power for 5 volts, a ground, and then an output. It has no adjustments, all right? So if you go looking around here, you could probably find the exact one that I have. But a lot of these ones on here, Amazon, that I just searched for, have some adjustments which make them more flexible. And they have some micro sensors which are really cool. These are all about, they're about 3/4 of an inch to an inch width by height, each one of these sensors. But they have some micro sensors as well, which are really cool because literally they fit. Let me see here, where's the camera? So if you look at the tip of this pen here, right, they fit into the tip of this pen. So you can kind of hide them, which is really nice if you want to detect motion. Okay, so what I'm thinking about is, I'm sure you, so like I said, obviously it's Halloween. I'm doing kind of a Halloween themed video here. So I'm sure you've seen at the stores, depending where you live, hardware stores or toy stores that have Halloween decorations. So when you walk by it, the eyes blink, or maybe it makes sound, something like that. So there's a passive infrared sensor inside of there, and then it triggers either some lights or it triggers some sound, some things like that. Now, to do sound, we're not going to do that because we just aren't going to do it. But whatever I do here can be applied to a sound system. And then when I finish up, I'll kind of talk about that. But you can get an MP3 player as well. So you can get kind of these DR Robot. This one's really good. DR Robot MP3 player. I think that's what it's called. DR Robot or DF Robot. DF Robot. Yeah, I think that's the name of the manufacturer. And yeah, there it is right there. So DF player, yeah, that's it. So the DF player, these are really, really cool. So this is not just an SD card holder. It's actually got a processor on it, and it actually decodes MP3s. I think it also does waves as well. But anyway, if you look here, and then you can see the back of it. So it's got this chip on it and so forth. And then on internet, you can go and find the documentation for this thing. And basically it allows you to play MP3s. So you put MP3s on here, and then it actually has a built-in amplifier, so you can connect it directly to a speaker. So all you need is an SD card, power, and a couple inputs, and you can play songs off of it. It'll go in sequence down the directory, or you can jump around and do all kinds of cool things. And you can talk to it serially also from an Arduino, for example, or whatever, and you can tell it to do different things. So that's how you can get sound. So you can use this DF player if you want to turn this into a sound project. But we're going to do something a little bit simpler. I didn't want to get all crazy with an Arduino. All right, so let's go back here. Okay, so we know that we've got power, ground, and we're going to have some kind of digital output. All right, so let's go ahead and let's start drawing up kind of what I'm thinking here. All right, so first let's get rid of this thing here. Okay, and let's see what we want to do here. All right, so what I'm thinking is we've got our sensor here, and let's go ahead and let's draw something for the sensor, and kind of do this and kind of draw its little sensing element inside of here, kind of like that. All right, and then we've got our outputs here. All right, and so we've got 1, 2, 3 outputs, and each one of these outputs here has a purpose. So we've got 5 volts, and I'm going to call this one ground, and then I'm going to call this one the signal. I'm going to call this S, or this is the output. Okay. Okay. So now we've got 5 volts ground. So what we're going to do is we're going to, literally take this and we're going to connect this to our 5 volt source. All right. So we'll call this like a V sub CC. All right. This will be our 5 volt source. And then obviously we're going to take this and we're going to connect this to ground. And we're going to supply that from something. Then we've got this signal. All right. And then what's going to happen here is we're going to get a square wave out of this. All right. So when this thing is triggered, we're going to get this square wave, and the square wave is going to occur for some time. We'll call this T0. And this can be adjusted, like I said, and typically this will go from rail to rail. So it'll go plus 5 volts to 0 volts, all right? Now, the T0 may be fixed or it may be adjustable, but typically these are on the order of, 0.5 to 5 seconds, okay? Now, if you want to do something else, then what you're going to have to do is you're going to have to process this through something. So say, for example, it puts out a 1 second pulse and you want a 10-second pulse or something else. Then what you could do is you could use this signal to trigger a 555 timer or another timing element, and then you could get the signal that you want. So basically, in that case, say we have this signal right here, and then we could pretend that we've got another block here like this, and we have this 555. Maybe we've got it in one shot mode. Then we would take this output right here. Okay, so we'll call this S output. All right, and we take S and we put it in here, and maybe S is 1 second, and then here on this output here, this output, we get a 5-second burst whenever it gets that trigger. Okay, so and that's what we could use something like that for. All right, so now let's go ahead and think about what we can do with this. So we've got our pulse here now. So we take this passive infrared, we hook it up to power, we get this pulse. We could directly hook this to an LED, right? There's no harm in doing that, right? So we could take this output and we could go directly to an LED, right? So we go like this, and maybe we put a resistor here and we go to ground, okay? And we've got our LED here, right? LED 1 and R1. Okay, now the problem though is we don't know what the current drive is of this passive infrared. So in the data sheet, maybe it says it's, maybe it's only 1 milliamp. Maybe it says it's 10 milliamps, right? And so forth, right? But we don't know what it is. Now, remember, whenever you're building something, you don't really want to put a whole lot of load on your sensors. You want to amplify or buffer your sensor output. So we really don't want to assume that we can drag a lot of current, especially if we're going to be putting things through LEDs, because LEDs burn a lot of current. Remember, we've talked about this, 10 to 20 milliamps, and even more if it's a big LED, right? So now if I wanted to have a bunch of LEDs, obviously I can't drag that much current out of here. So we've got a number of options, all right? So what we could do is we could put a transistor, right? We could do that. We could take a transistor. So for example, what I could do is I could take this output here, and I could go and I could stuff it into the base of a transistor, right? So we can get a little transistor right here and do something like this, all right? And we'll make a little NPN transistor here. And then what we could do is we could put our LED in either position, but we can put our resistor here, and we could put our LED here like this, and we put this up at V sub CC like that. So there's our little LED again, and here's R1 here. Here's the base, here's the collector, here's the emitter, and maybe we use a 2222, right? NPN transistor. And then so now what this would allow us to do, and then maybe we want to make sure that we pull this down, right? Because this is an active high. So maybe we go here and we put a 10K, something like that, to ground to keep this transistor off until it gets turned on. Now, so we could do that. Now we could put kind of anything we want here. We could put, loads from, 100 to 500 milliamperes, right? So we could do that. So you could put a bunch of LEDs inside of there, right? Or even a motor, so you could have this thing turn a motor, something like that, right? So this is kind of the better way to do things. So you take the output, you put it into a transistor or a FET, right? And then you use the sensor to just turn on the switch, and then you have the switching circuit, which might have your LED element or whatever else here. Maybe you want a motor, something like that, or motors. Okay, so that's that way to do it. Now, what we're going to do is we're just going to keep this all digital today. And so what I would like to do is just use chips, and to keep this really simple so we don't have to get all analogish with this. And I think I used up all my deletes there. Let me erase this. So what I'm going to do is, and we've done this in class. Now, if you're just skipping and just watching this, then you may not have seen this tactic. But what we're going to do is we are going to use a chip itself as an amplifier and buffer. So for example, if I were to take this output, right, and I were just to put it through a non-inverting buffer, right? Put it through a non-inverting digital buffer, right? A TTL kind of logic or a CMOS kind of logic. Whatever the current drive of this is now the current drive that I'm going to get. So if this is spec'd for 20 milliamperes, right, then I'll get 20 milliamperes of current I'll be able to now support. So that'll get me 1 or 2 LEDs. But no one said I can't put these in parallel, right? So first thing is, instead of using just the non-inverting buffer, let's just use something that's really common. So we're going to use a 74LS04, right? And that is a normal hex inverter package, right? And we'll take a look at that in a second. So there's an inverter right there. Now, you can always take these and put these things in parallel, right? And I've shown you this before. Take these and put them in parallel like this, all right? And we'll go like that. So now each one of these can put out 20 milliamperes. So now we've got 40 milliamperes of drive. You want more drive? Okay, fine. We'll go like that. Okay. And now we've got 60 milliamperes of drive. Okay. All right. And so now you say, well, wait a minute, I don't really want this inverted. I'm not sure, whatever. Well, then what we can do is we can just put one inverter in front here or not. We can jumper over it. So what we can do is we can have this and we can put an inverter here like this, and that inverter can go here. So then what we can do is we can break this open if we wish, right? So we can go there and you can just break that open. You can put an inverter there so you can invert or not invert this signal, okay? And then once you do that, then you get the amplification stage. Now you can't put the inverter over here because then you only have one inverter, so now you're back to 20 milliamps. You need to make sure you put them in parallel. All right, so that's kind of the plan. So what we'll do is we'll put two or three inverters. We'll put 2 for now. 2 inverters in parallel, then we'll have a spot for a inverter in front if we want to invert this, okay? So now that we know this is inverted, let's, for just for a second here, let's pretend there's no, so get rid of this and let's just pretend there's no inverter. Let's pretend this is open here, right? So let's just pretend this is not even here. So when we get a 1, which means there's something there, we're going to now get a 0 out of here, right? So we're going to get a low. So what that means is if we want to connect our LED, we have to connect it in the right direction. So we're going to get a low out of here. We're going to get a 0 volts when this thing is active, right? So let's go here and let's go back to green. Okay, so we're going to go here, so we're going to get a low. So we've got to make sure we put our LED in the right direction. So we're going to put our LED like this, okay? And then we're going to put our resistor, and then this is going to go up to V sub CC, right? And this will be R1, our current limiter, and this will be our, kind of call it LED1. And then over here, all right, we can go again, we can put another one, right? Go like this, and we'll have our other resistor. Okay, and then we'll have our V sub CC, and then we'll call this one R2, and we'll call this one L2 or LED2. Okay, so now, and then you can, do this as many times as you want for as much current as you can support here with your little buffer driver, all right? So now what's going to happen is the second this turns on, we're going to get this signal and these LEDs are going to turn on. And of course, if I want, I can flip this around. I can not use an inverter, and then I can just flip the orientation of the LEDs. Why does this matter? So what does the orientation of the LEDs mean as far as digital circuit design and driving a load? But remember, when you have a digital gate, the output high and low, so when you're high, a 1, right, maybe you can source 10 milliamps. When you're a 0, maybe you can sink 20 milliamps, right? So when you sink or put out a 0, you can actually sink more current. So if we're going to be driving a big load, then we want to use this in sink mode so that it's going to output as 0. So for example, in this case right here, I'm kind of making an assumption that the drive is asymmetrical, and when it's sinking current, you'll get more drive, so we'll get more current out of this thing, right? But if it's symmetrical, if these two things are equal, if they both just equal 10 milliamperes, all right, then it doesn't matter which way you set these things up. You can set them up so that they're going to ground, or you can set them up that they're getting current from V sub CC. But be aware of it, okay? So let's take a brief look at that real quick. So let's go look at the 7404 real quick and take a look at that. So I think I've got them all here someplace, and 7404, here we go. So here's a picture of a 7404, 74 LS04. So this is what they look like. It's 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12. There are 14 pin chips, and then it's in, out, in, out, in, out, and then in, out, in, out, in, out. So they have the same orientation like that. And you might see this configuration or this drawing of it. I kind of prefer this so I can kind of see what I'm doing as I'm kind of hacking on hardware. Now, if we go to the data sheet for this, so here's the data sheet. Okay, so here is the LS04 series data sheet, all right? And now if we scroll down through here, we can see the current, and I get a lot of questions about data sheets. You just kind of have to go through here. So now here's the 7404. We want the 74 LS04. So we got to kind of scroll through here because this is this data sheet is for multiple devices. All right, now, okay, so these are test conditions. We don't really want this. We want recommended operating conditions here. All right, here we go. All right, so and these data sheets, a lot of times they'll leave things out. All right, but the bottom line is, the bottom line is that, let's see here. Here we go. Okay. No, we don't want that. We don't want that. We want output. Yeah, so as you read through these, you have to figure out, what different things that they're referring to. But the bottom line is that the 74 LS04 series can basically sync something around 4 to 8 milliamperes, and it can source about 0.4 milliamperes. Now it'll actually go much more. It'll actually sync about 20. It'll source about 10 milliamperes. Okay, so the bottom line is that the 74LS is asymmetrical. So you kind of want to use it syncing current, all right? Because the syncing current, it can definitely sync more. So it can sync like this 8 milliamperes here, and like I said, it'll sync more. But when we use it as a source, when we output a high, it's very weak. So we kind of want to use it to sync things. So what we do, whatever we do with our LEDs, we want to make sure that we put them so that when the LED is on, we want to sync current, all right? So to turn the LEDs as bright as possible. All right, so let's go back here. All right, so now, and you can see here in my diagram, we've got it so that we are syncing current. So this is going to output 0, it's going to turn this thing on. So that's kind of how we want to set this up, because these are going to sync a lot more current than they can source, all right? Anyway, all right, so that's kind of, one circuit we can do right there. We can just do this circuit right here, and we can use the passive infrared to turn on the LED. Now, we already talked about extending the pulse, right, or shortening and extending it. We can do that with the 555 timer. Now, what if we want to do something interesting, though? If you look at these toys out in the marketplace, when they turn on, the eyes flicker and they blink. So what we really need is a source of, we need a clock signal or some kind of source so that we can kind of make these LEDs blink, all right? So let's go ahead and let's erase some of this stuff here. And let's show you kind of some ideas. So what if we, and what I'm going to do here is I'm just going to kind of get rid of some of this area here, all right? So this section right here, we could think of as our amplifier, as a digital amplifier. So we've got a digital amplifier right here. And what we want to do is we want to somehow make these things blink, all right? So we got to do this, upstream here. All right, so let's go ahead and let's take this. Matter of fact, let's just erase this all the way here. And so we've got our output here. Now, what if I were to put this through, say, an AND gate like this, and then we'll put the AND gate right here, and then, again, we will, so let's figure out what's going on here. So when this thing is on, right, we're going to get a 1 out here. So when this thing is asserted, we're going to get a 1 out here, and we're going to assume that we're going to get a 1 out of the AND gate. So when we get a 1 out of the AND gate, we're going to get a 0 out of the inverter chain. which means we're going to get a 0 here. So that means we just have to make sure to connect our LEDs to V sub CC and then our resistors and then back to the system. So this configuration will work, right? So we don't need another inverter here. So we're just going to connect this directly here. Now the question is, what goes here? All right, so what goes here is I want a source of square waves. So when this thing turns on, so we're going to have, now remember this is an AND gate, so when the passive infrared signal is asserted, we get a 1, then what's going to happen is we're going to see this pulse train. So let me draw this for those of you that don't think in binary, in signals. Let's do both of the signals. So I'm going to call this the passive infrared signal right here. So here's the PIR signal, all right, and then I'm going to call this the clock signal. All right, so this is, we're going to call this the passive infrared signal, and we'll call this the clock signal. All right, so here's these two signals right here, okay? And so the clock signal, we're just going to have this clock, which is just going to be going up and down like this, all right? And this is going to be in the hertz range, you know, 1 hertz, 2 hertz, 10 hertz, so we could see it blink, right? Okay, then we're going to have this passive infrared signal, and it's going to be off, 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 off until it's triggered. And then it's going to be on like this. Okay, now this signal right here, I'm going to call this the AND signal. Okay, this is the AND signal. So what's the result of these two things if we were to AND them together, right? So let's go down here and put this here. All right, and this is going to be our AND signal, our ANDed signal. Okay, and what does that look like? Well, so we're going to have two signals here, right? And this is kind of like, you know, A, and this is kind of like B, and this is the output. We can call this Y, right? So we're going to have A and B equals Y. So A and B. So here we go. So here's A, here's B. So if we have a 0 and a 1 or a 0, it doesn't matter. So we're always going to get a 0 out, right? So if you remember the AND, 0, 0, 0, 0, 0, oops, 0, 1, 0, 1, 0, 0. The only time we're going to get a 1 out is when both inputs are high. So the only time we're going to get a 1 is when both inputs are high. Well, no matter what, this is always low. So we're never going to get a 1 out. Now, over here's where things get interesting in this area. So we're gating the signal. So over in this area, we're going to get a 1 here, and we're going to get a 1 here. So here and here, in these two spots, right, we're going to basically get a copy of the clock signal. Okay, like this. And then it's going to turn off. So only when the passive infrared is enabled, it will basically copy whatever's happening on this clock to the output. And then this clock signal goes up here and drives this right here. So basically we've got the passive infrared. We're going to put it through an AND gate. We're going to gate it with a clock signal. We're going to generate this clock signal somehow, which I'm going to get to in a second. Then we're going to put that through an inverter chain, 2 or 3 of these in parallel. Then we're going to take that output and we're going to put those directly to LEDs. Now, another thing you could also do, we could put another inverter here and then maybe put 2 pairs of these inverter gates in parallel. So we could create 2 outputs that are maybe opposite. So you could have these LEDs alternating if you want. So there's so many things you can do. You can just, you know, play and have fun. Okay, so now where are we going to get this clock signal? So where we're going to get the clock signal is we're going to hook up a 555, and we're going to hook that up in astable mode. Okay, and that just means it's just going to sit there and do this. All right, and then if you remember, there's basically 2 resistors. It's RA, RB, and a C. And when it's in astable mode, you hook this thing up, and I'm going to show it to you in a second. We're not going to do it here because you can just look at the data sheet. But the frequency is a function of RA, RB, and C, and then you get a square wave out of it with a certain duty cycle, and then you can muck around with that. That's how we're going to generate our signal. The signal comes out on pin 3 usually, and then we're going to just hook this up to V sub CC, obviously, and ground. All right, and so that everything is hunky-dory. Okay, so let's take a look at some of these chips real quick, so that we're all on the same page here. So we already looked at the 7404. You guys know what that one is. Let's see. Here's a 74 LS08. So this is a quad 2-input AND gate. So it just looks like this, just in, out, in, out, in, out. All right. Same thing. It has the same kind of drive as the other guys. So if you look here, I output high is 0.8, right? And then I output low is 16 milliamperes. So this one's got a pretty good drive, actually. All right. Now, and then if we want to look at what they look like more graphically, again, so it's in, out, then there's ground, then it's in, out, going in the opposite direction. So that the gates are always oriented in the same direction. So it's pretty easy to remember these little 14-pin TTL chips. Okay, so that's that right there. And then let's go back to our 555 timer. I think I have, let me see, do I have a data sheet for it someplace here I already got for you guys? Take a look. So we've talked about the 555 obviously a gazillion times. And if you go through the data sheet here, it'll show you all the different modes of operation, all the different pins. It's only got 8 pins. And then we wanted an astable mode or astable mode. All right, so if we go down, scroll down, scroll down, scroll down, there's monostable, and here is astable mode. So in astable mode, you've got 2 resistors, RA and RB and C. This sets the frequency and the duty cycle. Then you have this little extra 0.01 microfarad you put on 5. This is for noise. I can't remember. I'd have to look at it to see exactly why that's there, but put that there, and then we've got ground here. And then you can put the load either from the output pin 3 to ground, or you can put it from the output pin 3 up to V sub CC. Either way you want to do it, you can put your load. So that's why it's showing that as kind of dotted lines. And then the equation for it should be here somewhere. Yeah, so here it is right here. So the frequency is 1.44 over RA plus 2RB divided by C, and then the duty cycle is RB over RA plus 2RB, all right? So the bottom line is what we're going to do is we're just going to use like a 10K and 100K potentiometer for RA and RB, and I'm going to just set C at like 10 microfarad, and then we'll just adjust the frequency and duty cycle so we get a nice square wave out. All right, so that's the plan. Okay, so let's go back here and take a look. So in a nutshell, we are going to use a passive infrared sensor. We're going to use an AND gate. We're going to use an inverter gate. We're going to use some LEDs. We're going to hook this all up and we're going to make this. Okay, so let's go over to the bench and let's take, so I've already made it. Let's go over to the bench and take a look and we'll go from there. Okay, so here we are on the bench, and you can see I've kind of got this already built. So the first thing is, let's take a look at our passive infrared sensor. So here it is here. And like I said, it's got a little dome here. You can take this off and see the sensor right there. Matter of fact, let me see if I can get it to focus a little bit, and let's go take a closer look at this. There we go. And let me see if I can get it to focus for you. There we go. So that's what it looks like. Pretty cool. And then on the back, a couple little chips, this and that, and you notice there's no adjustments on this, no potentiometers, all right? So not a lot of features on this particular sensor, okay? All right, but you can see, and let's go down here a little bit farther, you can see that this particular sensor has only 3 outputs here. And let me put it back here so you can kind of see here. And let me get it to focus. All right, so we just got 3 outputs. So it's got power, ground, and the actual signal, all right? So I've got power, ground, and then I've got the signal here going to the oscilloscope. So we're gonna look at that in a second. And then the other thing I wanna bring your attention to is the power supply. So I've just got a power supply. This is actually a Raptor PSX from another bonus lecture. So if you wanna see how to build this, this is pretty awesome. So it's got an input for external wall adapter, lithium-ion battery, USB. It does 3, 3, and 5 volts, 3, 3, and 5 volts, and it has a boost converter for the 5 volts, so you always get 5 volts, and it'll do an amp out of the 5 volts and an amp out of the 3.3 volts. So this is, and it's got terminal blocks, so, and protection. Very, very cool. Anyway, so that's that guy right there. So now let's go take a look. So if you see here, on the oscilloscope. So this top waveform is actually the 555 already generating a signal. The bottom waveform is the passive infrared, all right? And the passive infrared, so now one of the problems with this is, you know, it's got to kind of cool off. So I can't move around. So I'm going to not even breathe here. All right, I breathed. All right, let me get away from it. All right, I'm not going to move. These things are they're super sensitive. So you can see it keeps triggering. All right, I'm not going to even move. I'm not going to breathe. Okay, now I'm going to move. There we go. All right, so it does work. I assure you of it. And so now let's take a look at our circuitry here. So we've got our power supply coming in. Here's our 555. Now, I told you on the 555, we are controlling the duty cycle and the frequency. So watch this potentiometer adjusts the frequency, I believe. All right, and then as you can see right here, that's the frequency. So 36 hertz, that's a little bit too fast for us to see, 100 hertz. So I'm going to slow this way down, way down into like 15 hertz. That'll make it kind of a good little flicker you'll be able to see. All right, so that's that part of things. All right, so then we have the output of the 555, which is sitting here and right there. Then we've got the output of the passive infrared. So all we need to do is take the output of the 555 and the output of the passive infrared, and then we're going to put it through the 7408, which you see right here. So the 7408, and let me just go ahead and move this for now. All right, so there's our 7408. And we've got input, input, output, input, input, output, all right? So we just want to do input, input. So let's go ahead and we're just going to connect those right now for everybody. All right, so we're going to take the output of the 555 and we're going to put that into one of the inputs here. I'm going to do that. All right, and then we're going to take the output of the passive infrared and we're going to put that into the other input. All right, and whenever I do these things in real time, I never know what's going to happen. So we will just hope and pray it all works properly. Okay, so that's good. And then here's the actual output. All right, and now if we look at this other chip here, here's the 74 LSO4. I've got two gates in parallel. Two is all I needed. And I've got these LEDs over here. Let me slide them here. These two big LEDs, these are my daughter's favorite kinds of LEDs. She'll kill me if she saw me using these. Anyway, so we've got two LEDs and they're just floating right now. So it's floating high, so we're getting a low, so they're on. And there's our resistors, just like our circuit. So basically, these are amplifiers right here, so we can get about 20 or 40 milliamps out of this 74 LSO4. So now we're going to take the output and I'm going to put it right into the input here. Okay. And the first LED, the first inverter is not being used. That's right there. That's if we needed to invert it again. Okay, so now, as you can see, we get our blinking LEDs, which is exactly what we want. All right, and now, so this is kind of, I'm moving around in front of this, obviously, as I'm talking to you. So I'm going to move away. So first thing I'm going to do is, let's see, let's turn off some lights here. Let's get more of a Halloween vibe going. All right, so now what I'm going to do is I'm going to move away to the door here. All right, so now I'm literally going to leave my lab. All right, and you're seeing, it's seeing me move around. So now I'm not moving, I'm just going to sit very still and let it calm down. So I'm about 15 feet away from this right now. All right, 15 feet away. Okay, so now it's calm, nothing's happening. So now I'm going to just wave my arm, and there it is, boom. So 15 feet away, it caught my arm move, all right? So that's it. So that is your Halloween sensor, passive infrared with lights, all right? So now let's go ahead and let's make this a little bit more fun. So I thought what I would do is something else. So let's go ahead and we will take out these LEDs here and we will put in these smaller LEDs, okay, like so, and flip this one around, okay, okay, all right, Okay, now I'm going to, through the magic of editing, do something and then we'll come back. Okay, so now we have a proper Halloween decoration that I drew and then printed out. And now if someone were to walk in front of our sensor, here's what would happen. Pretty cool. So that is it. All right, everybody. So happy Halloween. I hope you like that little Halloween decoration bonus video. And I will see you guys in the next video. Bye. Welcome everyone. We are doing a bonus lecture and it is Christmas and it is going to be 2021. So this is about a week before Christmas that I'm recording this. So Merry Christmas, Happy Hanukkah, whatever else that you may celebrate or not celebrate. We're all at least going to celebrate the new year that's going to happen in about a week and it'll be 2021. And you know, I literally just remember it being turning 2020. So 2021, obviously for obvious reasons, COVID and the economy and all kinds of things. The world has gone through a lot of stuff in the last year, but I feel like 2021 is going to be a lot better. And so one thing that a lot of students have asked me about is how to get into embedded engineering as a job, right? And you know, how do you start? How do you do it? So this is a, you know, this is a really big question. You know, how do you get any kind of job really? But I think I can bring some insight into how I get jobs and how I started doing contracting and then started my own company, software company, then hardware company, and kind of maybe give you a little seminar on doing things maybe out of the box, thinking out of the box, doing not what everybody else does, but do things differently. And that's the only way to be seen or heard in a world of 8 billion people where everyone does the same thing using the same social media, the same tools. So anyway, this lecture is going to kind of be just, you know, like all of my lectures off the top of my head. I've kind of made an outline of some things I want to talk about, but I think you'll find this insightful, whether you're trying to be an embedded engineer, a software engineer, any kind of engineering job that you want, and then some of the things that you kind of need to do to prep for that. And you know, and be honest about what you really need to be competitive in the marketplace, right? So, so let's start off. Let me pop off this Merry Christmas thing here. And let's start off, and I've just put this up here. This is a little website, Upwork, which I'm going to talk about. But let's start with, you know, prep and training. All right, so like anything, if you want to be an electrical engineer, an embedded engineer, a firmware engineer, a software engineer, a web engineer, a front end, a back end, whatever it is, you're going to have to study. You're going to have to train for this, right? And this, in my case, took many, many years, and I'm still doing it. You know, 40 years later, I'm still reading books and studying. So typically that it requires getting a degree, reading lots of books, taking extra classes, doing projects and all that. Depending on your age and who you are and your financial resources and your life, you may not be able to go to school and get a formal degree at a 4-year, or 6-year, 8-year college, depending if you're going to do a bachelor's, a master's, PhD. And you may just have to learn online, which is great. I mean, you can go to Stanford, MIT, Udemy, Coursera, you name it. All these online educational platforms have really high quality courses, so you can definitely learn from them. It's important though. I want to make a point that I think that in the past few years, people have kind of they don't realize this as much as they should. But when you're learning about something, you really want to learn from an expert, someone that has credentials, has a pedigree, that knows what they're talking about. Otherwise, it's kind of like the blind leading the blind, right? So you don't want to take a course from somebody who's not an expert in something, because they're going to probably teach you. They probably know more than you do, sure, but they're going to teach you things in the wrong way. So everybody now can be self-published, self-produced, self-everything. And that's not good. When I write one of these books that I write, there's probably 50 people that review that book. There's technical editors, there's development editors, there's copy editors, there's legal review. There's so many different kinds of editors that review it. It can't be wrong. Uh, they're checking my English. They're checking the technical correctness of it. There's usually a technical editor that's expert in the field that the book is about, and he knows or she knows a lot about it. So when they're reading it, they're going to catch your mistakes. Now everybody can just do anything they want, publish it, and say they know what they're talking about. So the point that I'm making is, uh, formal courses at a formal university with a teacher that has credentials, degrees in the field that he or she is teaching is very important. Also, if you're going to learn about something, I know it's really easy to go on internet and just kind of read random articles on Hackaday or this or that or whatever it is that you read them from, but it is really important to read books. Books take a lot of energy, and a person who's going to put the time and energy and effort into writing a book is usually pretty skilled at what it is they're talking about. Sure, there are bad books and good books, but nevertheless, if a book is going to be published by a publisher, it costs hundreds of thousands of dollars to publish a book. They're not going to invest that money if the person writing it doesn't know what they're doing. So the point is, as part of your training for whatever it is, embedded engineering, you've got to take courses, get a degree ideally, read, study, and learn from experts in the field as much as possible, people that really know what they're talking about. Okay, so that's step one. All right, so since the question has been, obviously this course is about electronics and PCB design, and people are interested in becoming embedded engineers. So there's different subfields of this, right? So you could focus just on firmware, and a firmware engineer is someone who programs the microcontrollers or microprocessors, and just basically you write software. You may have to, you're going to write software to control bits of hardware, but you're not going to be designing hardware per se. You're not going to be designing circuits. You're not going to be designing printed circuit boards. You're not going to do any of that. An electrical engineer or another embedded engineer is going to do that. He or she's going to give you a system, and then you're going to write the firmware for it. Now, the firmware may have different levels. We may be talking about something with a microcontroller in it that's very simple, like a toothbrush, right? Or a remote control. This little remote control has a microcontroller in it. It has a transceiver. This one's infrared, so this has an infrared transceiver. So an electrical engineer or embedded engineer would design that, right? A mechanical engineer would do the packaging. An industrial engineer would do the what it looks like, the look and the feel, right? And then they would present this to you, and then you would have to sit there and read about the microcontroller that's used. You would have to read about the infrared transceiver that's used. So you're going to read all this documentation. Then you're going to sit in C, C++, and assembly language, most probably, and write the code to control that remote control. And you're going to work alongside with the electrical engineer, asking him or her any questions that you have about the interfaces and so forth based on the schematic. And now, a lot of people that go into firmware, they may have backgrounds in electrical engineering, but they just don't like the nuts and bolts of it. They like the programming better, so you kind of go into firmware. Now, the next level of firmware, so now that we're talking about microcontrollers in one case, and now we might be talking about more complicated microcontroller systems. Maybe instead of using a little 8-bit microcontroller, it uses a full 32-bit ARM Cortex M3 or M4 or M7, right? Which is very powerful, right? Those processors are entire systems on a chip. And maybe that's inside of a set-top box, or maybe it's inside of a car controlling car subsystems, or a video player, something of that nature. So when you're talking about that, maybe you've got a rudimentary operating system. You might have FreeRTOS or some other operating system that may be on there, like Micro Linux. And so you're going to have to learn about that. You're going to have to read the manual on FreeRTOS or Micro Linux or whatever it is. And maybe your programming is going to be in C and C++. Maybe it'll be in Python. Who knows? And so you, at that point, you may be writing much higher level software, writing device drivers for pieces of hardware. You may have to communicate with more complex pieces of hardware. You may have to be talk to video transcoders, audio systems, microphones. You may have to control motors. Who knows what you may have to do? But we're talking about more high-level things, like something like a phone almost, right? And you could think of a phone that has an ARM processor, even a microcontroller, not a full-blown processor in it. All right. So At the low level, a firmware engineer might just do microcontroller kind of programming. Maybe he's got 1K, 2K, 4K, 64K, 128K, 512K. Then you start getting to a point where you're getting at a high level, and maybe now it's all in C++. Maybe there's a little operating system there. There's a bunch of device drivers you've got to integrate. So that's kind of the firmware programming, right? And so that's what a firmware programmer does. All right. Now, the other kind of embedded engineer might be someone who does the hardware. All right, so that embedded engineer, he's going to do the electrical design, and he's going to do the PCB design, and maybe he or she is also going to do the programming and the firmware as well. So in that case, you might be a full stack engineer, where not only are you doing the electrical design, the PCB layout, you're actually writing the firmware as well. Or you might write some of the firmware to get the system up and running. So for example, I'll do a lot of systems where I would like to write all the firmware, but maybe they can't afford me to write all the firmware, so they can pay someone a lot less, maybe to do the firmware than to pay me embedded engineering hourly rates. So I'll do all the embedded engineering for the product. I'll design electrical design, the PCB design. I'll get it all working, and then I'll write maybe some low-level drivers, some demos. Maybe I'll make a little SDK, a little API, right? And then I'll hand it off to another firmware engineer, or engineers plural, and they will finish the rest of the firmware and then work on the project for maybe 1, 2, 3 years thereafter. So that's so a typical embedded engineer, that's what we do. So we'll design the hardware, we'll design the PCB, we may do the firmware, all right? And then within embedded engineering, now you have all these different subfields. You have people that are maybe that are much more expert in, say, RF. So they like doing radios and transceivers and wireless communications, right? So maybe they're really good at that kind of thing. Or maybe they're experts in mechatronics, so controlling motors and servos and steppers to do mechatronic devices. Or maybe they're good at signal processing, digital signal processing. So they may be experts in doing image processing or audio processing. And so, and the list goes on, like IoT. So you could be an expert in maybe Bluetooth and Wi-Fi connectivity. So, people that do that. Now, here's the reality. So I've been doing, electrical engineering, embedded engineering a long time, like probably 3 decades at least. And no matter what, I don't know everything. No one does. And the majority of things I have to do, I have to learn them on the fly. Most people do. Even if you've done Bluetooth or whatever it is a bunch of times, there's always something different. So no matter what, you're always going to have to read the manual. You're going to have to read the documentation. You're going to have to do examples. You're going to have to take time. So every project you do is always going to have a lot of effort and energy reading things, figuring things out. And that's just part of it. Embedded engineering is really complicated. And again, if you're going to be a full stack embedded engineer, you have to be expert in PCB design, electrical design, firmware, and all those different things. If you want to start to specialize in just firmware or just the electrical design or just the PCB design, you can do that as well. All right. Okay. Let's see. And then now some of the other things, you hear me mention the word mechanical a lot. So say you're going to be an embedded engineer. So you're going to be an embedded engineer, and let's say, for example, a company is going to contract us to design a calculator. Okay. So, all right, great. So let's start here. So we're going to do a calculator. We're going to say, well, we can do all this math probably with a Cortex ARM processor, right? So a 32-bit processor with a floating point unit. We can do all the math, and we're going to have to write a bunch of software, obviously, to create a user interface so that users can type and we can process the mathematics, the algebraic expressions, and so forth. We can do integrations, derivatives, all these different mathematical operations. So we're going to write a lot of software to do all that, right? Now, we're going to have to design this hardware, and then we have to keep in mind, we're going to have to think, okay, well, maybe we're not going to do all the software because there's a lot of mathematics involved here, right? Unless you're a mathematician, you probably are not going to know how to do all kinds of approximations and matrix algebra and vector calculus and all the different kinds of things and numerical techniques that are needed to build a calculator's software. So someone else will probably do that. Maybe a software engineer will do it, right? And he'll look at this like a black box, okay? However, you're going to have to design the electrical design for it. And the electrical design for a calculator, so basically we're going to have a microcontroller. Maybe we're going to use a Cortex M4 with a floating point unit, or maybe maybe a Cortex M7, or maybe some other processor, right? We're going to have a display, so we're going to have to drive a display and have a processor. We're going to have a big ROM memory. We're going to have a power system with solar panel on it, a solar panel to do the charging, right? And but other than that, we don't have a whole lot. We don't have Bluetooth. We don't have Wi-Fi. We don't have haptics. We don't have motors. We don't have any kind of wireless charging, right? We just basically have solar, batteries, and buttons. So a bunch of buttons that we have to hook up to a bunch of GPIOs. And that's that. So a lot of what a calculator is the mechanical engineering of it, right? What it looks like, right? So it's important that you know about that as well, meaning you don't have to become a mechanical engineer, but you should know how to use SolidWorks or Fusion 360 or to design something very simply and 3D print it so you understand the language that mechanical engineers use. All right, because when you build products as an embedded engineer, it's going to go in something. It's not just going to be a printed circuit board, floating out in space, right? It's going to be a part of a product. So you want to be able to communicate, and when they're talking about, this should be 20 thousandths or 5 mils, or this needs to be retained better, or this right here is going to have, it's going to be a compression fit or a magnetic fit. You need to know what this stuff is. So you need to learn about the other fields, ancillary fields that are all part of product development, including manufacturing. And that's only going to help you because here, remember what I said in the intro, I'm not interested in being like everybody else. There are tens of thousands, hundreds of thousands, millions of people trying to become electrical engineers, embedded engineers. I want to be so unique that hands down, when someone looks at my resume or looks at my portfolio, they're like, why would we hire anybody else? This guy knows everything about all these different fields, and he's worth this outrageous amount of money he's requesting per hour or for the project, right? Okay, so that's where you want to be. So you want to study these other fields as well. So you're not just, I just know how to make PCBs, or I just know how to do electrical design, or I just know how to do firmware. You still have to study these other fields, and that's very important. It's not just about being well-rounded. It's about having breadth and depth of knowledge. So you can specialize, and maybe you're just an expert in IoT. That's great, but know something about mechatronics, know something about mechanical, know something about manufacturing. You need to know how a product is built. That's really important. Now, look back to the 70s, right, or the 60s or the 50s, and IBMers, right, and these people that would work at IBM, and they have one tiny little job, right, and they're in their little cubicle, and they do this one little thing, and they have no idea what comes before or what goes after. That still happens today, right? You have a lot of people who learn something in school, they do the projects in school, but they've never done anything on their own, right? So the next part of becoming an embedded engineer, so let's say that you're, maybe you're self-taught, you're trying to take classes, all right, or maybe you're going to school and you're about to graduate or you've graduated. You need to show something. Now, artists have what's called a portfolio. Do you have a portfolio? Have you built a bunch of projects and products and made stuff, right? If the answer is no, then this circular problem that people always say, well, how do I get a job without experience? But how do I get experience without a job? Well, you do it yourself. So when I was learning about programming or electronics or whatever it is, I make a list of things I don't know how to do, right? And I go through that list and I do them. So, and over time, this takes a long time. It's not going to happen overnight. But, when it came to electronics, right, I started playing with electronics when I was very, very young. I was probably 5 when I started playing with electronics, and I was about 10 when I started programming, right? You couldn't get your hands on a computer before I was 10. But I started playing with electronics by the time I was 5, with circuits, with resistors, LEDs, batteries. That's about all I had, and then 5, 6, 7. Then by the time I was 10 or 12, I was building things with microcontrollers. So over time, I became knowledgeable enough to know what I didn't know. And I started making a list. I want to make a radio. I want to make a blinking light. I want to make this. I want to make that. And embedded engineering is no different. You need to make a big list of all the things you don't know about, right? Maybe you don't know about RF theory. Maybe you don't know about semiconductors. Maybe you don't know how a microprocessor is designed. Maybe you don't know what an ALU is or how it's designed. Maybe you need to know a little bit more about FPGAs, field programmable gate arrays, and programmable logic. All right, you need to make a list of all these things, then come up with little projects and say to yourself, all right, I'm going to make a little project that does this. I'm going to take a little microcontroller and it's going to do this. And maybe I'm going to do something that's some kind of Wi-Fi device. Maybe I'm going to make something that's a little Bluetooth device. Oh, I don't know anything about stepper motors or servos or brushed or brushless motors. So I'm going to make something that controls some motors. And you just sit and make project after project after project. Ideally, if you can design the project, maybe make some firmware, maybe make a printed circuit board, and making printed circuit boards unto themselves is a whole project, right? The process of coming up with any idea and then designing the circuit and then building a printed circuit board is super awesome. And I talk about this in the course, obviously, when we do the whole circuit board design thing. But the ability to take an idea, design the circuit, and make a circuit board is really powerful. And that's what you need to do. You need to build a bunch of different projects. And the same thing if you wanted to be a software engineer. When I was learning programming, right, I got my hands on a TRS-80. In the late 70s, and I used to drive my bike, and I think I've said this in lectures, I used to ride my bike when I was a little boy, pedal to the Radio Shack, and I would sit on that computer and program in BASIC. I'd read the manual and program in BASIC. Then I kept hearing this Z80 assembly language. I'm like, what is that? So then I figured out how to program in assembly language. Then I started programming in assembly, and I started making video games on the little TRS-80. And then once I started doing that, then I read about, well, what is BASIC? It's a language. How does that even work? And then I started reading about parsers and things of that nature and interpreters and compilers. And I said, well, I'm going to write an interpreter. I'm going to write a compiler. And then the same thing, once I got really good at programming and I understood all these things, then I said, well, wait a minute, I've never written a database. So why don't I learn about databases? So I read books about databases and how databases work, complicated ones, and how do you do it, right? How do you build a database? How do you write your own database? And then I said, wait a minute, I'm using a paint program. I'm going to write a paint program. So I wrote a paint program. Then I wrote a 3D program. Then I wrote a music program, right? And I suck at music. I don't know anything about music, right? Other than I like it. But I learned about, how should I approach writing a music program and record different tracks and then play with them. So I sat down and made a list of every kind of program and I wrote one. So I had all that experience. That became my portfolio for my programming jobs. And then I did the same thing with electronics and embedded. So you need to create a portfolio of projects. So you can't just come to an interview and say, I think I know how to do something. I want you to show it to them. Take your hand and here's a project that I made. Here's another product. Here's another product. And that's how you overwhelm them with expertise. Like, okay, this guy's designed the PCB, he's made the PCB, he's done the firmware. I absolutely think he could do this project. Or imagine a guy comes in or girl comes in for an interview and they say, well, I think I could do it. I went to school. That's not enough. You're going to be like everybody else. Okay. So let's see. So let's go here and let's see what else I want to talk about. So let's say, for example, you want to start designing your own projects, right? And so let's talk about kind of, how we would fund that or pay for it. So now you could pay for them yourself, right, which you're going to have to do. And then some other things that you can do is, and I've showed these things. So here's like a Seed Studio, and it's got 3 E's. And what this is all about is you can actually design a product, upload it here. They'll manufacture it for you. They'll make the PCB for you. They'll do the electronics, the assembly, and then you can actually sell it on here for 10 bucks, 20 bucks, 50 bucks, 100 bucks and get people to buy it. So it's almost a way to take a little idea that you make and actually sell it and monetize it, right? And that's what this is all about. Okay, the notion of, I want to do something while I do a job to pay my rent. I'd rather pay my rent by doing what I like to do, right? So as much as possible, you want to try and monetize the things that you do so that you can use that money to pay for more things that you like to do. All right. So Seed Studio is one example. So you can design a product, you can put it on here, and you can sell it. Okay. So I highly suggest that you do this. Now, another thing that you can do is obviously everyone's heard of Kickstarter and crowdfunding and all those kind of things. So there's a number of different sites. Now, but there's a couple sites you may not have seen. So let me show them to you. So say you want to come up with a project and maybe it's a little bit bigger and you want people to fund it. Now, this is a really, really bad idea if you're not an expert at building products. If you haven't built a hardware product before, you are 99% probability going to fail at it. Absolutely. If you built one before, maybe you're going to be at 70% probability of failure. If you built 10 of them, then maybe it's 10% probability of failure and 90% success. The point is, be very careful using crowdfunding to fund electronic projects, because you will, underestimate how much time, how much money, how much just enormous resources it takes to build something physical. So be careful. But that said, the first one I want to show you is this one, and this is called Crowd Supply. I've showed this inside the lectures, I don't know which lecture, but this is a really interesting website. This is mostly hardware stuff. It's not like Kickstarter, so this is mostly hardware. And again, they will manufacture, do the PCBs, do the assembly. They'll make a video for you. So this is like a Kickstarter just for hardware stuff. And they'll kind of help you sell the product and make videos for it and market it and all that, and then put it on here. So this is pretty cool. So like if we just type in, let's just type in something. We'll type in Arduino. And let's see here. So yeah, here's something. So look at this, Microduino. All right, Microduino, so this is funded on 2017. It had 230 backers. He had a goal of 5,000 and got 10,000, right? And this looks like it's just an Atmel, looks like a 328p, a button, USB, power, and that's about it. And they probably emailed all of their friends, and were able to get 200 of friends and things on Facebook and maybe LinkedIn. Who knows? But pretty simple. This is clearly a prototype, not a manufactured. So it's got an Atmel 32U4. This isn't the manufactured version. But anyway, so there's $10,000 raised. So it's enough to fund the project, so you can get the project done. You can make the prototype, ship them out, go through the process, and understand what it's about to ship a product. Okay, so that's Crowd Supply. So I suggest you look at Crowd Supply. Then the big dog is, of course, Kickstarter. And you can raise millions and millions of dollars on Kickstarter, but everybody uses Kickstarter, and the quality of Kickstarter, some of these videos, I mean, they're incredible. The videos themselves take $50,000, $100,000 to make. But again, we'll search for Arduino and see what kind of Arduino-y things there are. And so 708 projects, that's a lot. So let's just look at something here. So this was 3 days ago, TimmyBot. Let's take a look at that. And some of them are really bad. What I like doing is looking at all these Kickstarter videos and look at the ones that got funded, the ones that didn't get funded, and look at the videos. Ironically, some of the videos are incredible for, say, some little product, but they didn't get funded at all. And you scratch your head and say, why? It's a mystery. Then some of them have really bad videos and they get funded, and you're like, that's odd. Anyway, there's not a lot of logic to it. So anyway, but it's worth going through the projects and saying to yourself, well, I could make this. So look at this. So he puts up, or she puts up, this thing called the TimmyBot here from Mexico, and basically looks like a ultrasonic HC, what is it, HCR SR04, kind of like a parallax ping sensor, and looks like probably an Arduino design. And this is a lot of work. It looks like this looks completely custom. So they made a circuit board. They got 2 motors. They've got battery. So this is a whole little robot. And sadly, it's been open for 3 days. 3 days to go, actually. And they wanted $1,300, only got 76. So this is probably poor marketing, because just looking at this, it looks like it's okay. But again, this is something like, if you want to make a little robot, design a prototype of it, figure out how much it's going to cost to ship it, to make it, to do all those things, and then go ahead and put it on Kickstarter. All right. Okay, what's the next one? The next one is Indiegogo, and Indiegogo used to be kind of people would kind of turn their nose at Indiegogo and go, it's nowhere near as good as Kickstarter. But these days, Indiegogo is pretty good. So let's try something here. How about let's try FPGA, Field Programmable Gate Array. Let's see if anything comes up. All right, so look at all these little projects right here. So this one right here is Flea FPGA. So let's take a look at this. Well, let's see if there's anything else here. That Ultra Miner, that looks like that's for mining Bitcoin stuff. This one, this is kind of interesting here. This one ended. Let's take a look at this one. Okay, so a UJA board. So Zinc 7000 on a chip, Emily Schmidt. from Germany. Very cool. So it looks like she designed this board and put the Zinc 7000 on it. And so let's see. Now, and interestingly, only 32 backers, but she was only looking for 5 grand. So people paid a lot for this. So if you look at this, I'm kind of shocked actually. Can I scroll this down, or you can, let's see, continue reading. Here we go. So it looks like, yeah. So people were paying 500 bucks a pop for this, 500 bucks, and listed as a contributor. So $500. Wow, that is a lot. That is a lot. So she was able to get people to put in $500. So these are people that really believed in this project and maybe wanted a Zinc 7000 FPGA. And so maybe there were none available that people liked. So she said, I'll build one with what we need and all the interfaces, and then sold them for 500 bucks a piece. So she rounds up 7 grand, and maybe these boards cost about 100 bucks each. So maybe the whole thing will cost 3,200, and then she, walks away with 3 grand to keep funding her projects. But also, it's not just making money we're talking about, it's building a portfolio so you can get jobs and contracts as an embedded engineer. All right. Now, okay, so now let's talk about the next thing. All right, so we've talked about kind of you've got to study, you've got to learn about this. Now, maybe there's some ways that you can build projects and have them funded by people so that you can get things done and not do it out of your pocket. Now, let's say that now you want to get a job. Maybe you want to start off in you want to do contracting. Maybe you've got a wife or husband, you've got a bunch of kids, and you just can't go, you're at home, I don't know. And you just want to do contracting at first, or maybe you've got another full-time job and you just want to kind of dabble. So where do we even find contracts, right? So how do you even do that? So there's lots of ways to do this, and you got to be really, really, really creative. Now, depending on where you live, there's word of mouth. There's lots of ways to find embedded jobs, and you have to be very creative about it. So I'm going to talk about, some of those things. So the first thing is, let's see here. Let me see what I'm looking at here. All right. Now, lots of countries have a thing called Craigslist. All right, you may have heard of this or not heard of this. And Craigslist is just kind of the super old 90s website that you can find jobs and you can do things. Right now, a lot of people don't know that Craigslist is worldwide. So Craigslist worldwide, and you can see, you can go here to Europe. Oops, you can go to here, Europe, and look at all these countries: Bulgaria, Denmark, Czech Republic, France, Germany, Greece, Hungary, blah, 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 all these different countries. So you can actually get to Craigslist, and a lot of people use this because it's really, really simple. Now, I'm in Austin here. Now, there's a couple sections you want to check here. So if you go over here to jobs and you go down to jobs, in jobs here, there's a lot of electronic jobs, electrical engineering. Here's the engineering section. Then there's another thing called gigs, computer gigs, etc. So if we go to gigs, let's just go to gigs and we'll go to computer for kicks. All right, I'm just showing you how I think. All right, so you go to computer gigs and let's just type in electronics. All right, let's just type in electronic. Okay, prototyping electronic product concept with accelerometer. Bam, first one is an embedded job. That's an embedded project right there. So let's look. I am building a top secret prototype of an innovative new product that involves activation of an electric motor based on the movement and position. If you have experience with wiring up accelerometers and you would like to be considered for this project, please contact me to discuss. Must live in the Austin area. There you go. Boom. First try, I find an embedded job. That's an embedded job. So someone wants you to take an accelerometer, hook it up to something, turn on a motor, do whatever you need to do, and then make this all work for them. All right, so you could probably charge, 500, 5,000, whatever it is, depending on the complexity. So that's the point, is you can look at Craigslist to find these one-off little things here, which are really interesting, right? Now, you can also go, instead of doing computer gigs, we'll go back, and you can go to jobs and just go to the engineering section. And this is like, hardcore engineering. So we could just look for, we'll look for electrical. Now, another thing is people don't really know the difference between an electrical engineer and an embedded engineer. And I'm not sure, there is a difference. So my degree is in electrical engineering, and I use electrical engineering to do embedded engineering, right? So, maybe an electrical engineer, people think of someone that just kind of plays with resistors and capacitors and diodes and charging circuits and transformers and knows circuit analysis and all that. Yeah, but an electrical engineer plays with microcontrollers and microprocessors and circuit boards and all that. So anyway, you got to kind of know what to search for. So that electrical doesn't come up with anything. We'll go to embedded. Didn't come up with anything. Let's try firmware. Firmware is a word that a lot of people use. Okay, nothing coming up there. So let's back up and we'll go back up here if we can. And we'll go back to that. So if we were just to go to jobs at the root, and now let's try firmware. Let's see if anything comes up here. FlexTech is now hiring low voltage technicians. So anyway, nothing in here right now. The point is, things like Craigslist are good to search in. Now, let's go to another site to search for jobs. This is another site. It's called Monster, and you may have heard of this. This is another great way to find jobs. But the thing that I want to convey to you is everybody knows about Monster, right? Billions of people know about this website. So you're just doing what everybody else is doing. That doesn't mean you shouldn't do it, but I just, keep that in mind that everybody is doing this. So keyword or title, now let's type in embedded. Now look, Austin is the #1 hardware startup city in the world. This is the number, it's better than Silicon Valley now. It's the #1 of a lot of things now. So this is the engineering focus of the planet right now. We'll type in embedded. And you can see 364 jobs, and these are all very high-paying jobs, all these embedded jobs, lots of good stuff here. And you just go through here, and you would start looking at what they're requiring and start sending resumes to them, all right? So that's Monster. Now, there's another thing that a lot of people don't know about is LinkedIn. You may know about LinkedIn, but you don't. A lot of people don't know that this is a great place to post jobs and look for jobs, okay? So if you go here and you type in, say, embedded here, okay? Let's see here. Embedded full-time, embedded software engineer, embedded systems engineer, embedded this, embedded that, embedded Linux. Lots and lots of job possibilities here that you could send your resume to, all right? Now, what's the other thing that you're going to do? Well, you're going to go to cool companies that you want to work at, and you're going to see if they have any positions open, right? So that's what you're going to do. So like Tesla, you want to work at Tesla, right? So you go to Tesla's website, and you look at their awesome new cars, and then you scroll down to careers. And all these websites of these large companies have careers, whether it's Intel, this, that, or whatever. Now you can get a job at a massive corporation, right? And or you can get a job at a massive corporation that's super cool, like Google or this or that. So anyway, the point is you may make a short list of cool companies, Tesla, Amazon, Apple, HP, you name it, that are super cool, and see what possibilities are there for embedded engineering. So we go, search all jobs here, and so you can see here job category. They've got all these different things here. So engineering and information, manufacturing, lots of stuff here. Region, North America, they're just everywhere, right? Location and United States, and then state. We'll just do it in my state since I live here. Texas, all right? And then we can see all these cool mechanical engineering, security systems, process engineer. There's a firmware integration engineer. Another few software engineers, mechanical engineer. It just goes on and on, right? So that's what you want to do. And then, of course, companies, go to Apple if you're interested in doing Apple stuff. Now, me, for example, if I was back in the job market and I was saying to myself, I want to get a cool job, I would say, well, I want to work at a company that builds spacecraft, and I want to work in embedded engineering, designing spacecraft control systems. So now Texas, as you might know, is the home of Houston and Space Center. All the rockets have been launched from here. So there's a big space program, obviously, in Texas, right? So there's a cool company here. Is this it? Firefly? So this is Firefly Aerospace, and so this is a company that makes, space stuff. And so I would go look for a job here. So right here, I go careers, boom, and then we look here and we see here, okay, areas of interest. Let's just go to states real quick. Texas has 19 jobs, boom, okay. And look at this, hardware design engineer, first one right there, Cedar Park, that's like miles from me. Hardware engineer, that's an embedded engineer right there. Avionics systems, senior firmware engineer, right? So right off the top here, right off the top, propulsion technician. So right off the top, I've got a hardware engineer and a senior firmware engineer right there. Let's see if they say how much they're going to pay. Let's see, designing with Vertex FPGAs, and that's another good thing here. If you can see this, designing FPGA firmware targets Kinetics, UltraScale, Vertex. So right now they want FPGA people. So that's why I said you got to learn these different fields and get expertise. So it looks like these people are really, really into people that understand FPGAs and can write in Verilog, right? You need a BS in computer science or electrical engineering or something similar, and 5 years messing around with FPGAs. Now, that's a perfect example of you want to be an embedded engineer, you got to go look at what people are looking for in embedded engineering, right? Okay, let's see. Okay, so that's that. Now let's see what else I want to talk about. Let's see here. Here's something. So now, and then we're going to go back. So now let's say that you're wondering how much people make, right? So I typed in senior electrical engineer, and in the United States of America, it looks like 120 G's a year is a senior electrical engineer. Electrical is 95, senior engineer is 130, electrical designer 90. Now I'm going to tell you right now, these rates they look like they've just dropped, probably worldwide, right? These things all seem really, really low to me, and this is because of COVID and the job market and the amount of unemployment in the United States and everywhere right now is at an all-time high, worse than the Depression, that kind of thing. So these numbers have probably dropped down, but still, nevertheless, they give you an idea. Okay, let's see if we can type in firmware engineer. Let's see what pops up there. Search, and there we go. And there we go, firmware engineer, 110 Gs, 23 openings. All right. And this is a great place if you want to kind of go this route and find jobs, start sending in resumes. This is what you're going to do, right? Okay. Now, these are usually going to be part-time or full-time jobs, right? Same with Monster. Now, Craigslist might be little gigs, but what if you kind of want to do a little one-off you want to start simple. You're like, well, Andre, I don't have a degree. I just kind of want to do electronics. How do I start off simple? Okay, well, there's other options. Let's go back here. So this thing is called Upwork, and Upwork is like Fiverr and all these other online job matching systems. Upwork, though, has a lot of electronics projects on it. From PCB design, power supplies, Arduino things, IoT, motors, toys, you name it. And I filled this thing out a couple years ago because I wanted to see, someone mentioned it and I wanted to check it all out and stuff. The problem for me personally is the rates are just way too low, and the reason why is because this is a global marketplace. So I mean, I bill 125 to 150, really 125 to 250 an hour is what I bill to do embedded engineering, and the average in the United States for a contractor is about $150 an hour. So you can look here, things like, let's see. These just popped up randomly on my thing. I haven't even looked at them here. I'm just trying to find some money here. Well, anyway, this guy, a new product engineer for a new toy game, budget $1,500. I mean, to build or design a new toy or video game takes hundreds of man hours. So you want to pay me what, $1 an hour or something, right? So, but nevertheless, depending on where you live, $500 to you might be a lot of money, and maybe you're not doing anything else, and maybe this is just for experience. So you would tolerate being paid $1,500 to spend 2 months working on a toy, right? Because you want to get some experience. Here's an IoT thing. 1 to 3 months, and let's just take a look at this right here. This is U.S. only, but doesn't really matter. Let's see, what's $60? No, that's not bad. $60 an hour, that's pretty good. $60 an hour, that's not bad. If you're used to making 10 or 12 or 15 or $20 an hour, $60 an hour, that's great, right? So anyway, this is a great site, and this is a great site you basically create a profile for yourself, then you go and do proposals to people, and then see if they bite back. Now the problem is you're getting competed with by people from other countries with different economies, where so say someone puts up a job and maybe you're the best qualified person and maybe overall you're the best person, best price, but they're going to get 50 proposals from 50 people, and it's going to be really hard for them to filter through all of them. So again, you got to really make yourself unique in your proposal. So what I can suggest that you do is write them a proposal that's a paragraph, and then make a video link maybe, and make a video of yourself talking to them. No one does that, right? You do that, make a little video of yourself and explain, say, hi, my name is Andre, and I saw your job proposal on here, and I was really interested in it. I've done something just like this before, and here it is, and I'd like to talk to you about it, whatever. People love video, obviously. You're watching one right now. All right, so Upwork is a really good avenue. Okay, now let's see here. What else is there? Oh, I wanted to talk to you about this. So now, if you are going to go the route where you're going to send out resumes to Firefly and Apple and Amazon and Microsoft and Google and whatever, and you're looking for embedded jobs or electronic jobs, prove that you know something about electronics. So you can make your resume, and then that's a whole other discussion to make resumes good. Please do not listen to what everybody tells you. Resume should be one page and this and that. Make your resume unique, make it colorful, put graphics on it, put images, put links, just make it so that they get 1,000 resumes and they all look the same. My objective is to get a good job at a company and be a good worker. No one wants to hear that. They want to hear someone unique and interesting, right? Because they're just going to throw it away, right? So try and be unique. And I know that goes against everything everyone told you. Anyway, but some people make really cool cards, business cards, that they send with their resumes. Now, I've done this before, and I tell people to do this that want electrical engineering jobs. So I just Googled for credit card, business card, single board computer, and I was able to find this one. So check this out. So this George Hilliard, whoever this is, he's getting free advertising. So he wants a job as an embedded engineer, or that's what he is, and he sends this to people. And check it out. It's an actual business card that runs Linux. It's got a Linux SoC on it, and he runs Linux on it. It's got power and all that. How cool is that? So his business card, he designed a PCB. He got Linux to work. He got it all to work. He manufactured it. He hand assembled it, or had it assembled, and hands it off to people. Do you know Linux? Clearly you do. Do you know PCB design? Clearly you do. So this is a conversation starter, and it's super unique because all I'm going to get is a stack of papers, and I'm not even going to get papers. We're just going to get emails, right? There's nothing even physical. But when you send somebody this, send it in a FedEx or a Priority Mail or a DHL along with your printed resume, right? Someone's going to look at that. That's what you want, right? You want to differentiate yourself from the sea, from the masses, from the noise, because that's what it's all is. Everybody is saying and doing the exact same things. That's why people can't find jobs. You go to school for 4 years, 5 years, 6 years, 7 years, 8 years in college, right? Did you ever take a course on how to get a job? No, I guarantee it. I've got an electrical engineering degree, a mathematics degree, and a computer science degree. Not one of those degrees was there a class called Get a Job. None of them did. Once in a while, maybe a really good teacher would have somebody from industry come in and talk, right? But there was never a whole class on the real way to write resumes, on the real way to hustle, on the real way to use word of mouth and talk to your friends and do all that, right? To get a job. There's just not. So everybody, you graduate from college, you put on your cap and gown, and then all of a sudden you just like, what do I do? You don't know, right? And it's not your fault. You've never been taught. Now it is your fault not to go out and figure it out, right? But it's like anything. You have to be good at it. You have to be good at selling yourself. And here's another thing. I've never worked at a job for more than a few months, maybe a year as a contract, right? So I go from job to job to job to job to make more money into contract, right? I did that starting in my teens and 20s and 30s until I started my own companies. Um, and to do that, you have to be good at selling yourself, which means you have to speak clearly, you have to be articulate, you have to be funny, charismatic, charming, you name it, whatever it is, you got to be able to talk to people and manipulate them, right? At the end of the day, there's all these studies done by Yale and Harvard and Stanford, these psychological studies that say when you do a job interview, whether it's on the phone or in person, you have 20 seconds. In 20 seconds, someone either likes you or dislikes you, not based on your education, right, but based on how you speak, unfortunately, what you look like. So, some more advice if you're going to go for a job interview, please don't be crazy looking. Just kind of tone it down a little bit. Whatever it is you're into, don't be into it. I like bodybuilding and fighting. I'm not going to go in there MMA gear, right? So just tone it down, right? Um, and so you've got about 20 seconds to make that impression, and you got to be careful of it because it's a reality, and that's all there is to it. So, and then after that, after you've made the impression and they're willing to listen, now they start to actually hear you. All right. But it's really important. So that's another important thing about doing interviews. You got to be good at selling yourself, unfortunately. All right, because people are just looking at you pieces of paper. So once you get on that phone for that phone interview, and then these days because of COVID, we're not doing obviously a lot of in person, doing it Zoom at least. But remember, eye contact, body language, sit up straight, all those things. And this is all part of getting a job. So people ask, and I'm telling you. Let's see. Okay, last thing, let's see, is there anything else? So that's about it. So that's kind of my thing on how to get an embedded job. So you got to learn about embedded. You got to do it. You got to make projects, make products, put them on Seed Studio, try them on Kickstarter, try them on crowdfunding. Look for jobs on things like Craigslist. Look for jobs on Upwork. Try and find small jobs so that you build up your portfolio and your experience so you know what you're talking about. And the most important thing is be honest with yourself. Be brutally honest with yourself. As far as I'm concerned, I'm an idiot, right? The more I learn, the more I know nothing, right? A wise man or woman, when you become wise, you realize how much you don't know, right? When you think you know everything, you are not wise, okay? You're ignorant, because if you think you know everything, you're absolutely ignorant. So you just have to constantly be learning and constantly saying to yourself, how do I make myself better than my competitor? And that's what this is. Life, unfortunately, is a competition, right? We're competing for the same jobs, the same resources, the same whatever. You've got to make yourself more attractive, just like an insect and another insect. You got to do whatever you can, be colorful, do a little dance, but you got to do it in the job market. And that's how you get an embedded job. So anyway, I hope you found that entertaining at least. And like I said, a lot of students have asked how I do embedded engineering and how I got jobs and did all that. So I thought that would help. So anyway, Merry Christmas, Happy New Year, and I will see everyone in the next bonus lecture. Bye. Hello, everybody. This is another bonus lecture. And let's see, so this is the beginning of the year. This is January 29th here. And I think the last video I did, last bonus video, was in December of last year, Christmas, so, last month. So it's a new year. Obviously, we had an election, so that's done with, and we've got a kind of a historical point in the United States. We have a women vice president, so that's important. And I have a 6-year-old daughter, so that's a really good thing for her. So I'm pretty excited. Anyway, let's talk about what we're going to do today. So in these bonus videos, obviously we do various kinds of things. We might sometimes do some electronics, we might do some PCB design, we might look at some math or some retro computing things. These are kind of a potpourri. They can be anything. So if you're new to the course and you're just skipping around, these bonus videos can literally be anything that I just feel like doing. I put them all up for free on the course, so you can take them or leave them. So today, what I'd like to do is for Christmas, I got a power-up motorized airplane. And I don't know if you've ever seen these power-up toys, but it's basically you take a paper airplane, you put a motor on it and a battery, and you throw it and it flies. So I saw this product when it came out in 2015. I never got one because I put motors on airplanes, and I'm a big remote control RC person. So I've played with airplanes, helicopters, RC boats, gas, electric, even submarines, quadcopters, you name it. I played with it if it's remote control. But I was thinking this would be kind of a cool electromechanical, a real simple project that's kind of fun and for us to make. So what we're going to do in this video is we're going to kind of take a look at this power-up technology so you can see what I'm talking about, right? If you've never seen this, right now you're like, I have no idea what you're talking about, Andre. So we're going to take a look at that, and then we're going to do this video in 2 parts. Part 1 is we're going to take a look at some of this stuff, and then we're going to go onto the bench, and I'm going to build a paper airplane in front of your eyes, and we'll talk about that. And then I'm going to go out and purchase a bunch of different parts, or purchase more parts, and kind of see what works and what doesn't work. And then we'll come back and have a part 2 next month, where we'll actually build the paper airplane with a motor on it and fly it. All right, so that's kind of the plan. So this lecture, this video, don't buy anything because I'm not sure what I'm going to use, but I'm going to just kind of show you what I'm thinking so you can see my process also. All right, so let's take a look here. So I've got the website up, And so let's see, this whole thing started as a Kickstarter, and let me see if I can find it here. And forgive me, I've got horrible allergies. I live in Austin, and we have cedar trees, and they just dump cedar into the environment. It is horrible. I'm amazed I can breathe right now. Anyway, so hopefully I won't have a sneeze attack. So this is a Power Up 4. So it's called Power Up Paper Airplane, and there was Power Up 1 and 2 and 3 and now 4. And so I can't seem to find 1.0 on Kickstarter anymore, but nevertheless, you can kind of see this has already raised $1.1 million. It's pretty impressive. And so, what is this thing? It's basically a motorized airplane now, and this one's very advanced. This one's got 2 propellers, got a power source, it's got a transceiver, compute, it's wireless, and this one you can steer. So it modulates the power to both of these propellers, which then allows it to basically steer. All right, so pretty impressive. And then I'll just kind of scrub through. Let me see here. I'll just kind of scrub through so you can kind of see. Basically, you get this unit here, this plastic assembly with the 2 propellers, the control unit, and this piece of plastic. And then you put it on anything you want. As long as it's light enough and is aerodynamic and has some lift, it should fly, right? You can fly anything really. And so that's kind of cool. And so you build your paper airplane or balsa wood airplane, whatever, and you kind of stick this thing on there, and then you can fly it around with your cell phone. So that's the whole idea. So obviously we're not going to do something that complicated. We are just going to do motors and power, but just to give you an idea, of what's going on here. And now the other thing is, if you're like me and you've played with a lot of paper airplanes and aircraft and model aircraft made out of paper, balsa wood, or plastic, you know very well that when you throw a paper airplane in anything but the most deadest of wind, it is just going to get hammered and just gets, crash into the ground. It's not going to do much. So some of these videos and some of the examples, like when you see real people play with paper airplanes with a motor attached and they try and take it outside, the paper airplane just falls and hits the ground, which is exactly what's going to happen. So when you do play with paper airplanes, it's best to do it in complete dead silence, no wind at all, indoor, ideally if you can. So there's no winds, no gusts, no nothing. So that you have control. And I would also say kind of the same thing when you're playing with the motorized version. Anyway, so let's see here, and it's got 2 propellers, and then you can make it out of different materials. Just kind of talking about it. This is a really huge Kickstarter, and then there's some lighting stuff they've added to it, landing gear. They're just going crazy with it on this 4th version, kind of showing you one built out of balsa. And these motors are very, very powerful. These little tiny motors, which I'm going to show you, they definitely are powerful. So you can get a lot of things up in the air. But like anything, it's hard to kind of work with paper. So we're going to talk about the kind of papers that you should use to make paper airplanes and make something so that you have a platform to put the motors on. We're going to talk about purchasing the motors. And again, I haven't even really looked at this whole thing myself. I'm just kind of scrolling through, and it's a great project for kids. If some of you are adults and have children, you want to play with something with your children. All right, this is a great project that we can do. You can always get a power up yourself, but this might be something fun. And this is just showing all the different specs and rewards and all that kind of Kickstarter stuff. Okay, so anyway, that's on Kickstarter, just to kind of show you the where this came from, right? And like I said, this is not new. People have been putting motors on airplanes for, I don't know, probably 50, 60 years. So anyway, I'm talking about toy airplanes, obviously since the invention of the airplane, right? It's been, 100 years. But just even with toy airplanes, they've been around for decades and decades. So not a new thing. Okay, if you go to the website, it's poweruptoys.com. And again, you can kind of look through here and you kind of see the different things that they have. So what I did was I bought, and I'll show it to you once we go on the bench. I think I didn't buy it. I got this for Christmas. So I have this kit right here, this Power Up 4. And so it basically comes with the Power Up, then it comes with a bunch of, let me see if we can kind of open this up. You'll be able to see it here pretty good. Yeah, so comes with a kit and comes with a bunch of pieces of paper with pre-drawn airplanes on them with artwork and so forth, some plastic assemblies so you can put it on a stand, this and that. And then, here's the entire thing really. So basically you got two motors, a couple extra propellers. This is all made of plastic. Then you've got a wireless module here. Something, you could do this with an ESP32, for example. This is where the power is, and then the signals are sent back to control the two motors. So there's no control surfaces on these things. It's just modulating the power to each one of these motors, which creates torque and rotation so the plane can change direction. So that's really about it. So that's kind of the idea. So let's make something like this, right? So where do we even begin to kind of do this? So really, we need a motor, we need a propeller, and we're not going to do anything wireless. We just need a battery. So we're going to do something like the very first one of this product, which I think I have a video of it here. Yes. So this is the very first one. I don't know if you can even still buy this, but I was able to find a video of it. And so here's some guy, and he's bought one of these power-up planes. And so, there's kind of the packaging, and he kind of cracks it open here. And you can see it's basically just a motor mounted on a piece of plastic, then a plastic rod, all right? And this might actually be metal with plastic around it, I'm not sure. And then here's the battery. So basically just a lithium-ion battery. There's some more plastic. And then this is a little charger right here. And so all this is you charge this up, or I think you put batteries in it, then you can kind of plug it into this unit here and charge the system. That's it. That's it. And some paper. That's all this thing was, right? So, anyway, so you get it, and let's see if he takes it apart here. Yeah, so he takes it apart, and he's, got the paper, and he's going to kind of read through the instructions here. All right, put the paper airplane together, put some batteries inside of here, and then you're going to tape this thing together. Cool. And then kind of show you this. And that's really all there is to it, not much to it. So we're going to have to mount our motor onto something, so I'm going to have to do some 3D printing. So I'm going to do some design in 3D printing so we have something to mount our motor on. And when I'm done, I will provide you with the STL files if you want to print your own. Right, we're going to need to do that, so we'll do some SolidWorks kind of work and use my Prusa 3D printer to print some stuff out. All right, and then let's see here what else. He's just talking there, and I think he's going to show charging this one. Yeah. So, and then all you do, and this is kind of designed for kids, so this kind of is to charge it up, all right, and that's it. So it's running, so you can see it there, and it's blowing, a lot of wind there, and that's it. And this paper that he's using here, I'm not sure how many pounds that is. Now there they are flying it, and you can see it just basically goes and hits the ground, all right, and and then he's trying, maybe I'll throw it harder, and it just hits the ground. So when you do this, so if you had a little, if you had a little kid or girl or boy, and you got this kit for him, and then you went out and threw it, you'd be kind of disappointed, right? That's not a whole lot of fun. So like I said, you got to really kind of do this in a very, very quiet area, indoor ideally, so that there's no wind at all. You can't just take these things outside; they just won't work. So anyway, let's see if he gets one good flight. Maybe a little bit. So anyway, so that's kind of that, all right? And then we move up, and then here's kind of the number 4, and going through here, talking about it, linking it up to your phone. This has Wi-Fi, and then it's got an accelerometer inside of it so that this thing can tell what's going on, and then it uses the phone itself. So as you move the phone and the accelerometer and gyro, it sends that information to the plane, and then the plane then can adjust the two motor thrusts. All right, so pretty cool. All right, and just talking about all that, and then again building it here. All right, and then here's this little, this is kind of a cool little thing. So this little rotating piece right here is kind of a good idea for stability, so that you can put some rigidity across this. Now again, if you built a lot of paper airplanes or model airplanes or gliders, powered airplanes like I have, or just made a lot of paper airplanes, you know that rigidity is important, and sometimes as you're building these things, you can kind of put something so that you get some strength. And then also you notice how he just moved it up and down so they can change where the center of gravity is also. So that's kind of a cool thing. That's another thing when you think when you put a motor on here and when you put a battery on here, we're going to have weight, and we've got to make sure that we weigh this thing up and down so that the center of gravity is where the center of gravity should be, so it'll fly. So there's going to be some playing around. So anyway, So there's that, and let's see if he goes and flies it here. And now this will probably fly a lot better. Just saying, don't play by power lines. Okay, so here we go here. And so now, in this case, I think he just is throwing it just to kind of get the hang of the airplane. So, you know, before you have power, just throw it and see how it works. All right, and here we go. I think they're going to fly it here so you can see this. And let me just turn this up. So he's just using the phone, right? And that's how he's steering. He's just moving the phone around, and the gyro and accelerometer in the phone is used to control the airplane. So you can see this flies pretty good. And notice how tail heavy it is. So the tail is really sagging and sinking. So it's always climbing up into the air. All right. So that's kind of another key thing, so it doesn't nosedive, because these are heavy parts. I mean, this is really heavy. This Wi-Fi module is heavy, and this is heavy also. So it just goes to show you enough thrust. If you have just a little lift, you can fly anything. All right. So that's basically what we're going to build. All right, so let's take a look real quick here. Let's go here. So all we really have to do is we are going to need to, let's get something that represents our motor. All right, so let's maybe get kind of this gray here. All right, so we're going to have a motor here. Okay, real simple. This is going to be a standard DC brushed motor. All right, and we're going to get something that runs around 3.0 volts, okay, in that range right there. And the reason why is we just want to use a standard lithium-ion battery. One lithium-ion battery, and a lithium-ion battery kind of loaded, you know, is about 3.7 volts, 3.6 volts, roughly, once you start discharging it. So we want to just use, you know, a LiPo battery, a teeny tiny LiPo battery. All right, so that's what we're going to, you know, have for thrust. And then, of course, we're just going to have the single propeller here, you know, connecting in with a shaft. And on this part right here, we're going to be using kind of something very, very small. So the diameter of this motor, right, we're going to try and find diameters kind of in the range of approximately 6 to 8 millimeters. All right, so that's kind of what we want the diameter to be, because we want some small motors. We don't care too much how big these are, how long they are. Typically, there's something from, you know, 15 to 20 millimeters. All right, but that's kind of on the size range that we want. And then another thing that's going to be important is on these shafts. These shafts are typically, we want to look for something that's going to be 0.8 to 1.0 millimeter shaft diameter. And we'll just call that DS for diameter shaft. All right, and so we need a shaft diameter that's 0.8 to 1.0, which means, of course, the propeller has to also have the exact same hole in it so that they will fit, right, and couple together. And now there's a couple other things on these motors. Obviously, they've got some of them prefer, and let me just use green here. I use green. So all right, so this is, we'll just call this the minus side, and then we'll just call this the plus side. All right. And some of these motors prefer to be ran in one direction. So they really do want plus to go on one side, minus to go on the other side, but you can run them in the opposite direction. A lot of times the bearings just don't like that, and it'll make like a whining sound, right? But either way, we're not making a product to manufacture and sell, so we can run the motor either way, and it just is probably going to run better in one direction or the other. However, what that means is depending on the geometry of the propeller, right? When you run this thing one way or the other, you're either going to get thrust in one direction or the other direction, right? And if you know anything about quadcopters or drones or whatnot, you know that we have clockwise and counterclockwise rotors or propellers. And so depending on which way they're going, thrust will go in one direction or the other, right? It'll blow wind in one direction or the other. The blades are cut. Their angle is in such a way that if they're going clockwise, they'll blow wind in one direction. If they're counterclockwise, then they'll blow wind in the other direction, create thrust in either direction. Point is, if you turn the DC motor on as it should, and you apply your 3.0 volts here, or whatever, 3.6 volts, 3.7 volts LiPo battery, and the thing is thrusting in the wrong direction with the propeller that you got, then you really have only two courses of action. One, you can switch the power around, which is fine, or you can get the opposite kind of propeller. You can get a clockwise or counterclockwise, respectively. So when we order these, we're just going to try and get clockwise and counterclockwise from the same maker manufacturer, so we have both options, so we can kind of play with that. All right? Okay. Now, so what's next? So really, this is a really simple circuit. All right, so we've got our motor, and then all we're going to do is we're just going to literally take two wires here, boom, boom, okay? And then we might want to, if we have a little space, we'll put a little switch. We'll call this S1. Let's call this M1 for motor 1. All right, switch 1, and then we're going to come down here and we're going to come down to our LiPo battery. All right, right now I'll just put it kind of in the correct orientation here that it should be, like this. All right, and we'll just call this B1. All right, and that's plus and that's minus, and this is approximately 3.7 volts LiPo. All right, and the kind of size that we're talking about here is something along the magnitude of 50 to 100 milliamps. Okay, 50 to 100 milliamp hour battery. That's it. That's all we can tolerate, because we actually want it to be pretty small. So when we get this battery, really what you're kind of looking for is something, these batteries are prismatic shape, right? So they're big rectangular solids, right? So we're kind of looking for something we could think has got to fit in this airplane somehow, right? And whatever the thickness is of the battery, one of those dimensions can kind of have to fit someplace in it. So we kind of want to make one of these dimensions really thin. So if you look around, the smallest you can kind of find, you can find batteries that are thinner than 3.0 millimeters. But I'm going to kind of find stuff that's in the 3.0 millimeter range. So I have one dimension at least that's really thin, right? And then the other two dimensions I don't care so much about, but no matter what, that's going to have to somehow go into our little plastic assembly or something to hold it, right? Okay, so this is basically it. We close the switch, boom, then we're going to get current flow, and boom, boom, through here, and the motor's going to turn on. That's it. It's just going to turn on full blast. That's it. We'll just let it go max out and throttle. Now, if you wanted to have some kind of control in here, you could put a for example, you could put a diode in here if you want, right? You could put a diode and drop 0.3 volts, maybe a Schottky diode, 0.2 volts, or you can put a silicon diode in there and drop 0.6, 0.7 volts if you want to drop the voltage down a little bit to just decrease the thrust. So, or you could put resistors in there if you want to just burn heat. Either way, this is all we got to do. So this is fairly simple, but no matter what, we've got some technical challenges, because we've got to we're going to have to build some kind of housing around the motor to hold it. Then we're going to need some kind of long kind of structure, right, made out of plastic or metal, right? And then that's going to go the length of the airplane. And then this is going to have to be semi-adjustable for different length airplanes, right? And then we're going to need some kind of platform just to hold our battery, right? And then also we want something that we can slide around, right? So we're going to want something that kind of goes over this, that maybe has a little bit of weight, that little structure that we saw that kind of held things, created rigidity, that we can kind of slide back and forth. So there'll be some mechanical stuff. So on the next lecture, I'll talk about those designs, and when I show you the SolidWorks models that I create and objects that I print to kind of do this. But at the very simplest thing, if you wanted to, you could literally take the motor, you could tape that thing to a paper clip outstretched or a long piece of metal. You could tape the battery to the other end of the piece of metal. Then you could connect the wires, and then you could tape the entire thing to your plane and just throw it, right? So you don't have to do all this 3D printing and stuff. Or you can just use, there's a lot to be said. You can just get ballpoint pens, you can get things around, Legos, all kinds of things, drill holes, cut, fabricate. You don't need a 3D printer to do this. You can just kind of use stuff. So you got to be creative. So this is going to kind of be a fun project, all right? So that is kind of what I wanted to show you. And then before we go onto the bench, what I want to do is I want to show you some of the parts. Now again, we're going to pick final parts after I built this thing. But right now, I just want to kind of get you thinking about it. So here are some of the motors. So the motors that I like are these 6 millimeter diameter, 15 millimeter length motors. And so you can see here they are right here. And I think, yeah, so if we look at this, you can see the shaft is 0.8 millimeters, it's 15 long, 6 millimeters, and then it's got a wire connected to it. These happen to have these micro JST connectors, these Japanese connectors. And 1.25 means the pitch between the pins. So we're going to need to either cut this off or get some connectors that we can connect to this, males and females, as we play around with this, right? So that's another thing we'll need to get to make things easy, so we can use these connectors and disconnect it. So it might be, so we might have the motor and the battery, and it might be instead of using a switch, we just connect the connector, the motor will turn on, the battery powered, and then we can throw it, and then we can just disconnect it rather than putting a switch, right? Okay, and then it shows you kind of, you could put them in this quadcopter, for example, another picture anyway, and yeah, that's about it. So anyway, these are the kind of motors that we're going to need, all right? Now, then these are the kind of propellers that we're going to need, all right? So these little propellers for the ducted fans and drones work great, and you can see the different properties of them and features. So the center hole is 0.8 millimeters. So this is exactly what we need, 0.8. So some of them are 0.8, some from 1.0. So you kind of maybe get both different sizes and play around. And then the prop diameter is 31 millimeters. We don't want to go much bigger than 31 millimeters. I have some over here. I think at 40 millimeters is about the limit for the diameter of the prop. And let's see here. Yeah, and then this particular model, and then you can see there's where the dimension is, right? 31 across and then 0.8 for the hole. And that's going to go into the shaft of the motor. But you can also see that they come with clockwise and counterclockwise. And that's what we want. We want both clockwise and counterclockwise. So if we want to turn the motor in one direction or the other and get it to work the best so that there's the least amount of friction, then we can do that. So it pays to have both different versions of these props. Okay. And again, don't buy anything yet. This is just part one, is just looking at it. And then, we're going to start looking through these batteries. So you can see here's a really small one right here. So that's 12 millimeters in that direction, 10 millimeters in that direction, and 3 millimeters in that direction. So I actually bought a couple of these, and these are really small. This is 50 milliamp hours. So this will power our plane for at least I'm going to say these motors probably draw. We could find the draw on here. We'd have to look someplace and see what the actual current draw is. But let's just say, let's say it's 100. Let's say it's 100 milliamp hours, right? 100 milliamp hours, right? So that means that this 50 milliamp hour battery would work for 30 minutes, right? So anyway, that just gives you an idea. And then in reality, cut that in half. So maybe it'll fly for 15 minutes, something like that, right? And of course, it'll crash far earlier than that. Okay, and then the last thing is we need some paper to make these things out of. And so what I like to use is this bright kind of construction paper, and we need it to be heavy. It's got to be cardstock paper. Now, in the United States, we measure things with pounds, and so like so many pounds of paper, they take a certain amount of paper, and then it weighs so much, and that's it. And then there's these other there's another measurement also, not this GSM, but there's another measurement also, which I can't remember. But anyway, 65 is about the limit. So I say about 50 to 65 pound paper is kind of where you want to be. Anything greater than 65 is just too thick to fold, and anything kind of less than 50 pound is just too thin. I mean, the airplanes that come with the power-up kit that I have actually does have I think it's like 24-pound paper. It's just real flimsy to me. So I just prefer something thicker. But anyway, that gives you an idea, and that way you have a bunch of different colors to play with. So that's it. We're going to need motors, propellers, we're going to need connectors, we're going to need batteries, we're going to need paper to build this thing. So these are kind of all, this is my process, right? And a lot of people say, how do you build embedded systems or a product? Someone approached me about designing something like this. This is what I would start with. I'd start getting pieces and parts and start putting it together. Okay, let's go We're about 25 minutes into this, so that's good. Let's go over to the bench, and on the bench we are going to go ahead and build an airplane for fun, fold an airplane. I'll talk about some of that, and just so you can kind of see the process, that it's not impossible, and we'll go from there. All right, so I'll meet you on the bench. Okay, everyone, let's take a look at some of the stuff that we have here. So first, let's see. So I've actually purchased some of those parts that we just saw on the list. All right. So I'm going to kind of show you some of those things. All right. So let's take a look at the propellers. And again, I'm going to probably get some other ones. But here's these guys right here, and that's what they look like. And then they've got their tiny little 0.8 millimeter holes in there. Now I believe these are all. This particular brand is all clockwise. There's a little, oh, that's kind of cool. That's to get the propeller off, the prop off. All right, so now let's take a look at the motors. All right, so these I believe are 1 millimeter shaft. These I believe are 1 millimeter shaft. So now here's the some motors here, and they kind of all stick together, right? And then here's one of these motors right here. And then if we try and put this inside here like this, what we will find, and let me zoom in just a little bit here, just a little bit. Just a teeny tiny. All right. So if we try and put this inside of here, oops, what we're going to find is it will go inside, but then it just kind of, it's not connecting, it's loose. The reason why is this is 0.8 millimeter shaft diameter, and then this is a 1 millimeter prop. So now if we bust out the calipers here, let's just kind of confirm. Can you guys see that? All right. Yeah, so you can see 0.79. All right. And then there's really no way for me to look inside there, but I guarantee that's what's going on. All right. So anyway, that's important. Now we can actually make that fit, and we're going to make it fit. So we'll put a little piece of wire in here so we can test it, and I'll actually use a piece of wire to create some like a spacer, and we'll press it on there. So I'll show you that in a second. And then some of the other things, and then let me show you this. And again, this is really important. Now, when you're going to build something, anything you're going to build, you're going to have to buy stuff and play around with it and experiment. And when it comes to electronics, it's not like you need to buy 20 different 1 microfarad capacitors. You just buy 1 microfarad capacitors with certain specs. But when it comes to mechanical things, you have got to buy a lot of stuff. Now, I'll be honest with you, when I build a project that has mechanical aspects to it, and there's a lot of fabrication, like a toy or something, I might spend $10, $20, even $30,000 I've been known to spend purchasing just parts and things to build and experiment with that toy. All right. Now you can see here, this is a huge difference, these two motor sizes. So this is a big motor, right? Now if we look at that, I think this is 10 millimeters. Actually, it's like, maybe 8.5. So that just goes to show you, that's 8.5, right? And I mean, that is huge compared to this other one, which is 6. So it just goes to show you, you might say, oh, a couple millimeters, no big deal. But when you actually hold these things in your hand, you're like, wow, that is way, 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 way bigger. That's just not going to work. And that's why you have to buy things and touch them when you're doing mechanical, because your perception is so different than what you think. 2 millimeters, oh, that's nothing, but it is. It's huge. Okay, what else we have here? Let's see. So those are some motors. Those are motors. Let's keep those all out right there for now. We'll keep another prop there too. So here's some of these connectors. Here's these JST connectors. I believe these are 2 millimeter. Let's see, upgraded, can't tell. We could measure it though. But I believe these are 2 millimeter JST female. All right, and then I've got some JST, some more male and female. As a matter of fact, I think I have one, right here. So now, if we take a look at these motors, let's grab this little guy right here. So if we look at this tiny little connector right there, there's that JST connector, right? And then here is one of these connectors that I got so we can connect it together, and we don't have to solder everything ourselves. And then we're basically just going to pop that together like that, and then push it together, and then now we have these wires which we could solder onto something else. But this way we have a connector that we can go back and forth. So it just makes things cleaner, all right? So there's that. Let's see, is there anything else fun? And again, just some show and tell. All right, here's that battery, one of those batteries that I got. Teeny tiny battery. And then this one's actually got, it looks like, let me just take a quick peek here. So this battery looks like it's a 2.5 millimeter pitch. And to tell you the truth, the difference between 2 and 2.5 is, yeah, I think this is 2. So, if it's 2 or 2.5, you can usually kind of, mash them together. The bigger one obviously will fit a little bit better if it's a shroud around there. But the bottom line is we have to make sure these connectors are all the right size. So we might have to cut things off or do whatever. But this battery right here, let me just take this out. And of course, I have no nails, so it's always hard for me. There we go. It's always hard for me to get things. All right, so that's going to work really good. I like that because that can go right in a paper airplane, right? So that's good. Okay, so let's do a quick electrical test, all right, to kind of show you what's going on here. All right, so I just want to show you how powerful this thing is. All right, now, so first what I did to get this propeller on here, so it would stay, is, oh, and it looks like it wants to fly off too. So what I did is I took some wire wrap wire and I actually put it down the shaft, and then I pressed the inner shaft into it and then cut the wire off so that it's tight. So I mean, it's pretty tight right now. Now, I wouldn't trust it for very long. It'll probably spin off. But anyway, it's pretty tight. So now we've got this connector here like this, and then let's go ahead and we will connect this on here like so. All right, mash those together, good. And then there are two connectors, all right? So now when I connect this up, one way it's gonna blow wind, create thrust in this direction, and the other, it'll create thrust in this direction. So I can't remember which one, so I'll just go red to red, black to black, and pray. Otherwise, you're gonna have to switch it. Now, another thing, everybody, please respect these little propellers. I know this thing looks tiny, but believe me, when it's going 15,000 RPMs, this is sharp. I mean, when it's going 15,000 RPMs, if you put that on your finger, it'll cut your finger. It'll definitely cut, and draw blood. This is not from that. That's from some other project. But respect these things and keep your fingers out of the way so you don't hurt yourself, especially if you have children that are going to play with this. All right. So what my plan is, I'm going to hold this. I've got 3 volts on my power supply. I'm just going to hold it, and I'm going to power this up. And I'm going to hold on to this thing for dear life because it's going to create a little bit of torque. It's going to move fast. All right. All right, that's moving fast. All right, and it's thrusting in the wrong direction. So the thrust is actually coming down towards my hand. Let me see if I can get a little piece of paper. Yeah. You can see it's blowing the paper down. All right, so let's just switch it. Let's switch it real quick. We'll go red to black, black to red. I think that's what I want to do, right? Okay. Now, I don't know if you noticed, but it's making a different quality of sound, and that's because we're running it backwards. So the bearings are running a little bit different, and there's pressure on the shaft in a different direction. But anyway, this is blowing this thing will definitely fly. I mean, look at that blow the paper. It's blowing the paper all the way back. All right, so that's cool. That's a lot of thrust. All right, and I'm pulling, so that's pulling 800 milliamps right now. All right, so that's pulling a good amount of current right there, right? 800 milliamps. So our little 50 milliamp hour is not going to last very long, a couple minutes if that. All right. So anyway, but that's our motor. So we're going to mount that somehow and get that going. All right. And then, like I said, we might want to put a little switch in there somehow, or we might want to just use the connector. I don't know. Okay. So now let's go ahead and look at some other stuff here. So what I want to do is I'm going to, just for fun, I'm going to build this paper airplane in front of you right now. Okay, so, all right. Now, we're doing, electronics, electrical engineering, embedded engineering. One of the most important things is being really, really good with your hands. You have to be, okay? You're playing with electronics and stuff, and depending on what products you make, you may be assembling really small things. So it's really good to get good using your hands to build things, because you're going to be using a lot of tools, as you take the course, if you've already taken the whole course, you know all the kinds of crazy tools that we use. But if you haven't, if you're just skipping around, then this is something that's very useful. It's building things. Now, let me give you a little anecdotal information. So like I said, I've been playing with remote control everything my entire life since I was a little boy, and I've always liked it. But when I was in junior high school, I held the records for paper airplane and balsa wood plane contests, meaning I could make a paper airplane or a balsa plane that would fly the longest. Now, it's been a long time since then, and it's a little bit hard to remember, but I believe my record was on the order of 30 seconds, meaning I could throw a paper airplane and it would stay in the air like 30 seconds that I had made. That's a long time. Believe me, 30 seconds is an eternity for an airplane. Anyway, so I like making paper airplanes. Now, another thing also, I'm a mathematician, and there's a whole field of study, or you've heard of origami, paper folding, right? Japanese origami. But there's a whole field of study using paper and paper folding to do mathematical calculations. So, for example, when you fold a piece of paper, you just cut something in half. If you fold that again, you've cut it into quarters. So you can use paper to actually do design and do computation in parallel. And there's a lot of people that do designs that their names escape me at the moment. But there's for example, a space designer, a space engineer who designs structures, and I believe he designed the one of the space stations, a lot of the structure of the space station, the International Space Station, and he did it through paper folding. He would sit and fold paper to figure out these extremely complex mechanical problems and how things should fold and unfold in real time so that you could have unfolding solar panels and all that. So it's not just for kids. Paper folding is a very, very complex field of study. All right, that said, if you know anything about paper airplanes, I think you can see this is a pretty cool looking paper airplane. This is one of the favorites that I make, and it's inspired by the movie Firefox. Firefox 1979, Clint Eastwood, one of my favorite movies. He steals a Russian MiG, and it's got thought control, and it's super awesome. And Firefox kind of had this kind of delta wing configuration. It had canards up here. It had all kinds of control surfaces. It actually had two vertical stabilizers. Anyway, so this is one of the favorite planes that I make, and it flies really, really well, actually. It's very stable, and you can play a lot with it, and it looks good and flies good. So I'm going to show you how to make that. Now, to make it, we are going to use some paper here. All right, so now, like I said, here is, so I actually bought some of that Astro Bright paper cardstock, and this one right here is, it should say, a 65 pound. Can you see that? Yeah, 65 pound. And it comes with all these different colors. Now I also have, this is normal, I believe this is about 24 pound. And this is my daughter's construction paper. She'll kill me if she sees me use even one piece of it, but we'll steal one. And I think the highest contrast will probably be orange, but you can see this is really flimsy, okay? So that's really flimsy. That's 24 pound, I believe. And let me show you a 65 pound. I have a white one. All right, so obviously here's the plane. It's just very, very rigid. But here, this is 65 pound. That's what I made this out of, right? But it's a lot harder to fold, so we'll just do it with the 24 in front of you, okay? All right, so you can slow down, you can do this in lots of ways. All right, so let's go ahead and let's just fold ourselves a cool airplane, all right? And I'm gonna need some scissors. Let me grab some. Okay, all right, so we have some cool scissors here, and let's just make a paper airplane. Okay, so like I said, paper folding is a lot of fun, and it takes some time to get good at it. But there are just a couple rules as you're doing it that it will help build it, just like anything. You know, if you're going to do any kind of construction or fabrication, keep it clean, keep edges straight, don't be sloppy, don't be messy, don't be lazy. End of story. You got to do those things. All right, so let's go ahead. And the first thing that we're going to do, and I'll tell you another thing, I've been making paper airplanes my whole life, and when I look at the instructions to make a paper airplane from a book, it's really hard to follow when you're seeing pages being turned and all. It's really hard. So don't beat yourself up if you try and start doing a paper airplane from some instructions. You can't figure it out because it's not that easy. You really need to see video. Okay, so this is 8.5 by 11 paper. So we're going to go ahead and we're going to take it lengthwise and we're just going to fold it in half. Okay, we're just going to fold it in half. That's the first step. All right, and then the first thing I'm going to always do is I'm going to kind of get these things lined up. All right, and then we're going to kind of break this over. All right, and then, you know, the whole point is we want to get this thing to perfectly line up top and bottom. All right, so I'm going to take off. I always wear glasses because I'm looking at another screen, so I'm going to take those off because I don't need to see. All right, and now here's the key. So now I've got it, I'm ready, so I'm holding it here, and I'm going to kind of go out, and then I'm going to create this razor sharp edge, right? And that's kind of what you want to do. You want to create a nice edge, and so you have something that's nice and equal. And then, you know, go back and forth and look at it, and it may be perfect or not, all right? It's not got to be exacted, all right? It's not brain surgery. Okay, then we're going to go ahead and we're going to fold both of these over to the midsection here, this bisection line, all right? Now, here's where I wish I had more light. It looks like there's a lot of light here, but I actually have to have the lights down, so it's kind of hard to find the exact center. So I'm going to just kind of eyeball it, and then angles matter. So again, we're going to go like that, and then we're going to get it here, and then nice straight hard lines, okay? And then we're going to do the same thing right here, all right? Okay, all right, okay, cool. All right, I'm happy with this so far. And you know, when you're making these paper airplanes, one mistake, one little angle off, and it kind of propagates through the entire thing. So right now we're okay. So we're good. Okay, so this is all we got right here. Okay, now what's the next thing we're going to do? Now we're going to fold again both sides. So we're going to take one side here, and I'm just going to fold it right to the center line. Okay, right to the center line. All right. So I'm going to fold it to the center line, and I'm always paying attention to here and to here, right? I don't want this overlapping in the wrong direction like that. I want it exactly straight and here. And again, this is extremely bright paper, and so even with this 24 pound paper, it's not that easy to make. Once you fold it a couple times, this gets pretty hard to work with. So you can imagine the 65 pound cardstock. Now I'm going to fold this one over, okay? All right. Folding it over. Okay, so that's good. See how that's meeting right there? That's good. Okay, now let's go look at the other end before we talk. Let's see how that is. All right, and again, you got to kind of work it here. And again, it's not got to be perfect. Close. All right, and then again, once I feel good about it, boom. And now what we're trying to look at here also is see where that hits there and that hits there. That should be the exact same, right? If everything's symmetrical. All right, then I'm going to go over here. All right. Okay. And that overlapped a little bit, so I'm going to just back it off. And that, you know, sometimes you have to do this a couple times. And with 36,000 students, I'm sure we have some paper airplane experts that are really, really good at this and have all kinds of tips for us. But we will, for now, just build this one this way. There we go. Okay. There we go. Good enough. Okay. Trying to keep this in camera. Okay, so there we go. So now we have our basic delta wing configuration. All right, so now we're going to go one more fold. So now we're just going to fold this in half and we're going to match this, meet this all up. So that's what we're going to do now. So now I'm going to, you know, kind of play with this and get it to meet up. All right. I'm going to do some twisting, and you need to have really dry hands for this, but they have to have a little bit of moisture so you can kind of grab the paper and kind of put it between your fingers. So just in a little thing. So your hands can't be wet, but they can't be too dry. All right. All right. I think I'm happy with that. This is not too bad over here. Okay, so now I'm going to really hammer it down and create that seam. Okay, so now what we have is this. All right. Cool. Okay, so now we've got you know, the basic shape here. Now here's where you kind of do whatever you want. So now we're going to fold this over. Now we can fold it like that. We can fold it like that. We can fold it like that. It really depends on, you know, what you want to do here. All right. So typically I keep this kind of straight and I kind of pull it down. All right. And you're going to have to play with this to kind of figure out what looks good to you. All right. And then whatever you do with one, now we're going to turn it over and we're going to do it with the other one. and we just got to copy it. So everything's mirrored. All right, and we're going to really see error. So now, like I said, these errors propagate. So we want to make sure this front end hits in the exact same spot. All right, so it's symmetrical. All right, that's pretty good. And again, don't burn yourself, everybody. All right, don't burn yourself. When you do this, you can get a paper burn or a paper cut. Ouch. Okay. Okay. All right. Now, okay, so that looks pretty cool. So that's it. So now, this is maybe something you've seen out, how are we going to get to that from that? All right, so let's keep working. Okay, so now the next thing that we want to do here is let's go ahead and let's put the kind of vertical stabilizer, right? So let's do that. So what we're going to do there is we're just actually going to cut. Now, we're going to cut a line here, right? And you got to think about things being inverted. So I'm going to cut a line here, and then I'm going to pull this up. All right, so I'm just going to pick a line. Now, if I cut it this way, that would be backwards. So be careful, everybody, or you'll mess this up. So I'm going to make it about this big. All right, about this big, and I'm going to put that angle on it. Okay, so I just put a cut just like that. Now, check it out. I'm just going to open it. I'm just going to push this through like this, fold it again, and then refold all this. And then I'm going to bend this down a little bit here. I'm going to bend this down a little bit here. All right, now check it out. There we go. Boom. Okay, now let's get those little vertical stabilizers, the little ones that are on each one of these sides, these tiplets. All right, so again, you can kind of pick wherever you want to go. Depends how much surface area you want to use. All right, so I'm just going to kind of go like this. All right, and then I got to do this one the same. And again, I'm looking here and I'm trying to match here. So it's about the same size. All right, everything we're trying to do symmetrical. We could measure everything out, and of course we can make a template. We could draw on here and make an exact template. That's just going to create a more stable flight. Okay, that's good. All right, now let's see. Let's go ahead and let's put some front canards on here. So again, we can kind of put these wherever we want. All right, so kind of pick a spot here, how far you want to go back, right? How crazy you want to go, and then you can kind of pick where you want to put them. All right. Now, there's you can kind of cut these either way and then fold the paper. All right, so it doesn't really matter. You can kind of cut them either way and then fold the paper. So we can cut them this way or we can cut them this way. All right, but I'm gonna go ahead and I'm gonna cut them. I'm gonna cut them straight in this case. So I'm gonna do them about here. So I'm gonna literally. You guys see that? Yep. I'm going to cut right through here. Be careful. Don't cut too much. Okay. I'm going to cut there. And you can rip these with your fingers. Like if I'm doing this and I'm making a paper airplane at a, in a moving car, I'll just kind of do things with my fingers. But that's that. Okay. So now we have those two cuts right there. So then all I'm going to do is go like that. Now see, there it is. So I've got that. All right. So we're done with that. And then what do we do with this? We just fold these over. Fold them under. All right, we fold these under out of the way, and again, make them symmetrical. All right, so all I did was fold those under. They're just under there, right? And again, we just flatten them all out. Okay, so now let's take our whole plane here, and let's kind of straighten it out. Okay, let's look at it. That looks good. That looks good. Twist, twist. That looks good. Get a whole view. Okay, now what else? All right, let's see here. So now we're starting to take a look here. You can see our two planes are looking very, very similar. Cool. Now the last thing that we want to do is create some elevators right here. So you create elevators here, right? And those elevators allow this to pull up or pull down or to twist, right? So again, we gotta kind of pick where we want to put them here. All right. So I'm going to kind of go about a ½ inch off. And I'm going to make it about 3/4 of an inch, and I'm really eyeballing at this point. So I'm going to go like this. So there's that elevator right there, and then I'm just going to do the same thing right here. All right, holding my breath a little bit. Okay, and right about there. All right, and we'll put that flat, and then we'll just put those back into the line of the plane, and then you can play with those elevators to get it to twist or turn. All right, so let's back out. And there it is. Okay, so that is it. Let's go back to our drawing here. So this is what we need to do electrically. We've taken care of what we're going to do mechanically. So my homework is to test these parts, the propeller, the motor, the battery, do some 3D modeling, kind of model up what we're going to do to put this thing together and kind of snap it together, do some testing. We're going to use that plane that I just made. I like that plane, so we're going to kind of stick to something like that. Of course, you can do whatever you want. And then in part 2 of this bonus lecture, we'll go ahead and put the whole thing together. We'll take it outside and try and fly it someplace really with calm air, or maybe I'll find something indoor. Maybe I can find a basketball court, an indoor basketball court or something like that at night that I can take it into and put up a tripod and throw it so you guys can see it. So anyway, I hope you guys, I hope everyone liked that. And, you know, I thought just something a little bit different, a little mechanical. So I will see you all next time when we do part 2 of this. Hopefully in a month for the next bonus video, I'll have it all done and all working. All right. Until then, have a good one, and I will see you later. Bye. Hey everybody, how are you doing? Today I thought we would look at an online tool. So a lot of students obviously know that I'm working on another course right now, an Arduino embedded microcontroller course. And that's getting to the point where I'm going to start recording videos for that. Anyway, in the meantime, you know, I'm playing with lots of different tools and kind of experimenting with how I want to present the course. And a tool, I may have mentioned it before in the electronics class, so if you've gone through all the lectures in this course, then I may have mentioned it. I may have even shown it to you. But if I haven't, there's a tool called Tinkercad, and it's one of these online tools. It's not very powerful. It's free, and you know, it's not something you want to use professionally, but it actually is, you know, kind of cool. So let's just take a look at it. And what this tool allows you to do, so this is by Autodesk, and Autodesk is a big CAD manufacturer. They make a lot of different CAD applications. And Tinkercad is kind of a tool that lets you play with both doing 3D modeling and doing electronics. So you just go to tinkercad.com and you just sign up for it. All right, it's free. So let's just close this thing here, and we're going to do join now. And if you're in school, you can go educator, start here, students join a class, or on your own, just create a personal account. So we're just going to do that right now. We'll sign in with a email. All right, and we'll just make one up here. So let's see here. Let's do November, was it November 9th, 1955? Any of you seen Back to the Future? I think that's when Marty McFly went back in time. It was 1955, November 9th. Anyway, so we'll create an account. And then the nice thing I like about this is it doesn't do email verification, so you can kind of just make anything up. All right, so we're just going to say, we're just going to call this test account 01 at hotmail.com, and for password we're just going to say password, and then we'll just make something up here, and we'll agree, and we missed something. There we go. Okay, and we'll just save that for fun. Okay, done. And that email is going to get a bunch of marketing emails. All right, so here we go. So we've got this new account here, and so where do we even start? So the whole point of this thing is it allows us to do different things, like do 3D modeling and do circuits. That's what we're interested in. So let me show you this. All right, so we're going to do, and you know just about as much as I do about this. I played with it a few times, and like I said, it's a toy. It's not that powerful. In our course, Crash Course Electronics, we learn about Lab Center Proteus for simulation. We use Altium Circuit Maker, obviously, for most of our circuit design and our PCB design, schematic layout, PCB design. But we also use Lab Center Proteus, which is a an extremely powerful enterprise simulation tool that simulates processors and analog digital electronics. And of course, you can do PCB layout and design with that as well, but you have to pay for it to do that. And when we use Proteus in free eval mode, we can at least run simulations. Anyway, this is totally free. So we're just going to go to create new circuit. And I just wanted to kind of run you through playing with this. It's kind of cool. All right, so I have, now let me tell you, it's very sluggish, even on this very powerful workstation of mine. So hold on a second here. If I can even get my browser to respond to me here. There we go. Okay, so let's put it at about 150, and then you should be able to see everything pretty well. All right, so it doesn't have that many controls. So it's got rotate, garbage. This is undo. I think it's hide or something. And what are these? View, hide, and what is this one right here? Yeah, this is to put a note. Okay, so let's delete that note. This is for wires. So let's just kind of jump right in, and we'll kind of see how to do this as we go. So the first thing is there's code. So you can actually write code here. So we're going to back that off and start the simulation. So this thing is a simulator. It's going to simulate something, simulate some electronics. In our case, we're going to use it to simulate an Arduino. And of course, you may or may not know an Arduino is a single board computer based on the Atmel 328P microcontroller. At least the Arduino Uno, the basic Arduino, is based on the Atmel AVR 328P processor. So if we go scrolling through here, we can also search, and we could say Arduino here, and here it is here. So we'll say Arduino Uno 3, and nothing came up. So let's back off and go like this. There we go. So there it is right there. And if we scroll down, it's got some basic circuits also, all right, but we're not going to use those because we want to kind of figure this out. But these are starters, and you can just use one of these and play with it. All right, and so you know what? Let's do this real quick. Let's just take one of these and click it, and there we go. All right, and like I said, I'm surprised at how slow and sluggish this thing is. It is kind of slow and sluggish. All right, so I'm going to zoom out just a little bit here, and to zoom in and zoom out, you can also use Control. So I'm making the browser larger and smaller with Control plus and minus, but if you hold Control and then the scrub wheel, we should be able to get it to get a little bit, there we go. Okay, so we have the part here, and as you see, as I move it around, it kind of drags everything with it, all right? So let's go ahead and let's just see what's going on here. So we have this simulated Arduino here. Here's the processor. All right, and then we have these 3 piezo speakers, and we have 3 resistors. These are brown, black, brown. So these are 100, 100, 100 ohms each. And apparently they're connected to pins 6, 7, and 8. So someone is going to kind of drive these with square waves, and the hope is probably to make sound out of them, right? Okay, so let's go ahead and start this or run this or do something. So how do we do that? So we go to code, and right over here, what we can see here, these are all of our different blocks. So this is really interesting. This tool allows you to program in one of these graphical drag and drop languages, which, you know, I get the point of these. These are nice, but let's be honest, these are really for children, little kids. You know, I teach my 6-year-old. Actually, I teach her to code with actual code. She writes in BASIC. But she also will use these kind of block languages, and they're fun to play with, but you know, you can't really get what you need done with blocks. It's just kind of silly, in my opinion. But it's really good just to experiment and play with things and kind of show a concept graphically. So, you know, I get it. Anyway, so we have output blocks, we have input blocks, we have notation, we have control, math, and variables. All right, so these are just fun to play with, and then you drag them over. So this is the program right here. All right, and the program says title block comment and then comment. All right, so all these gray ones are comments. Okay, so these are comments. So it's really kind of hard to see what's going on here, but turn off speaker on pin 8 and then play speaker on pin 6 with tone 69 for 0.2 seconds. And it goes through here and does all this, right? Okay, so let's go ahead. And now what we're going to do is we're going to close the code window. So that's our program in block mode, right? In block form. So let's just run the simulation and check this out. Okay, whoever wrote this was not very musical, that much is for certain. So anyway, but it did what it's supposed to do. It's just going to kind of play tones. Now, let's look at the code again. And now you can go into two different modes. Check this out. It's in block mode right now. We can do block and text. So now it opens up the window and it shows you the block version of the program. But then over here, it shows you the actual code generated by it. All right, which is kind of cool. But let's do something. So check this out. So if I click on this, let's see here. I was hoping it would jump over here. Maybe it will. No. Does it jump? Does it jump? The cursor doesn't jump over here to kind of show you what the block is generating as code. But one thing is for certain. When you're in block mode, you cannot edit. So for example, see this POS variable? And if you don't know C, C++, you'll be a little bit lost here, but I'll kind of try and help you through here. So POS is some kind of variable, and I do not see it here in POS equals 0. So that's interesting. So he or she is not even using, I think it's he who wrote this, Greg. Okay, Greg, whoever this is, wrote this and then made this variable and then didn't even use it. So he must have had it for some testing. Anyway, if we try to edit something, so like we'll go right here to POS and notice when I hit backspace or 1 or 2, nothing happens. You can't edit it. The reason why is because if you were to edit this, you could potentially change something that would have no reflective effect in block code space or in the block code language. So they don't let you edit. If you want to edit, then what you have to do is go into pure text mode. And when you do that, it's going to say, are you sure? Because it's basically going to blow everything away and just give you code. And yes, we want to continue, so we're going to go ahead. So now we have our program here. Okay, good. All right, and let's take a quick look here. All right, so these are all comments here. / is a comment, and then /* and / or asterisk. This is a range of comment, a multi-line comment, right? And then we have integer, POS equals 0, which is not even being used. And then in the Arduino will run, and the first thing it'll call is this function called setup all the time, lowercase setup, and inside of here you're going to put your code that you want to happen one time. And in this case, it's using the Arduino library function pin mode, and then it's saying pin mode for pin 8, I want it to be an output, pin mode for pin 6 output, pin mode for pin 7 output, and that's that. So these are all Arduino functions, all right? And again, these are setting up the GPIO or general purpose IO modes of the processor's pins. And you can use whichever ones you want. There's a lot of different pins on here you can use. Anyway, now we go to loop. Now loop is going to be called over and over and over. Now you'll notice that loop has no parameters, and it starts here and then ends here, and then it just falls out. So something else is calling it. What really is happening, and of course, the class that I do on Arduino and embedded systems and so forth and microcontrollers is going to explain this in great detail. But loop is actually being called by C main. The main in C has a loop, and part of that loop makes a call to LOOP. So it calls this over and over. This exits, goes back to main. Main does some stuff for some kind of multitasking and interrupts, and then it jumps right back here. So this will keep kind of getting called over and over and over by something else. But if this was just straight C code, the second it got done here, it would just exit and that would be that. So something's got to call this over and over. So be aware of that. It's not magic. Arduino is just C, C++. It's just C++ 11. Depending on when you watch this video, it's 11, maybe it's 13, maybe it's 17, but right now it's 11. Anyway, then there's some functions here, no tone, tone, and these functions are pulsing out these pins. Delay is delaying in milliseconds. And so that's about it. So it's a very simple program, right? So let's go ahead and let's see if we can do something ourselves. Now, the first thing that I've learned about this tool is that it is not very user-friendly. This is definitely a work in process. And it doesn't do a lot of simple things. Like, for example, there's no delete. You cannot delete this project. At least I can't figure out how to delete it. And I've Googled, and other people can't either. So if you want to delete a project, I'm not quite sure how to do it. So we press, the garbage can. That doesn't seem to help much. Not quite sure how to do that. Maybe someone else can figure this out. Probably if I go back here to Tinkercad, if we do this, and we say create a new circuit, but you see this thing right here is kind of being saved already kind of for eternity, which is this kind of persistent cloud-based technology. Anyway, let's just go create new circuit. All right. And let's go ahead and let's get our Arduino. There it is right there. And I'm just going to click it, and there it is. All right, and you have to get used to the kind of idiosyncrasies of how slow this thing is. And you know, I type really, 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 really fast. Once I'm in the groove, I can type super fast. And what I tend to do with this is I start typing, and then it doesn't type. So I think, oh, I must have made a mistake, and I type what I thought I typed, and then I double type, and I make a mess. So it's really hard. You can see the cursor refreshing. See it flickering? I don't know if you'll be able to see it in the video, but it's actually flickering. That's a refresh. So this is doing some really poor screen updating. So whoever developed this is not updating the screen properly. When something needs updating, it's continually updating, and that's why it is so slow. All right, so we're just going to call this Arduino. We'll call it Arduino SBC for single board computer. It's got a little name. All right, cool. And now we have our Arduino. Now, I want to build a circuit, but before I build a circuit, let's see if we can do something really, really simple, all right? So for example, let's go and I wonder if we go to, let's see if we go to code again. Yeah, okay, so if we go to code, then built in every time kind of is some default code, and look what this says. Set built-in LED to high, wait 1 second, and then set built-in LED to low, and then wait 1 second. So this is gonna blink the LED, this little LED right here. Now I should be able to move this, yeah, and you can drag this around and stuff, okay? And so this is all it's gonna do. So if we go ahead and we run this and start the simulation, I'm gonna put this right here, let's start the simulation. Here's the power LED, and then you can see this little LED is blinking right here, and it's blinking at 1 second, or attempting to. Okay, let's go ahead and stop the simulation. Now, let's put this in milliseconds, all right, milliseconds, and now let's do it for 500 milliseconds, half a second. So this is going to go twice as fast, right? Okay, now let's go and start the simulation. And it should be blinking faster. You should be able to perceive that, hopefully, blinking faster. Now, let's go ahead and look at the code again. And where's the little code button, and here we go, blocks. That's not what I want. Stop the simulation first. Now we can do this. Blocks and text. So here's our code right here. So you can see there's our setup. It sets pin mode, calls the pin mode function for pin 13, sets it to an output. Then it says we have the loop function, which is going to be called by the C++ main over and over and over. So we can put our code in here that we want to execute every single time. And it does what's called a digital write, and this is out of the Arduino library or API, right? And this is just the function that writes to a pin. What pin do you want to write to? 13, what value, high or low? And then delay is a millisecond delay, and then digital write a low, and then delay again. And there's our blinking LED, all right? Now, let's go ahead and let's do some circuit design here. So let's see. So we know that the LED is on pin 13, right? Let's go back here. You can see it's at pin 13. So if we were to go online and look up the pinout of an Arduino Uno, we would find that pin 13 is the built-in LED. So let's just stick with that. And let's see if we can blink an LED on a circuit board. All right, so we have all these parts. Now, the whole point of a simulator is it's going to simulate DC and AC to understand circuit analysis, and it does these simulations. So let's do a breadboard small, and let's click on it. And there it is. Okay, and we're just going to call this bread 1. Okay, all right, and let's put that like that. All right, so the first thing that we're going to do here is let's get some power to this board. So we need to draw some wire. So how do we do that? Well, here's the color of the wire, all right, and then this is the type of the wire. So alligator, automatic. So we're going to use hookup and normal. So let's start up with normal, and then let's pick black. All right, now if you look closely here, here's a ground, right? So we're going to need ground and power. So here's ground and power down here. Here's ground here. This one's closer, so I'm just going to go here. So now notice how I do this, and notice it'll snap. So let's make it kind of pretty. Now, if we put it right here, we could do that. But what I like to always do is bring the power in on the corner of a board. So let's do that. Let's kind of go like this, and we're going to put it right there. Okay, good. So that's nice. So there's our ground. Now let's go ahead and let's bring in our positive power. Now, the Arduino runs at 5 volts, but it also has a 3.3 volt regulator on it these days, so you can get 3.3, but we want 5 volt. Now let's go change our color to red. And remember, Some new students, might think that maybe different color wires do different things, right? They don't. Wire is wire. It's made out of copper, aluminum, or some alloy thereof, usually, maybe with some silver in it. Anyway, the colors have absolutely nothing to do with it, so you can make them whatever you want. But there are color codes, right? Black is ground, red is power, etc. So, and depending on what field you work in, certain colors mean certain things, all right? But we're pretty safe saying that red is going to be a power color. So we'll go ahead and we'll just kind of turn this and kind of make it pretty. And we'll go like this and bring it up here like that. Looks good. Okay, so I'm happy with that. And then you can drag these. Just drag them like that and they'll drag, all right? Now another thing, as you take my course, I'm sure that you have seen that I talk about bypass capacitors, decoupling capacitors, right? And so if you don't know what that means right now, it doesn't really matter. Let's see if we can just put one in here. So we're just going to call this C1, and let's just put it in microfarad, a little bit easier to understand. Okay, 0.1 microfarad, cool. And we're just going to take this capacitor, and now it doesn't really matter where we put it because we can put wires, but so I want it right across these two right here. So I'm going to just do this. And I think this tool will allow me, even though in reality, can I undo that? Yeah. In reality, let me move this over and zoom in a little bit. In reality, you wouldn't really be able to stuff this capacitor into the same hole that this wire would be in, but this tool kind of allows you to do it. So you can kind of get away with a little bit here and there. All right, so we're going to do that, and that's going to smooth out the power coming into our little solderless breadboard. All right, so now what else do we need? We want to blink an LED, so we need a resistor. Okay, so let's look RES. Oop, and I press the button, and let's see what did we do here. Let's try and get this back. Something just happened. Okay, I don't know what I hit, but something happened. Anyway, like I said, this tool is very, very touchy. So let's go back and let's come here and let's go back to code. All right, everything looks okay. Now, so we have our bypass decoupling capacitor inside there. So let's go ahead and get a resistor. There's a resistor. Now, we can place this in a number of different ways. So now the function to rotate, so this is selected now. So let's call this R1 first. Let's start there. Capital R1. Let's go ahead and make its resistance 100 ohms, not 100K, 100 ohm. All right. And so it's going to be brown, black, brown. So that's correct. And now where's rotate? This is rotate. So that's how we rotate things. So what I'm going to do is I'm going to put this right here, right here. How about that? Okay, now we need to take a wire and we need to use pin 13 because if we look at code again, pin 13, and let's go to blocks plus text and let's make this bigger. And there we go. Bear with me. Okay, so pin 13 is the pin that we want. All right, and let's get out of code mode and let's make this smaller. Okay, so we're going to get pin 13 now. Let's just use a green's actually good. So here's pin 13, and we're going to draw a wire, and we want it to actually go right here. So you know what? I'm going to kind of. So now one thing that I notice people doing a lot with these kind of online CAD programs is they're really messy. They draw straight lines. I'm not a big fan of drawing straight lines to things. So kind of make it neater one way or another. Use 90-degree angles or 45-degree angles to kind of bring things in straight. So now let me see here. Can I do this? I'm just curious. What does this do? All right, so that's nice. So that's much better. So there's a curve and the wire is not going into the hole there, but it's going in the hole here. Okay, now we need an LED. So here's an LED here. So you just click on it, and then all of a sudden it appears. Now we got to be very careful here. So let's put it right here and then watch this. There's the cathode and there's the anode. We need the anode facing the positive side. Okay, so where we're going to apply a positive voltage, we need that to be the anode. So we either need to wire this backwards or turn this thing upside down. So let's rotate this. So first let's call it LED 1. Next let's change it to something more interesting. How about blue? Now let's go ahead and rotate it. And now there's the cathode, there's the anode. That's much better. Now I can just the whole idea of a solderless breadboard is that, remember, all of these, you can see the green highlighting, so that whole column is connected, right? This whole column is connected, this whole column, but across they're not, okay? So only in these vertical columns, and then this opening here, this cleft, right, they're not connected. So when you go over here, it's not connected over here. So this is kind of how these wirings work. So we can put this right here. All right, so now the circuit goes up here, goes through here, goes through here, goes through here. Now we need to connect something here and then go back down to ground. So let's do that now. So let's go get a ground. So we're going to get black. So I just need to go here, and I can go here also because all of these are connected. So I can go any one of these that I want. I'm just going to go here because it'll be cleaner, right to ground, and I'm done. So now we've got our LED plugged in. So let's go ahead and let's zoom out just a little bit. All right. There we go, there's our circuit. So now if all goes well, and let's scoot this over a little bit. If all goes well, when we go into code mode here, here's our program. When we run this thing, we should see our LED blinking. And sure enough, there it is. So it worked. All right, now let's go into pure, let's stop simulation. Let's go into pure text mode. It's going to complain. Yes, I want to continue. And let's modify this manually. Now you can see we can modify it, so we're going to just change those. My habit, if you're a programmer like me, every time I make an edit, I press Control S, Control S. There is no Control S. If I press Control S, it's going to try and save this someplace, okay? So we don't want it to do that. It's just saving it all the time continuously, so there's no real saving. We don't need to do that. So let's run the simulation. All right, there we go, and it changed to 100 milliseconds. So there it is. That is the use of this. Let's do one more thing before we go. One more thing. And what I want to do is let's open up a serial terminal. So notice down here it says serial monitor. So there's a little serial monitor down here. So check this out. So what we're going to do is we're going to use the serial function so that we can actually send debugging data over this virtualized serial monitor. All right. So now, normally what you would do is you would go to the Arduino website, arduino.cc, go to documentation and go to reference or tutorials, either is kind of fine. And then if you search for serial right here, go there. You can read about how serial works and what pins it's on and all this, and explains everything, and then all the different functions, right? To get this thing running is pretty simple. So the object itself is called serial, and if you don't know what an object is, don't worry about it, but it's called serial, and all we need to do is say serial begin. So if we look at begin, serial.begin, and you can control this with the speed or speed and configuration. And if you don't put the configuration, it defaults to 8 bits of data, no parity, and 1 stop bit. So we're going to do serial.begin. So check this out. And we're going to do that right here. So we're going to say serial.begin, and we're going to say 9600 baud. All right, and we're done. And then that's that. So now what we're going to do is we're going to do something here. Every time we write to the LED and change the pin, we're now going to say serial.print, and there should be a print function, right? Serial.print, and we're going to say high for high, and this is how you print to it. Oops. And then we're going to say low after we do this one. All right. Okay. And that's it. And it's already saved. So now we start the simulation, and you'll see down here in the serial monitor, check this out. And it's saying high, low, high, low, high, low, high, low. And this is how you can kind of print out information. So the point is, this is another cool tool. You know, so if you wanted to play with Arduino, now there's another one called Fritzing. I've also mentioned that as well, and you may have heard of that. This is just another tool online to kind of play with things, do simulation. This the unique thing about this is it allows a block-based language, so you can kind of do block programming if you like. And it's just instead of getting an Arduino and setting it all up, you can just do this on a computer without hardware and just kind of play with it for a little while and just kind of say, oh, you know, I get it. It's there's a microprocessor. This thing has got code running on it, and we can connect it to electronics and make it do things and write code in C++. And there's a compiler in the background that's compiling it and building a binary for this, an executable, and then somehow it's getting uploaded to the simulation like we would with the real hardware. and so on and so forth. But just a fun way to play with this. And again, this is really more or less a toy. You're not going to do any serious work with this, but it is great just to play with. So I think that's about it for today. I hope you like that, and just trying to show you something you may not have seen before. All right, I will see you all in the next bonus lecture. Bye. Hello, everybody. So this is Labor Day weekend, which means we should all be laboring. I know I am. I have been working in the yard. I've got allergies. I'm dying here. Anyway, we had something happen. Version 2.0 of Circuit Maker came out, which is really cool because we've been waiting for years for this to happen. Probably, I think 5 years, something like that. Anyway, it's not a major revision. The tool is nearly identical. However, there are some tiny, small things inside of the tool that have changed a little bit that may cause some confusion for some students. So I thought I would take a look and show you how these things have changed. Also, the documentation for the tool is being worked on and updated, so the documentation for the tool will be, fixed shortly, or probably released shortly, whatever shortly is. Anyway, so let's go and take a look at what I'm even talking about here. So let's pop up. Let's go to the Circuit Maker website, and what I want to do here is let's start at home. And if I can, let's go to Circuit Maker Desktop. All right, so in the course, when you get to the section on using Circuit Maker, you're going to install the software. So you go to the website just like this, you're going to download it. Everything you're going to do the same. There's just a couple little steps. It's literally you're going to click something in a different way to fork a project, and maybe one other thing that might confuse people. And it's something, you figure out in like 5 minutes. You're like, oh, that's where it is. But you know how it is. Sometimes they make changes to tools and you can't find where something is. It's frustrating. The other thing is, so the big deal about Circuit Maker 2.0, so we've been using version 1.3 to about 1.65 in the course, and over the course, I upgraded and updated it, and like I said, you can't ever tell if there's anything different. It's usually just in the background bug fixes. But with version 2, they did something pretty big. Also in the background, it doesn't affect your design or the tool or how the tool works, but it affects where the data is stored. So the one thing about Circuit Maker is it's a cloud-based tool, so your data is stored on the cloud. Now there's also local copies of it, but the whole idea is it's kind of this cloud-based system, and Circuit Maker was separate than Altium, their other tools. All right, so Altium makes Altium Designer, which is their big design tool, their CAD tool, their multi-$1,000 tool. And it was kind of these two separate things. And so Altium has this thing called Altium 365. And this is very similar to Microsoft's 365, and everybody else has one of these kind of Office 365, whatever it's called. Everyone has kind of one of these, online cloud systems, database, so that everybody can work and share and do all that. So Altium's had this for a few years, and but it's been separate from Circuit Maker. So what they wanted to do was integrate it together. So from your point of view, this is a good thing. It just means that people can collaborate with your files and access them, and they're integrated with Altium's entire ecosystem rather than being this separate Circuit Maker thing. So anyway, I guess what I'm trying to say is this is good, but it doesn't really affect you, right? Unless you really care about it. Okay, so anyway, when you go to the tool, you're just going to download the program like you would normally do in the lectures where we install it. All right, so you do that, you install it. So let's just go ahead and take a look and see what things have changed. Now I'm going to kind of jump around a little bit here to kind of show you some things. So the first thing is when you go online, and let's see here, let's go to my account. Let's back up. Let's go to Altium Circuit Maker. Let's just go to Circuit Maker. Let's try this. Okay. So once you, now another thing that you'll do when you go through the PCB design section of this course, which is, what is it, section 8, you'll install Circuit Maker and you'll create an account on the Circuit Maker account. So one question that you might have is, say that I have version 1.3 or 4 or 5 or 6 of Circuit Maker on my desktop, and then I want to upgrade to version 2.0. Is anything going to happen bad? No, nothing bad will happen. You just upgrade just like you've upgraded any other smaller version, point versions. Nothing will happen. But what will happen is all of your projects will then go live on a slightly different part of the website as far as you accessing them. And let me show you that. I'm going to show you that. So right now, and then of course you always have to create an account on Circuit Maker. And then what happens is, this is kind of cool, is Circuit Maker will create a free Altium 365 account. And these things are pretty expensive. I don't know how much they are. They're $500 a year or $1,200 a year, something big. So they're not cheap, whatever they are. And you get a free one with your Circuit Maker account always. So that's really nice. All right, so anyway, right now I'm signed in to Circuit Maker. Now I'm not looking at the desktop version of the tool. This is just the online kind of version of things. So you can kind of look at things here and do stuff. All right, so now for example, you can see right off the top here, it says the new home of your Circuit Maker projects is on Altium 365. All right, so I'm not going to click that yet. So what I'm going to do here is, I click on projects, and I see all these different projects, and these are different things that I've looked at or that are inside of my Circuit Maker kind of projects list. So I go click on this one, for example, and this is a project from our course. And you can see Crash Course Electronics Magic Wand. So in the course, we're going to build a magic wand, and this is the project. Now, here's the problem. Before, when you would watch the lecture on the magic wand, you would go to this page on Circuit Maker, and then you would just fork this project and make a copy of it yourself, and then you would be able to see it in your copy of Circuit Maker so you could work with it, right? Now, what's happened is that fork button is gone. That's it. That's all that's happened. The fork button is gone. No big deal. So now what we have here is we have something that just says open an Altium 365. So this is kind of something for me. So now I go here and I say, okay, open an Altium 365. Now watch this. So now there's this whole new tool here. Now we're in this Altium 365 subsite of Altium. And then here is the schematic, and here is the printed circuit board. And again, if you've already been through Circuit Maker, this is going to make a lot more sense. If you haven't and you're just watching this video, you may be confused. But anyway, now say that I want to look at this thing right here, okay? So then what I'm going to do is I'm just going to say open in Circuit Maker. So I go ahead and I say open in Circuit Maker. And now what happens is it pushes it into Circuit Maker. All right, so this is kind of the process. So instead of forking something, you're just going to open an Altium 365, and then you're just going to say open in Circuit Maker, and then once you're done here, then you're just going to go right here, and then you're just going to say you're just going to save this project. All right, you're going to save this project to the server, and then it'll be your project, or you can clone the. You're going to clone the project, right? So if we click clone here, then it's going to create, yeah, that's what we want to do. We want to create this clone, and that's how you do the save. So I'm not going to do this because I don't want another copy of it. So that's all you do. You make a clone of the project, then once it's cloned, that's kind of like forking it, and now you have the copy of it, and then you save it and do whatever you want to. Okay, so that's the difference. So let's go back and let's just kind of review here what happened. So before, when you wanted to mess with a project, right, we would come back here, and let's just go back here, and let's say shared projects. So here's kind of all of my various projects. And then you would search, inside of this Circuit Maker tool, and you can do a general search. So if we go back to projects, and let's see here, you can say view all. There we go. And when you do view all, then you have this kind of search tab, right? So say if you wanted to find something like, say the organ, right? You would type in organ, right? And then this searches through, and then you see all these different organs. Then you would find the exact one that's from the course. So it has a very specific name, right? And these are all copies of my organ that people have forked and made. So it's searching the entire Circuit Maker database, and that's why you're seeing all these copies. But here, for example, 555 timer organ, all right? So we go here and we see which one this is. All right, and here's kind of one of the original files, right? So this is kind of the root file. So here's the one that you want, right? Now notice there's no fork again, so you just say open an Altium 365. So again, we would go do that. So you don't have to fork it, so don't fork. Then you just say open in Circuit Maker. So now we go say open in Circuit Maker. And there it is. Now it's open in Circuit Maker. Now notice I can't save it because I can't save it on top of its own name, right? So I have to clone it. Then I have my copy of it, which is on your cloud storage, and now that's the fork of it, and now you're good to go. Okay, so that is the only difference. So that's literally 2 clicks different. In the previous versions of Circuit Maker, when you wanted to clone something, you would do it right here. Inside of this, there'd be a little fork button and you could fork it. That's all. And then it would keep it kind of in your Circuit Maker cloud storage rather than pushing it to your Altium 365. All right. So that's it. So just no fork button, just click open in Altium 365, then click open in Circuit Maker, which is down here. That's all you have to do. Okay. Okay. So let's close a couple of these. And all right. Now let's go back here and let's get to our desktop version. So obviously I've updated this. So if I go, I don't even know if I can find, it's always hard to do things on the fly here. Let's see. I don't want to look at that. Anyway, this is version 2.0. It says welcome to Circuit Maker 2.0. All right, and let's go ahead and let's close these. We're going to do close project. And we're going to do close project. Okay, now that we've closed those projects, they're out of the view tree over here in the project tree. So now let's go ahead and let's do 2 things. Let's bring in a little project that I made previously. So watch this. So we'll go to File and we'll say Open Project. All right, and now we have my personal space and shared with me. So this is a little bit different also. So this is just a little bit more convenient now. So before Circuit Maker used to open up kind of that same view that we just saw. Let's go back and look at it. It would kind of open up this view right here on the window, right? It would open that up in the tool right here in this little area right here. So you kind of had a copy of that web view, that's all. Now it kind of has this, and then you just go through here and search for whatever you want. So I made something a few days ago, and it's called Circuit Maker 2.0 Test. So let's just open that up. Okay, and there we go. All right, and you can see it has 2 pieces here, a schematic and a PCB. Let's just open those up. Double click on them both. All right, and there we go. Okay. And all this is a tiny little, I don't even know what, oh yeah, it's a 555 timer. So like in 5 minutes, I just put together a little 555 timer. So we've got power in, we got a little power filtering, a ferrite bead, couple capacitors, we got a power LED, then I have a 555 timer, put in Astable oscillation mode, and then the output goes to another LED and then goes to a little clock out. So it's literally a little blinker. That's it. That's all it does. And it's got fixed resistors. There's no potentiometer. So if you wanted to mess with this, you could add to a potentiometer so you could adjust it. So it's a cute little toy to make something with. So let's go back in 2D mode. So here's the circuit. So everything is the same. Like I said, so using the tool is the same. So all the lectures, 25, 30 lectures on the tool are all the same. If something is not the same, it's literally just been moved slightly left, right, up, down, or maybe it's in another menu. In general, anything you need to do, just right click on something and that's going to get you to what you want. For example, here's a flood fill, right? A polygon fill. I select it, then I right click on it, and then I can go to properties, and then I'm here. So and before, I believe if I double clicked on, yeah, so now that works also. So before I could double click and get to it, not have to right click and then go to properties. But any little thing like that, just play with it for a little while. Don't get frustrated. Things have just been optimized and moved around a little bit. These tools are big and they adjust them over time. All right, so let's really quick look at how we would build an entire kind of little project really quick. Let's just do something really fast, all right? So let's go ahead and save this. Let's go ahead and save this. Let's close it. We're done with it. Okay, so let's go here to new, and we're going to do a new project. All right, and why don't we call this CM 2.0 Live LED, all right? And what's the description? A simple LED circuit, okay? Spell that right. Okay, create. And here's another interesting thing. It's creating it on your personal space. And like I said, there's personal space and then your shared projects that other people have shared. So this is kind of your little personal workspace, all right? And again, this is all very similar. We're just kind of being redundant here, but I just want to go through a little tiny little project real quick. Now, everything that's cloud-based is slow. That's just the way it is. So it's going to go talk to the server. It's going to go create this project and get it all set up, and then it's going to go over here to our workspace project view and kind of show us the directories and so forth. So I just have to wait for it for a second. And another thing about Circuit Maker is sometimes this thing takes a long time to boot up, and you're not helping yourself by having lots of applications running. So a lot of times, if you can, if you're going to work with big CAD tools, just in general, reboot the computer or close things and just kind of give it a lot of space to work in. So let's wait for this. Okay, there it is. It's finally done. All right, and if we go take a look over here, we see there are no documents added. So what I'm going to do is I'm going to add something to this. So I'm going to select the project here, and I'm going to right click, and I'm going to say add new to project, and I'm going to add a schematic. And we're just going to call this, no, you know what, let's just call this LED. All right, and we have our schematic here. And again, I'm not teaching you how to use Circuit Maker. I'm just showing you a couple little things. There's a whole section, there's a whole course within the course in section 8 of Crash Course Electronics that teaches PCB design using Circuit Maker. So this is just a quick little bonus video to kind of show you Circuit Maker 2.0 is exactly the same. For anybody that's freaking out thinking, oh no, it changed. It didn't. It didn't. It is the same. All right, so here we go. We have our blank sheet here. So let's go ahead and build our circuit. So now, another thing that's changed is when you go to get parts, there was kind of some different layout in the tool here, how you can get parts. So now just right click and then just say place and then just say component, which should be here someplace if we can find it. Part, yeah, that's right. C for component, P for part there. All right, and there. Okay, so now this right here, this thing used to be able to dock over here, and I believe you can still do it, but I haven't been able to figure out how to get it to dock yet. All right, so that'll be a mystery for now. All right, so anyway, let's go ahead and let's build a little circuit here. So the first thing let's look for a, let's say 0805 resistor. All right. And we should probably set a value. Let's say 10K. 10K. Okay, there we go. And let's see, Vishay, thin film, 1/5 of a watt. Looks good. Oh, so now what I did was I clicked it, and then what happened was it showed me the actual part number on Octopart, which is fine. So that's not what I wanted to do. I don't want to click this. I've already got it selected. So now what I'm going to do is say place. So if you click this, it actually goes and shows you the part. That's fine. All right, so now we'll just say place. So now we've got it here. So I'm just going to place it down here. All right, and then I'm done with it. And then this library thing dialog stays up. So that's the one thing. This stays up. So let's see if we can adjust it a little bit here. Okay, so now we've got our resistor, and okay, so I don't like that. I'm not sure why it's showing two things. Let's just do this. Let's do this. Let's do this Vishay one. Let's try this place. That's better. That looks like a resistor to me. Okay, the next thing, let's get a green LED 0805 size, also SMD size. All right, let's look through here. And I like King Bright stuff a lot. Okay, oh, did it again. All right, and let's go ahead and place it. Okay, And last thing, let's power this up with a little terminal block. So let's say 2-position terminal block. Let's see what that gives us. And these are all coming from Octopart for your searches. All right, and let's see here. TE Connectivity, one of my favorite companies, but let's use this kind of smaller profile one. All right, click on it once. It shouldn't go crazy. There we go. Got to be careful clicking. Okay, I'm done. That's it. So now let's zoom in here a little bit. Okay, so we got that. We've got this right here. Let's take this and we will mirror this. And let's see here. Where was, we want to, and I want to see where. There should, I'm trying to remember. I thought there was rotate on this. Maybe it's gone. Anyway, when you select a part, you can always hit spacebar to rotate it. All right. So anyway, we've got it rotated there. All right. We've got our LED here. This is good. We'll put our LED right there. We'll put our resistor right here, and we'll move the part number up here. We'll move this part number right there, and then we will go into wire mode by pressing W. We will start putting some wires here or nets, and we'll just run that right back there. And we'll put this. Oops. We'll put this right here. Okay. Maybe put this up here. If I can grab it. There we go. And you know what? Let's grab this a little bit and let's drag this back. So, and one thing you'll learn when I do the all the lectures for PCB design, a lot of times we just want the footprint for something and we're not going to use that exact part. So we might erase this or erase this and just make it generic, and we'll just put, for example, a 10K resistor. So this says, you know, Vishay and the exact part number and so forth. We don't have to use that. We just want to have a 0805 SMD footprint. So right here I might just change this and say, instead of, you know, putting this entire value here, I might just say, you know, 10K 0805 and just leave it generic. That's all. Just leave it generic, right? And I could do the same thing there, right? Okay, so now we're done. And so now we've got this circuit here. So now what are we going to do with this? Okay, so the first thing is we are going to, let's go ahead and say, we can say save. But now that hasn't been saved to the server. So now we're going to go and say save project to the server. All right, you must save project in all documents. Okay, so this is kind of another little step that we have to do now. With this. So now we're going to say save to the server, and now it says what documents do you want to save. I want to save them all. There. Now you see all these kind of green check boxes. We're good, and then we can also always say validate, and that just updates everything and makes sure everything is good. And then again, we don't need to save to server because it's good to go. Now we have this project. Now here's the interesting thing. So this is the thing from your point of view when you create a new project. So now this has been saved to the server, all right? So this is sitting on the server right now. Now, if you wanted to fork this for yourself, you would just say clone, right? We've already talked about that, all right? But now this is sitting on the server, but everyone else is not going to be able to get to it. So see how it says CM20 underscore live? That's kind of its name, right? That's the prefix to its name. Let's go see if we can find this. Let's see what we have to do here. All right, so we're going to go back to Circuit Maker here, and we're going to go back to, we'll go back home. All right, and then we'll go to, if I can go to view all. All right, then we'll go to search, and then we're going to say CM20. That should be a big enough search string to find everything. So if we look under here, there's only two things. We see the CM20 LED, and what's this thing called? CM20 Live. So we're not finding that. And as a matter of fact, let's just look for CM20 Live, okay? Let's look for CM20. File not found. Uh-oh, what's going on here? All right, so what's going on here is we have to go to Altium 365. Now we can go to it with this link here, which is always on the Circuit Maker page to remind you. You can just click that. So we can click that, or if we've already got it open, like we do here, we can just click it, and then we're kind of in this 365altium.com live, which you're logged into as part of your Circuit Maker. So we'll just do a refresh here. All right, and lo and behold, here is that project right there. So there it is. And if we double click on it, we can go here, all right, and then we can say, now if we go here and we say, now let's just do this, let's just see what happens. Watch, say here we go open in Circuit Maker. Well, it's already open in Circuit Maker, so we don't need to do anything. But that doesn't help us making this thing public. So now the other thing that you have to do is we have to go here and we have to say publish to Circuit Maker. So this is key. So this is something that like I have to do. So all of my projects that were on Circuit Maker, they were hidden because they all got moved to Altium 365, transparent to me, totally safely. And all I had to do was go through here and make sure to publish them on Circuit Maker. So that's all I had to do. So same thing with you. If you want to make stuff public, you got to go in here and make sure to say publish it. So I'll just say publish it like that. All right. Do you want to publish it? Yes, I do. And then watch what happens. And it will publish it. Okay, now it's published. So now let's go back to Circuit Maker. So now let's type in CM20 Live. And if we're lucky, it will work. If we're not lucky, we'll have to do refresh or something. So let's do refresh. All right, and oh, there it is, CM20 Live. Okay, so that's cool. So no photo. I'm just going to open this up. So there's the project. Notice again, there's no fork or anything like that. And now, if we go down here and we say we need to find edit someplace. Where's edit? Right there. And again, this is all shown inside of the lectures on the Circuit Maker program. But you have to go down here and you have two different modes: public mode and sandbox mode. Another thing is in the version 2.0 of Circuit Maker, and I should know this, but in the previous versions you got two sandboxes, meaning two totally private projects that no one can see. I believe in 2.0 you either have 3 or you have 5 projects that no one can see, which is really good. So you can use this to have totally hidden projects. So it's either 3 or 5. All right, I could go look it up, but I hate Googling things and pretending I know something I don't know. So it's 3 or 5. All right, so now we're just going to leave it public so you could access it if you wanted, and then we're done. Or we could switch it to Sandbox, and here's where we could edit all this stuff, and we could just add all these links, and then we can set the different licensing. And let's see, which one's the most restrictive? Here's the least restrictive, so we'll just add that license and be done with it. The least restrictive license. So anyone can do anything with it, and we're done. So that is it. So that is basically, in a nutshell, the changes to Circuit Maker. Notice I didn't have to do anything up here and mess with anything. All of this stuff is all identical. All these things, just a couple things have been moved around when you go to File, and here we have this new clone, and that's really about it. So other than that, bugs have been fixed, features have been added in this whole Altium 365 thing, which is going to be really cool for working with other people and collaborating and all that kind of stuff, and just having all of your projects in one place so that if you ever want to upgrade to Altium's Designer or something, you kind of have all this stuff. So that's about it. Hopefully that helps anybody struggling with Circuit Maker 2.0 if you update to the new version and things are like all of a sudden you can't see where a button is or something. That what we just did is basically all you need to know. That's it. All right. So that is the end of this lecture. So I will see you next time. Bye. Hello everyone, this is a bonus lecture for Crash Course Electronics and PCB Design. So if you're not actually registered into the course, then these bonus lectures, anyone can watch them, so you just might be watching to check them out and see what's going on. So these bonus lectures are added little fun lectures, demos, interesting topics that aren't necessarily part of the course, but things that, you know, after the fact, maybe a student asks for a lecture or there's something cool that I'm working on, so I'll make one of these bonus lectures. So anyway, you don't have to take the course to understand kind of what's going on. You should be able to get something out of it if you have some minimum amount of electronics knowledge, and if not, just listening to it, you'll at least hear about something new and interesting that you can learn more about later, and of course, you know, if you take the course itself. So today what we're going to be talking about are op-amps, or operational amplifiers. And a lot of people are interested in these because they make amplifying signals a lot easier than using transistors or field effect transistors, FETs. And so op amps were invented, I think sometime in the 40s, definitely by the 50s they had them. And operational amplifiers were simply to do mathematical operations. And instead of having a single transistor or FET, a number of transistors, capacitors, resistors, and so forth were kind of put together to kind of create an ideal amplifier. All right, and these ideal amplifiers have properties that just make it easier to work with as a building block, as an analog building block. All right, so right here up on the screen, this is a great book by Texas Instruments. It's a free book. You can get the PDF anywhere. It's called Op Amps for Everyone, and it's written by Ron Mancini. And I'll add this and a number of other PDFs will be in the downloads for this lecture. So there's a few different things you should read. And this is 464 pages. It's not an easy read, and it gets quite advanced as it goes. Just the table of contents is pretty massive. But the first few sections are really a good kind of basis for op amps. Now, if we're going to study op amps really seriously, then like I said, we would need 10 lectures minimum to kind of really deep dive and understand them. So what we're going to do is we're just going to talk about them so that we can just use them. So if you have just a minimum amount of electronics experience, or if you've taken the course or you're in the middle of the course, my goal is to get it so that you can just kind of use an op amp. All right, so let's just start into it. All right, so the whole idea of an op amp is you want to have a amplifier. All right, and the symbol for an op amp is this right here, just a triangle, and you may have seen this before. All right, and it has two inputs. All right, depending how you like to draw things. So we're going to put, we'll just put this one here and this one here. And this one is called the inverting input, and this one's called the non-inverting input, all right? So minus and plus, all right? So we'll put a couple lines there. Then there's an output here, all right? And the output is simply called the output, okay? And then I'm going to label these over here. I'm going to just kind of label them. I'm going to label it V plus, and I'm going to label it V minus. All right, so that's kind of the symbol for an op amp. And then there's also a couple of other things that op amps will need, and they're going to need a positive power supply. So, and then also on this V minus and V plus, we might want to say V in minus, and we'll say V in plus. And then the op amp has two power rails, all right, and one is called V plus, and the other one is called V minus. All right, and we'll get to this in a second, but the idea is that the op amp is used in analog circuitry, so you may want to amplify a signal, and if that signal goes positive and negative, then the op amp itself is going to have to go positive and negative. Therefore, you're going to need two power rails, usually symmetrical. All right, so that's the symbol for an op amp, right? And again, op amp just stands for operational amplifier, so op amp is kind of for short, and it's really just operational amplifier. All right, and the cool thing about op amps is they can be used for amplification, they can be used for buffering, they can be used for addition, subtraction. You can do derivatives with them, you can do integrals with them, you can do logarithms with them, you can do a lot of crazy things. And the reason why is because as you put capacitors, resistors, even inductors inside of the feedback circuit as part of the op amp, the property of the capacitor or the resistor becomes part of the feedback network and the kind of gain function. All right, so that's what the symbol is for an op amp. All right, cool. So we've got these two inputs. So the first thing we have here is this is called the differential input. All right, differential input. So that's one thing. We've got two inputs right here. All right. And then there are some properties of op amp. So inside of the op amp, there's a lot of stuff going on. All right. Now, a lot of people may have read or have seen kind of a famous op amp called the LM741. All right, and this is really similar to in digital electronics. There's a really famous chip called the 555 timer chip, right? everyone knows about the 555 timer. So the LM741 is kind of like the 555 timer of op amps. This is kind of, one of the original, kind of modern op amps that people would use. You don't really use this anymore. There are thousands of op amps now, and every manufacturer that does anything analog makes op amps. So there are thousands, maybe even tens of thousands of different op amps by manufacturers. So I would never use an LM741 anymore, even though I would use a 555 timer, maybe in something real simple. But there's no reason to use an LM741 because it is just the performance of it is so poor compared to modern op amps. But anyway, it's a good model to look at because it's fairly simple to understand, relatively speaking. So I think I have it. Yeah. So here's the LM741 data sheet here, and this is from Texas Instruments, and it shows you, all the different pieces of information, the pinout, the different kind of packages for the op amp. But what I want to show you real quick right now, because we're not really going to care too much about this, I want to show you, here it is. Here's the functional block diagram. So this is actually what's inside of this op amp. So there's the non-inverting input. There's the inverting input. There's a couple inputs here called offset null. There's two of them. We'll talk about that later. Then there is the output, and there's your V minus power supply and your V plus power supply. So to properly cover op amps, we would want to go through and analyze this entire circuit. And I've done this before. A number of times, unfortunately, had to actually analyze this circuit and figure it all out and so forth. But you just do it a couple times just to make sure you understand what's going on inside of there. All right, but we're not going to do that. But I just wanted you to see it's not that complicated. I mean, you can count there's maybe 24 transistors and maybe a dozen or so resistors, a couple capacitors, not too much to it. But there's enough in there to kind of create this idealized version of an amplifier. All right, so let's go back here. Okay, so we've got a differential input, we've got a positive power supply, we've got a negative power supply, we have an output pin, and then we have these two input pins, inverting pin and non-inverting pin. All right, and then we have something else here, which I'm going to call the gain A. All right, so now let's talk about what the op amp kind of looks like on the inside. As far as a model goes, right? We've seen what it actually looks like, right? But let's kind of talk about what maybe a model of it looks like. So we'll change colors here. All right, maybe we'll use this color. And so what does it look like? So if we were to kind of make a mathematical model of this, the model would kind of be something like this. Have our output here, and then we would have our input here, and we'll put this. We'll put the plus input here, and I'll put the minus input here. And then inside of here, there's kind of a resistance here. All right, we'll just maybe call that Rn. And then so here's our differential input again, right? So we've got our V plus in and our V minus in. And then on the output here, what's going on is there's a dependent source here. All right, and there's a resistor. All right, and so this dependent source depends on what this input is, the voltage inside of there, right? And then there's an output. So, and we'll call this again, let's call this V out. So V out equals this giant gain, all right, so this gain, and this gain, so what's the size of this gain? So A equals the gain of this amplifier. So this gain is somewhere in the neighborhood of 10,000 to 1 million. All right, so it's really big. It is really, really big. So the gain is huge. All right, so that's one property of these op amps, massive, massive gain. So you can't really use them in open loop form. The whole idea of the op amp is to create negative feedback, right? And that's a whole other subject, talking about feedback, but we're going to do it and just accept the fact that negative feedback kind of controls the circuit and allows it to be useful. All right, so V out, what does V out equal? So let's go here and we're just going to call this, V in plus, and we're going to call this V in minus. So V out equals what? It just equals A times V in plus minus V in minus. That's it. That's all that V out equals. So we're talking about million, 100,000, a million times whatever the voltage differential is on this input. All right. So that's kind of what the op amp does. Now, as it is right there, that's not very useful because it would amplify so much, it would just ping things to the rails, right, to the positive or negative rails. Right now, but there's some other properties of the op amp. And again, once we have just a couple rules, we'll be able to analyze this. So another one of the properties is that the current going in or out of the VN plus is equal to zero, nearly zero, right? They're talking about microamps or nanoamps or pico or femtoamps, right? Nearly zero. And the current going into this pin or out of this pin is also nearly zero, right? Ideally, it is zero. All right, so there's no current flowing in to this part right here, into this sense resistor. You can think of this impedance. So the other thing is the impedance looking in here, the impedance looking in is nearly infinite. So the impedance looking in is nearly infinite. So rule one, we have A, and this A tends towards infinity. All right, so this gain factor is massive. All right, number two, we have no current, so we're going to call this, we're going to say I plus and we're going to say I minus are both approximately equal to zero. And then we're going to say number three, what else do we have here? We've got the currents are nearly zero, we've got the gain is nearly infinity, and then the input impedance, right? So the input impedance, so we can call this, and this is really a side effect of no current, but we'll just call it this Rin. This Rin also tends towards infinity kind of ohms, all right? So those are, three properties right there. And then there's one more property. So you can see there's this resistor that I've drawn right here, kind of to represent the output impedance of the device right here. So this output impedance, so we're going to say number 4. So we're going to say this R out is nearly 0 ohms. So it tends towards 0. So in the ideal, in the limit, we've got infinite gain. We have no current going into the device. We have Rin is nearly infinite, and then we also have R out as 0. And then there's one more little thing. And when we analyze the circuit, the op amps themselves, one other thing is that V plus with feedback now, V plus will equal V minus nearly. All right, so that'll be the last thing. All right, and this right here, this V plus equals V minus. This is, so we'll say V, and we can just call this, Vn plus because it's just the pin. So we'll say it's Vn plus will nearly equal Vn minus. And this feature right here, this property, is called a virtual ground. Okay, virtual ground. All right. So as we analyze things, if we know the voltage on, say, Vn plus, we can then, by inspection, say that the voltage on the Vn minus has to be the same. Has to be the same. So, and again, you say, well, what if I put 5 volts on here, and what if I put 2 volts on here, right? Well, obviously 5 volts and 2 volts, they're not the same, right? So you've created a paradox yourself. But when you have the feedback loop and so forth, the device itself will adjust the other input, will adjust the input so that these two inputs match. So if you force yourself on the inputs and force them to different voltages, obviously, this is not going to be maintained. But when you use the device as it's supposed to be used, then this property will be maintained. All right, so let's remember them. The gain is nearly infinite. There's no current going into or out of the input and output for the plus and minus. The output resistance is 0. The input resistance is nearly infinite also, and we have this virtual ground. So we have those properties right there. All right, so those are our properties. So now, given those properties, let's see how we can use this device. All right, so what I'm going to do is I'm going to show you a couple of different circuits that we can make with these devices to amplify signals, all right? And then we're going to analyze them really quick, and see what comes out of the math, all right? Okay, so let's go get another color for fun. All right, so let us do this. All right, so the first configuration we're going to look at, let's look at the, it's called the inverting amplifier. All right, inverting amplifier. All right, so here we go. So we've got our plus, we've got our minus. All right, I'm going to do this right here. I'm going to call this V out. All right, we've got our input here. We've got our other input here. All right, and now we're not going to show this all the time, but just for now, so that you get the hang of it, we're going to have V plus and V minus, and we're going to hook these up to some voltage, right? And, maybe it's 9 volts, maybe it's 12 volts, maybe it's 5 volts, but for now we might say maybe this is like, plus 12 volts here, and this would be minus 12 volts here. All right, so the first thing is when you use op amps, you're going to have split supplies unless you do something about this. So this is a big problem, right? Most digital circuits don't have split supplies, right? We have 0 and 5 volts, or maybe we have 3.3 volts, or 2.5 volts, or 1.8 volt, but we definitely don't have a negative supply. Now your PC does, right? A PC power supply, ATX power supply, whatever's in your modern PC, it does have a negative power supply. For things that require, this kind of other power rail. But most things that, you're going to build or I build do not have dual rails. So we're going to have to work around this at some point. But for now, we're just going to pretend we have access to a negative and positive supply. Okay, so now how do we do this? So check this out. All right, so I'm going to just kind of put some wire here, and I'm going to make sure this is connected nice. All right, so what we're going to do is we're going to put this here and put this here. All right, so we are going to, first, we're going to simply just ground this positive input. And then what we're going to do is, I think I'll draw this in a different color, is we're going to take the output here at V out, right? We're going to take that output, we're going to connect to it, and we're going to put a feedback resistor, just like this. All right, and we're going to connect it right back to the input. All right, then coming into the device, we're going to have an input resistor, right? And we can call this, let's just go ahead and we're just going to call this Rn, and we're going to call this RF. In lots of analyses, people will call them RF for feedback. They'll definitely do that, but they might just call this R1, or sometimes they'll call this R2 and R1. The bottom line is there's only 2 resistors, 2 of them, so R2, R1, whatever. Just don't get them backwards, all right? Just kind of whatever you label them, make sure you're careful with things because we're going to start messing with signs here, all right? So let's go ahead and grab another color here. And all right, so now we want to analyze this. So we know our rules. So our rules are we have A, right? And this A is tends towards infinity. This is the gain of the device. We have this Rn, which also tends towards infinity. We have this R out, which tends towards 0 ohms, right? And we have no current going into either of these pins. And we also have this virtual ground where these two things here are practically at the same voltage by definition of how this thing works. So let's see if we can analyze this, all right? Here we go. Okay, so we put our source over here, and this is where our actual input goes, all right? So we're going to put our input right here. So here is our voltage supply, whatever our input is, okay? And it's also connected to ground. I'm just going to call this VS. So this is what we want to amplify. This is whatever signal. So this is some small signal here, some small signal. And we want to amplify it, all right? So this might be DC, it might be AC, but whatever it is, we're going to get a current, and this current is going to go this way, all right? And it's going to go through this resistor, fine, all right? It's going to go here like this. So I'm just going to call this IS here. All right, so as this current is flowing here, none of it can go inside of the op amp, right? So nothing is going to get inside of the op amp. However, this virtual ground right here, this virtual ground, right, is sitting here, right? And this means that this right here is at 0 volts right here. So this is at 0 volts because we have it right here. So this point here is kind of at ground also, all right? So this point's at ground also, all right? So now what's going to happen is we're going to try and track what's going to go on with this current here. Where is this current going to have to go? So the current can't go down inside this op amp. So the current is going to have to flow up and through this feedback resistor. All right. So now this is where it gets tricky. You have to just kind of trust these rules. So we've got this current here flowing here, right? And what is this current? So this current that we have flowing here is simply Rn divided by Vs, all right? So this Is here, this Is is equal to, what's it equal to? It's equal to Vs over what? Rn, right? So that's what that current is equal to, all right? But that current has to keep flowing up here because it can't go into this op amp. But this voltage here is going to get virtually pulled to this ground right here. So now let's see what happens. So this is at 0 volts. End of story. This is at 0 volts. So if this is at 0 volts, then we're going to have this V out right here. All right, so this is going to be kind of what V out is. So now what is the current? What's the current that's flowing here? So let's be very careful here. So the current that's flowing here, so here's this Is, right? And then that same current is going to be flowing here. But what is that current? All right, so that current is, let's be careful, we're at 0 volts right here, all right? And the current is going this direction, right? So it's going this direction. So it would be this voltage minus this voltage over the resistance. So it would be 0 minus V out over the resistance. That would be what the current is. Okay, so it would be 0 minus the output over the resistance, which is what RF, our feedback, right? And 0 minus V naught is just minus V naught. So this just equals minus V naught over RF. Okay, so let's take a look at that. So now this and this are equal, right? So we can just rewrite here. Let's go Vs over Rn equals minus V naught or V out over RF. Okay, and instead of, so instead of, just make this, instead of me calling this Vs, let's just call this Vn, all right? I'm just going to call this Vn, all right, on the next line. We'll do it on the next line. So let's just go over here, and we'll say that Vn over Rn, all right? This is also, we'll just say we can also call it Vn. Vn over Rn equals minus V out over Rf. Obviously, anybody that's good at math has already gone many steps ahead of me and figured this out. So now what we can say is, what's V out? So what's V out? So I'm just going to move things around. So I'm going to move RF over here. So I'm going to move RF and put it up here. And once I do, and then I'm also going to move this minus sign. So then what am I going to get? I'm going to get, and I'm going to flip things around, V out equals minus RF over what? Rn, and then the whole thing is simply times Vn. That's it. So what's interesting is, first, the amplifier is inverting, and we said that. It's an inverting amplifier. So whatever you put in 1 volts, you're going to get a negative voltage out. But the gain of the amplifier has nothing to do with this A. So if A was 5,000 or 50,000 or a million, it has nothing to do with it. It just has to do with these 2 resistors. That's it. So the gain is minus RF over Rn. That's what the gain is. So the output voltage is simply V naught equals minus RF over Rn times Vn. And that's it. So if we were to set, say we set RF, let's go here, and set this equal to 10K, and then let's set Rn equal to, say, 1K, then that would be 10 divided by 1, so we would have a gain of 10. So whatever voltage you put in, right, it would voltage amplify by 10 and you'd get 10 times more out. So if you had millivolts, a very small signal, we could set these resistors so that we amplified by 100 times or 1,000 times, right? You don't want to go much farther than that. If you do, you want to cascade these together, but you can very easily get 10 times, 100 times, and even up to 1,000 times of gain with one of these op amps. All right, so that is the inverting amplifier configuration. That's it. So that's how you kind of do the analysis. All right, so let's go ahead. Let's do another one. Let's do another one. All right, let's do another one. And okay, so let's do the there's a non-inverting. All right, so let's do the non-inverting version here. All right, so this is going to be the non-inverting. And there are so many things you can do with op amps. It's just crazy because they're just like black boxes, analog amplifying black boxes. You can make them do all kinds of stuff. So anyway, you can get kind of crazy with it. And there are, books that just have circuits, just hundreds and hundreds of configurations that do crazy things. So anyways, let's do non-inverting. All right, so different people draw this in different ways, and I do it in different ways also, depending on my mood. All right, so let's just see what kind of comes out here. I guess there's a ghost. Oh. Now, one thing, if you're taking my course, you know that I do everything unscripted. I just do it as I go. I just come up with it. So there's no script, so I never know exactly what I'm going to do. All right, and that's half the fun of it. So it's very realistic, just like we would be lecturing in school, in class. All right, so again, we're gonna have our two power supplies, and this time, just for fun, I'm just gonna call this positive one. I'm gonna say plus V sub CC. I'm just gonna call this minus V sub CC. All right. Okay, and then here's gonna be my output again. All right, and I'm just gonna call this V out. All right, and this time, let's see here. I want to figure out what I want to do here. Let's say, let's see here. Let me see which way I want to draw these. Let me see what's my favorite way of drawing. Yeah, you know what? Let's do it like this. Let's do it like this. Okay. All right, so these will be our inputs like this. So there will be our non-inverting input, and that'll be our inverting input. Now, so here is where we're going to put the input in. So let's go ahead and pick a different color here. Why don't we pick orange? We haven't used orange yet. All right, so here's where we're going to put our input, and this is going to go directly inside here. All right, so right here, plus to minus, and again, this could be an AC signal as well. So we're going to call this VN, right, like that. All right, now where things get interesting is in the feedback network. All right, so in the feedback network, it's kind of interesting. All right, so let's take a look at how that goes. So what we do is we take the output here, and what happens is this: come through here, and then we do one resistor like this, and then this gets tied right to that inverting input, and then another resistor goes to ground like this. All right, and then again, depending on what you read or whatever, what reference you look at, this will be called RF, or it'll be called R2, and this will be called RG for R ground, sometimes. All right, so this is the non-inverting configuration. All right, so this is the non-inverting configuration, and let's see. Why don't I go ahead? I'm going to go ahead and I'm going to show you what the amplification is. So let's do that. So the non-inverting configuration, this is what you're going to get. You're going to get, and then we're going to derive it. All right, so this time we'll just show you the answer. So V out, this is kind of interesting, equals 1 plus RF over RG times whatever the input is, VN, right? Always times the input. So the gain factor here is RF over RG. And so for very large RF and very small RG, this number is going to be very large, and this one will get it'll get dominated by this term. But for, like, if you had RF equals 10K and RG equals 10K, that would be 10 over 10. That would just be 1, and 1 plus 1 would be 2. So you can't just throw it away. You can throw it away if the RF is large with respect to RG. All right, but that's this is the gain right here for this configuration. Okay, so let's try and figure this one out. Let's see what we can do. All right, let me get over here. Okay, let's see. Let's go get a different color for fun here. All right, so let's see here. What can we do to figure this out? So again, as usual, let's see if we can use the rules. And what are the rules again? So we know this thing has this massive gain. We know that the input impedance is infinite. We know that there's no current going into or out of these input pins. And we also know that the output impedance is nearly 0. All right, and then we also know that there's this virtual ground going on. No matter what, these two pins are always going to be at the same voltage. So this is the trick that is necessary to analyze this, because otherwise you're like, well, how do I relate Vin to any of this out here? Well, how you do it is because we know that whatever's on Vin has to be here. All right, it has to be right here. So let's go ahead and do this. All right, so here we go. All right, so if you've stared at it for a couple minutes, you may not know where to begin. You could start playing with currents and whatnot, but there's even a better trick. So take a look at this. So Vn is here, right, on this non-inverting input, which means it's here. So that means that Vn is right there, which means this node, this entire node, right, this entire node is all Vn, right? It's got to be Vn. Okay, and we know that this is V out, right? So we take a look here and we say, well, wait a minute, we've just got a voltage divider here, right? We've got RF and this RG creates a voltage divider. And the voltage right here, which is also Vn, has to be the voltage that would be generated by this voltage divider. So let's do this. So check this out. This is almost silly. It's so easy. So Vn must be equal to, what must it be equal to? It must be equal to V out. All right, and then remember your voltage divider equation. So we've got a voltage divider here. I've got a voltage, and then I've got a resistor and another resistor, and I'm taking this node. So what I have right here is this. Let's just take a look at this real quick. So I have V, we'll just say VCC, and then I've got one resistor, and I've got another resistor to ground. Okay, this resistor up here is really this RF. This resistor right here is really this RG. And I want to know what that voltage is right here. What is this? All right, so all that voltage is it's RG over RF plus RG times this V sub CC. Okay, so that's what that is. So this is all that's over here. So Vn has to equal V out times RG over RF plus RG. Okay, all right, so let's flip this around now. So I just want to move things to each side. So what I'm going to do is I'm going to take this term here and I'm going to flip it over here. So I'll have to invert it, right? So, and then I'm going to flip the whole thing around left to right. So I'm going to get V out equals, so I'm just getting V out equals, I'm just going to take this over here. All right, so V out equals, what does it equal? It equals RF plus RG over RG, and all that is times Vn, okay? So I didn't do anything tricky. I just took this term here and I just moved it over here, and of course I had to invert it, and then I just wrote it left to right, right to left. So I got this. Now look, check this out. So what do we have here? We have V out equals, what's RF divided by RG? Well, it's just RF divided by RG, no love there. We can't do anything there, right? But what's RG divided by RG? That's just plus 1. and then again the whole thing is times V in. So there is our transfer function again, and you'll notice that this is equal to this up here that I told you in the beginning. So that's it. So now if we put in a positive voltage, we'll get a positive voltage out. If we put in a negative voltage, we'll get a negative voltage out. So that's the non-inverting. So you might say if you're going to use a non-inverting configuration, you definitely don't need to have a negative supply. And yeah, that's true-ish. You can get away with that. All right. So now we've seen the two different configurations. All right. Now let's talk about how do we get away with, so how do we get away with using only a single rail supply. So I just want to use a single rail supply and I want this to go to ground. So how do we do that? Okay, so how we have to do that is what we need to do is we need to take this virtual ground, so whatever the virtual ground, say like here, or for the inverting configuration, so when we have the inverting configuration, let me come here and draw that real quick. So here's the inverting configuration. Let's go draw this really quick here. And so we've got the output here, and let me see which way do I want to draw this. I want to draw this, let's draw it like this, and this right here would normally be to ground, and then we would have our resistor here, and this is our R in, and then we have our output here, our V out, and then we have our feedback resistor here, like this, and it goes like this, okay, and then this right here is where we put our V in, and then this of course is our V out. So now in both cases, the trick is that this virtual ground, that's not bright enough. Let's go green. This virtual ground right here, make sure that whatever is here, which is ground in this case, is here. So what if we were to increase this ground and put it halfway between the rails? So in other words, say if we only have a positive 12 volt supply, and then we have 0, which is of course ground, so we don't have a negative supply. So what we do is we just kind of go up here halfway and we say, well, we're going to pretend that 6 volts is ground, so that 0 is kind of negative 6 volts relative to 6 volts, and 12 is positive 6 volts relative to 6 volts. So the whole point is we're going to put the op amp halfway in the supply, from ground to positive, and that's going to get us the ability to be able to use a single supply. So in this case right here, whatever I put here, we're going to call that V sub CC for the positive, and this is your V plus, and then I have this connection, which is our V minus. We're going to put this directly to ground, but then we're not going to put this to ground. What we're going to connect this to, we're going to have to create V sub CC over 2. We're going to have to create this V sub CC over 2. And likewise here, we're not going to put this to ground. We're going to connect this also to V sub CC over 2. So that's the trick that we're going to do. So to use a single supply or a single rail power supply with op amps, there's no way around this. We have to do this. So this is one little glitch that makes things a little bit difficult. So, all right, so I want to wrap this up so we don't take too long. So what I want to do now is I want to show you, of course, I always want to show you a circuit and a simulation, something so you can see this actually working. But let's go back to some of the documentation, and I think, yeah, so I think I have a document here someplace. Oh, here we go. Yeah. So, and this is a great little document. This is also from Texas Instruments, written about 21 years ago, right? And it's still, this is what I love about electronics and math. It's just forever. All right, so this talks about single supply op amp circuit collection and how to do things, all right? So the bottom line is, we'll take a look right here, and you can see that in this circuit right here, let's make this a little bit bigger. In this example right here, this is kind of what we've been doing, right? So we have a positive rail and we have a negative rail, and we're stuck with this because we have a plus supply and a minus supply. But what if we just want to have a ground and a positive supply. Well, then in this non-inverting input, in this case, we need half the supply. So how are we going to do that? All right. So one way to do that would just simply be, let's just get a voltage divider. Now, and the reason why this works is, you'd say, well, don't you need a regulated half supply, right? Yes, sort of, if you were going to draw a current out of it, but we're not going to draw any current. So there's going to be very little current going into the op amp. So we can just use two resistors, right? These are 100K, and that's going to burn a little bit of current to create this voltage. And then this capacitor right here is a smoothing capacitor to filter out noise. So what we get is, at this node right here, we'll have V sub CC over 2. And then you don't even need this. So what they're doing here is they're using this op amp as what's called a unity follower or buffer. So they're actually using an op amp itself to buffer this signal, but you don't even really need this. So you could just cut this piece out here, and right here at this node, you've got your V sub CC over 2, and you're done. Or you could use a precision voltage regulator or voltage source that can go half rail.